Hello, Kevin. Hello, okay.
Yes, we can hear you just fine.
Okay, thank you. So, yeah, share the screen is the first the slide of the first speaker is a wallpaper of the first one.
Yes, that looks good.
Okay.
And just so you know, Kevin is currently working on
On
the
video download.
link to
Yeah.
download.
Yes. Okay, no
Okay.
problem. So, how does it sounds online?
Yes, this looks and sounds great.
Okay, thank you.
Sure.
schedule 10分钟，所以我们可以慢慢来。然后偶尔会。
Okay, everyone, thank you for showing up this early. This may be unseasonably early for most of you. However, we have a very crowded schedule, and we apologize, but there's nothing better we could do. I'm Boyan Yang, and this is Kai-Min Chung, and we are the general chairs. If you have any problems, find us or find one of the people in the bright yellow T-shirt. Not that guy, but accept no substitutes. If you need Wi-Fi, look for the piece of paper around. We have the information written up there, and it's obvious, and the Wi-Fi password is Asiacrypt 2022 in all small letters. Okay, Asiacrypt and then 2022. And so for those who needs it, behind your badge there is a easy card, which is our Metro card with about $3 on it. So you can write something like 5 or 6 times on a bus with it, for those who asked. And finally, before we start the first session, we would like to tell you that there is a rump session. And we have the chairs of the rump session.
Hi everyone. Does it work?
Yeah, it should work. Oh.
Okay, hi everyone. I'm Khan. This is Matthias. We are the rump session chairs. It's gonna be here on Wednesday at 8:30 p.m. Wednesday night. So please submit anything funny, interesting, a song, whatever. So the deadline is Wednesday noon. Thanks.
And finally, those who would like to join the official excursion, please sign up at the registration desk by noon today, and after that, we may not be able to accommodate you. Okay, I think we should start the first session in a few minutes, and then at that point we will hand the podium over to our program chair, Professor Shweta Agrawal, and we take a few minutes break. Okay, Shweta, I think you can probably, you can either do it from where you sit, or you can come over to the podium to, we have 5 minutes. Yeah. Okay.
Good morning, everybody. I'd just like to add to what Boyan was saying. So, apologies for starting so early and having such a crowded schedule. And this was actually not the general chair's fault. This was actually my fault because we had so many fantastic papers. We still had to reject several papers that had very positive scores. So, yeah, we felt like we needed to accept as many great papers as we can, and I hope that everybody will enjoy the program.
And I also need to apologize to certain attendees. And this entire hotel is under central air conditioning, so it is essentially not possible to adjust the temperature. So, like if you came with the expectation that Taiwan is a very hot area, we apologize, but you know, put on an extra shirt or something. Yeah.
Good morning, everybody. Welcome to the first session of Asiacrypt. And this session will feature all the award papers. So I'm very happy to invite you all to the paper that won the Best Paper Award at this Asiacrypt, Full Quantum Equivalence of Group Action, Discrete Log and CDH and more. This is a paper by Hart Montgomery and Mark Zandri, and Hart will give the talk.
Thanks a lot, Shraddha. Hi, everybody. I'm Hart, and today I'm going to be talking about the full quantum equivalence of group action, discrete log, and CDH, as well as some other related results. And this is a joint work with the always excellent Mark Zandri. So let's get started. So for a brief outline of what I'll go over today, I'm going to start by discussing some background on group actions. I'm going to argue why we should study group actions. I'm going to go over our results, And then I'll go over an overview of some of the techniques behind our main result, which is the quantum equivalence of group action, CDH, and discrete log. And then I'll go over some open problems in future work. So let's get started. You all are probably familiar with group actions. Who's used to group actions here? Some people? Awesome. So it's really a pretty ancient mathematical primitive. A group action is just a tuple of a group, a set, and a mapping that satisfies the identity and the composability properties. And you can think of the composability property as sort of an analog of associativity in groups. In this talk, I'll mostly be focused on what's called regular group actions. And these are sort of simpler to think about. And what a regular group action is, it's a group action where for any two set elements, x1 and x2, there's a unique group element such that x2 is equal to g star x1, where star is, of course, the mapping. And this leads to a number of nice facts about the group action. For instance, the set and the group have to have the same number of elements. And for a fixed set element, little x, g star x is a bijection on x. Most group actions used in cryptography are regular, and we'll warn you when we use non-regular group actions. So what about cryptographic group actions? These have a long history in cryptography, going back to the work of Kuveni's in '06. And before we start by defining hardness, let's think about some efficiency things that math people don't really bother when they define group actions. So we're going to start by assuming what's called an effective group action. And I don't really want to dig into this definition because it's a little bit tedious, but what it basically means is that the group action works like you want it to work. Group action operations and group operations are efficient. There are efficient ways to sample uniformly random group elements, and set elements have unique representation. We'll also assume abelian group actions because, well, our results only work for those, and non-abelian group actions are not very useful for cryptography, particularly public key cryptography. And finally, since every abelian group can be mapped to the additive group of integers for some integer p using a quantum computer, we'll often just assume that our group is the additive group of integers because we can efficiently compute this mapping. And if you want to see more on this, there are a bunch of papers that have gone over what's called known order group actions. So let's define some hardness problems for group actions. So here I'll just put on the screen the group action discrete log, CDH and DDH problems. And I'll note that these are very analogous to the traditional definitions over groups. You really just replace exponentiation with the group action operation, and the definitions are similar. Like for discrete log, for instance, given two set elements x1 and x2, the problem is just to find some group element such that g star x1 is equal to x2. I'm going to ignore some of the subtleties with sampling elements. So for now, we'll just assume that everything is uniformly sampled. Now, it turns out that you all have probably been using group actions for much longer than you've noticed. Group exponentiation is just a group action. And how is this the case? Well, if we set the set of our group action to be the group G, and we set the group to be the exponent space ZP, then group exponentiation is just a mapping that obeys the axioms of the group actions. And this is a little bit special and confusing because the set is a group, and this causes the quantum insecurity. And the main issue is that there's a set mapping for group exponentiation, which is just group multiplication. And in general, for group actions, there's no structure preserving set mapping. So it turns out that many other cryptographic group actions, assumptions are group actions in disguise. I'll talk about isogenies in just a second. Stickles key exchange protocol and related work, if you've ever seen that, as well as very recent work done on the semi-direct discrete logarithm problem are all group action based. So let's talk about isogenies. As I said before, certain isogeny-based crypto primitives can be modeled as group actions. I don't really want to go into the gory details of this because there have been a number of papers that are written specifically on this topic, but I'll say that psi-fish and its derivatives are effective group actions, as we defined earlier, and our work will directly apply to this. Seaside is a bit more complicated. Classically, it's something called a restricted effective group action. Our results apply here with some caveats, and I'll explain this more in a minute. And finally, SIDH and some recent follow-ups on that, are not group actions. And luckily for us here, these recent attacks do not appear to apply to group action-based isogenies. So one last thing on group actions, sort of how do they work? Key exchange from group actions is very simple. So if we have an abelian regular group action where the CDH problem is hard, well, setup is quite simple. We just start with the group action and we pick an initial set element. And Alice and Bob run a symmetric protocol where they each sample a secret group element. They compute the action of the initial set element with their group element. They send that to the other party, and then they can generate a shared key using their own secret group element. Correctness holds by the properties of the group action, and the hardness just follows almost immediately from group action CDH. So you might be asking, why should we study group actions? Well, almost all of our post-quantum crypto systems are based on lattices. And what if an advance in lattice cryptanalysis, say, renders these schemes much more efficient because we have to use larger parameters? As NIST suggests in their updated call for post-quantum digital signatures, we don't want to put all of our post-quantum eggs in one basket. And it turns out abelian group action-based key exchange protocols, like those from isogenies, are some of the most promising alternatives. But these constructions are very new, and the security is not super well understood. And this has led to some surprising results, like the excellent work done on attacking SIDH recently. So what can we do? We're looking for ways that we can establish confidence in group actions. And that's sort of the point of our work. Our main result is that we show the group action CDH and discrete log problem are quantum polynomial time equivalent for abelian group actions. And this is nice because key exchange requires CDH hardness, but the security analysis is much easier, and the security problems generally are much easier to state for discrete logs. So this gives us sort of a best of both worlds thing. And we sort of solved this folklore problem stated by Bonet and Lipton about the Diffie-Hellman protocol being equivalent to discrete log, although we obviously only solve it for the quantum case, and the much more famous and hard and interesting classical case is still wide open. So why does this matter? Well, you can probably guess what I'm going to say here, but it's good to have confidence in existing group action protocols and simplify what's sort of needed for these big attacks. And for theoretical security now, we only need to focus on the discrete log problem, not the CDH problem. This also makes building new group action-based key exchange protocols easier, because if you want to build a new group action-based key exchange, you really only need to focus on the hardness of the discrete log problem, not the more complicated CDH problem. And this has sort of already been used for some new constructions. And finally, I think it's just good to understand group actions since they're so ubiquitous in cryptography. So some other results we have. We show that generically group action DDH and CDH are not equivalent. We construct a very basic generic group action model that we use in some of our other results. We conjecture that the dihedral hidden subgroup problem is equivalent to discrete log on a generic group action. We show a very little bit of evidence suggesting this. And then we have a bunch of results on what's called restricted effective group actions. And these are sort of used to model Seaside classically. So informally speaking, a Riga is a group action where the action can only be computed on a fixed set of generators. And we define this problem that we call Riga cis here, and we show that if you can solve this problem, then our reduction goes through. But we also show a bunch of other connections between this problem and Rigas, like if you can solve discrete log on Rigas, then you can solve this kind of lattice problem in disguise. So we have a bunch of results on this, but there's a lot of work left to be done to fully understand this connection. So with that in mind, let's go over some of the core techniques of our main reduction. The starting point of our work is an ePrint note from Galbraith, Panny, Smith, and Vercauteren that essentially encapsulates the following idea. Suppose we have an abelian group action, and we define a CDH function relative to a base set element X that just does exactly what you think it does. It just outputs the CDH of two elements. Now, suppose we had a perfect adversary for this CDH problem. Well, the observation is that this adversary induces a group operation on the set X so that the tuple of X and the adversary forms an abelian group H. And this is not too difficult to verify. The elements of H are just the elements of X. The group operation is the adversary's computation. The identity element is the base set element. Inverses exist. You can see that the group would be abelian if the group action is abelian. And closure and associativity are also pretty straightforward. It's also the case that if G is ZP, then discrete log is well defined over H. You can sort of have a nice notion of exponentiation. I just put up a couple of examples why that might be visible there. And we can assume this, remember, since we can compute this mapping for any abelian group G if we have a quantum computer. So the core idea of GPSV18 is to consider this A-induced abelian group H, and notice that a group action discrete log challenge on the abelian group action is just a regular discrete log challenge on this induced group H. And then we can just apply Shor's algorithm and solve for G. The problem for this is that we need a very low error rate on our CDH adversary A for Shor's algorithm to work. So it could be possible that group action CDH was broken with probability 0.9, which would effectively break key exchange, but the discrete log variant was still hard. And so this problem was left open for non-perfect adversaries. So the core approach of this work is to take a CDH adversary with non-negligible advantage and amplify it to essentially arbitrary advantage. And then we can follow the roadmap suggested by GPSV18 and complete the reduction. To show how this works, I'm going to start by explaining a method that doesn't work, and one that you're all probably familiar with, which is classic group-based CDH amplification. So you all have probably seen this in your introductory cryptography class. Many of you have probably taught this reduction. But suppose we consider an adversary that on input G to the A, G to the B, outputs the correct CDH tuple, which is G to the AB, with probability P, and G to the UAB with probability 1 minus P for some element U. Now this is a simple adversary, and it's a pretty good adversary, but it'll be useful to examine. So obviously, given a challenge instance, we can re-randomize it, right? We can sample random integers, we can multiply in random group elements, we can call the adversary on these randomized terms. Sorry, this is running over. We can cancel out the re-randomization terms, and then we get these de-randomized terms. With probability P, we get the right answer, and with probability 1 minus P, we get something else. And the key point is with probability P, we get something fixed, and with probability 1 minus P, we get something that's uniformly random in U. And so we can leverage our adversary into an almost perfect adversary through repetition, as only the correct answer is likely to be repeated in any polynomial number of trials. The problem is this doesn't work for group actions. We critically use the fact that we could multiply group elements, and there's no analogous operation for set elements. So if we try to go through this process for group actions, we have an adversary that does almost exactly the same thing as before, AB star X with probability P and UAB star X with probability 1 minus P. We could try a similar approach. We could re-randomize, call the adversary, de-randomize, and then get output. But the problem is we're getting the same output here, and we really don't gain anything from re-randomization. So what can we do with this? Well, in the previous example, sort of the obvious thing to do is to say, well, if P is not too close to 1/2, we can just sample enough times, right? And then we can apply some statistical bound. But what if P is equal to 1/2? What do we do? And here I'm going to introduce just a little bit of extra notation. I'm going to overload the CDH function, and I'm going to define an identity element. The first idea is the following. Suppose we run our adversary and get both AB star X and UAB star X. And if we run it enough times, presumably we'll get them both, right? We can get them both, but we don't know which one is right and which one is wrong. So what if we feed these back into A? So the key observation is the CDH function is sort of invariant over feeding it the identity, right? If I send you a CDH function in classical groups of like G and G to the B, it should respond G to the B, right? So we can apply this observation and use it to sort of catch the adversary cheating. So In this case, right, if we feed these terms back into the adversary, A on X and AB star X will output AB star X and UAB star X, whereas A on X and UAB star X will output UAB star X and U squared AB star X. And note that this second set of outputs is different from the first one if U squared is the identity, whereas the first set of outputs is the same. And so if U squared is not equal to the identity, this allows us to tell which output is correct with probability 1, and we can naturally extend this idea to other distributions as well. So this sort of leads into a strategy we use in our proof that's called shift invariance. And for this slide, suppose G is a prime order cyclic and little g is a generator of this group. We can, I emphasize not efficiently, even quantumly, we can't efficiently compute this ordering, but we can order set elements such that the ith element is G of the I star X. And this gives us sort of a picture of shifting, where if we let A prime denote the distribution of A sort of run many times, you can either think of an empirical or imaginary distribution. Then we sort of put A prime of X on the top and A prime of WX on the bottom, where W is just G squared X. And you can see that this is just a shift. So as I said, we can't use this ordering without solving discrete log, but it's useful to think of shifts this way. And the point is, we can check for equality and matches across distributions. And sort of we can see that only distributions that shifts to themselves cannot be distinguished from correct. And this is sort of the core fact of our proof. But I left out one important case. So what if U squared is equal to the identity? So our approach from the previous slides will not work since the distributions will be equal. However, in this case, we can observe that the adversary essentially acts as a perfect CDH algorithm on the subgroup induced by G mod the elements generated by U. And we can just directly apply the approach from GPS V18 to this and then just brute force. And again, this idea can work for more general subgroups as long as they're polynomial size. And that's about it. We show that there's always a polynomially sized subgroup, H, such that we can amplify an adversary to have near perfect success probability on G mod H. You all can probably recreate the reduction from here. There are a couple of tricky parts. We could have super polynomially many possible subgroups if we're given a degenerate enough G. So we have to explicitly compute the subgroup rather than guess it. There are also some tricky points with respect to thresholdization, but this is really more tedious than interesting. I'll finally say that we assume a regular abelian group action in our reduction, but we can expand it to any abelian group action without too much pain. And if you're interested in that, it's all in the paper. That being said, there's a lot of room for improvement. So our reduction is almost black box, except the dependency on Q, which is the adversary's success probability. The running time is polynomial, but it's pretty bad. It's 1 over Q to the 13, where, that's not great. So it's useful for ruling out quantum polynomial time attacks, but not necessarily for setting practical security parameters. For practical parameter setting, you probably need 1 over polylog in the number of queries, and this might rule out our shifting technique, but maybe there's a better technique. And finally, in the same vein, it might be possible to do substantially better for fixed groups known in advance, particularly ones that don't have too many subgroups. A smart Asiacrypt reviewer pointed this out for SciFish. And it might be possible to have very tight instantiations for things like SciFish, and we leave this totally open. And finally, we think our work on Rigas and the dihedral hidden subgroup problem really just scratched the surface. So on that, thanks a lot for your time, and I'll be happy to answer any questions.
We have a couple of minutes for questions. Anybody? All right, then let's thank the speaker again. Our next talk is remote, so let's just take a minute to set that up. Can they hear us?
Hi, Shweta, can you hear me?
Yes, Shikhar?
Yeah, hi, can you hear me?
Yes, we can hear you. So our next talk is cryptographic primitives with hinting property, and this paper won the best paper by early career researchers. It's by Shikhar Patranabis and Naveed Alamati, and Shikhar will give the talk. Please go on.
Thanks, Shweta. Thanks a lot, and my apologies for not being able to give this talk in person. So welcome to this virtual presentation on cryptographic primitives with hinting property. This is joint work with Naveed. So we encounter hints frequently in daily life. For example, when we forget passwords and the hint allows us to guess the password without actually revealing the entire password itself. But it turns out that hints are actually also useful not only in real life, but also in cryptography. And in the context of a widely used and fundamental cryptographic primitive called a pseudorandom generator that I believe we are all familiar with. Now, in the traditional PRG game, a distinguisher or an adversary is not given any additional information about the seed of the pseudorandom generator. But in Crypto 2019, Popula and Waters introduced a variant of PRG, which is called a hinting PRG, and which is the fundamental motivation for this talk, where the distinguisher is actually given some additional information or hint about the seed of the PRG. More formally speaking, let's say that we have the output of the PRG as a sequence of n strings, each of length n bits, and we also have a sequence of n random strings of length n bits, and then we swap these two strings in certain positions depending on whether a bit of the seed is 0 or 1. In particular, we swap them if the bit is 1, and we don't swap them if the bit is 0. So here's a toy example for n equals 6. So you can see that the y and z vectors are swapped in the locations where the seed s is 1. Now, informally speaking, what the hinting PRG guarantees is that despite embedding information about each bit of the seed in this 2x n matrix, this ensemble of strings actually remains pseudorandom. That is, it is computationally indistinguishable from a 2x n matrix of random n-bit strings. And more formally speaking, this is what the hinting PRG game looks like, where we have a 2x n matrix Z, and its elements are either the output of the PRG or uniformly random, and they are swapped depending upon whether each bit of the seed is 0 or 1. And despite encoding these additional hints about the seed, this matrix Z remains pseudorandom. Now, why are hinting PRGs interesting? In the seminal work, Popula and Waters showed that it is actually a cryptographic booster. Well, we are all familiar with boosters in this era of COVID. But hinting PRG is a cryptographic booster in the sense that it can be used for a genetic transformation from CPA to CCA security for public key encryption and other advanced forms of encryption. And in more recent years, hinting PRGs have been used in a myriad of other cryptographic applications, in particular for new constructions of advanced cryptographic primitives. This makes hinting PRGs a very interesting class of primitives to study. Another interesting feature of hinting property is that it bears some similarities to another property that we are probably familiar with, which is circular security in the context of symmetric key encryption. In fact, one could view the hinting property as a deterministic form of circular security with respect to the bits of the PRG. However, there are some fundamental differences between the two. Historically, circular secure symmetric key encryption has been extensively studied, and we know how to realize them via simple constructions and proof techniques from certain standard decisional assumptions. And it is also known that they're weaker than public key encryption because they can be realized from random oracles and are hence black box separated from public key encryption. On the other hand, the known constructions and proof techniques for hinting PRGs are rather complicated and deeply rooted in algebraic or public key style mathematical assumptions, which naturally leads to the question of whether such kinds of public key techniques are inherent to hinting PRGs, or whether we can have simpler constructions and potentially non-algebraic constructions as well. So here's the one-slide summary of the current landscape of hinting PRGs and how we know to realize them in practice and what they imply versus what we ask in this paper. So to summarize, we ask three main questions. One, can we have simpler constructions and proofs of hinting PRGs? And can we realize these constructions from a wider class of assumptions, for example, isogeny-based assumptions that Hart gave us an excellent introduction. Then we ask whether we can extend the hinting property to other symmetric key primitives, and if such extensions are useful and realizable. And finally, we ask what exactly is the cryptographic complexity of hinting PRGs, and more concretely, can we establish whether mathematically structured public key style assumptions are truly necessary to realize these primitives. In this paper, we propose new extensions of the hinting property to another well-studied class of symmetric key functions called pseudorandom functions, and also their weak variants, where pseudorandomness is only guaranteed on uniformly sampled inputs. We also provide new security definitions for these primitives, where informally speaking, the pseudorandomness guarantee holds in the presence of hints about the secret key. But an important feature is that the security notion here is multi-evaluation, in the sense that the pseudorandomness guarantee holds over multiple evaluations of the PRF over different inputs. And this is in contrast to the security definition for hinting PRG, which is kind of one shot in the sense that you only get to see the evaluation on a single seed. So a hinting PRF implies a hinting weak PRF, which in turn implies a hinting PRG, all of these in a black box manner. Next, we show new stronger implications of the hinting property when extended to weak PRFs. In particular, we show that a hinting weak PRF implies a full-fledged circular secure symmetric key encryption scheme in a black box manner. This is in contrast to a hinting PRG, which only implies a weak notion or a one-time notion of circular secure symmetric key encryption. Next, we show, this is the major contribution of this paper, we show a new framework for designing hinting weak PRFs and by extension hinting PRGs. And our framework gives significantly simpler constructions and proofs as compared to the previous approaches like the missing blocks framework and the accumulation frame. And a corollary of this simple instantiation is that we can actually extend this to other assumptions, such as isogeny-based group actions, which we already heard about. Finally, we have an impossibility result where we show that hinting PRFs, and in particular this whole ensemble of cryptographic primitives with hinting property, is actually black box separated from public key encryption. And so public key style assumptions are actually not necessary to realize them. And we show this by showing a non-algebraic construction of a hinting PRF given just a simple random oracle. We also have some additional contributions wherein we show new strengthenings of the hinting property to what we call a functional hinting property, where the adversary is now given hints about each bit of some function of the seed, and this function can actually be chosen adversarially from a fixed function family. So here's an example. Suppose we have an n-bit seed for a hinting PRG, and a functional hinting property, for example, allows the adversary to get information not only about S, but also about each bit of this particular quadratic function of S, right? And we then show that the functional hinting property can have even stronger implications. In particular, we show that a functional hinting PRF with respect to some function family F implies in a black box manner a KDM secure symmetric key encryption scheme with respect to the same function family. Recall that in the normal hinting weak PRF case, we only got a black box construction of circular secure symmetric key encryption, and the amplification to KDM security was non-black box. However, the functional hinting property now gives us a new approach for achieving KDM secure symmetric key encryption in a black box manner with respect to Boolean function families. Finally, we also show that these kinds of functional hinting primitives can actually be realized from certain standard assumptions. In particular, we build upon our construction of hinting weak PRF and hinting PRGs from DDH to show a construction of functional hinting weak PRF and by extension functional hinting PRG with respect to function families containing projective quadratic functions and functions of higher degree over the bits of the secret key or the secret seed in case of the PRG. So this is kind of a one slide summary of our contributions. So here's an outline for the rest of the talk. I'll spend the next few slides trying to outline how do we construct a simple hinting PRG from the DDH assumption. I will then give a brief overview of how we extend the same techniques to build a hinting PRG from cryptographic group actions. And I will give a very, very brief introduction to hinting weak PRFs. And finally, I will end with summary and some open questions and future directions of research. Right. So the simple hinting PRG from DDH is in fact incredibly simple. I think that many of you are probably familiar with this construction. It is a very, very simple construction that literally consists of a matrix vector multiplication in the exponent of the group element, where the matrix is a uniformly random matrix of square dimensions, and the vector is a binary vector. Okay? So remember that in the definition of hinting PRG, the seed is typically considered a sequence of bits, and we do the same. Now, it has been implicitly or explicitly proved in a number of previous works that if we assume that the group G is DDH hard, then this particular function is in fact a PRG. And the hint is that the proof of security requires applying the leftover hash length. Now, what we claim in this paper is that this PRG, this very, very simple PRG from DDH, in fact, already has the hinting property. And the way we prove that is that we reduce the hinting property of this PRG to its fundamental pseudo-randomness guarantees. So I'll try to briefly outline what our proof looks like. Our proof basically is a reduction that takes as input the public parameter M for this particular PRG, along with a sequence of n group elements, which is the output of this PRG, or it's a uniformly random sequence of group elements. And what this reduction outputs is a public parameter for the hinting PRG, which by the way is the same construction. So it basically outputs a different public parameter from the same distribution. And then it outputs this 2 cross n matrix, which if you recall is the output of the hinting PRG game. And this is either distributed as in the real hinting PRG game, which means that it is the intersparse of the real PRG output and a uniformly random sequence of group elements where the positioning is done based on the seed, or it's a uniformly random sequence. And the main challenge here is that our reduction actually does not have any idea about the seed of the original PRG, because it only gets this public parameter and the output, which is not supposed to reveal any information about the seed if the original PRG is secure. And despite that, what we want to do is that we want to ensure that when the input on the left is distributed as in a real PRG game, we want the output on the right to be distributed as in the real hinting PRG game, which means it needs to embed some information about the seed. And the crux of our proof is how we do this without knowing the seed in the first place. Okay. And of course, we also want random to map to random. And this is in a nutshell what our reduction looks like. It looks quite simple. So what we do is we basically output the same public parameter, except that we shift the matrix in the diagonal by some uniformly random shift elements. And then in the output sequence, we basically set everything on the top row to be directly equal to the input from the PRG game. And we shift the elements in the bottom row by these uniformly random shifts. Okay, so in other words, Zi0 is equal to Yi, and Zi1 is equal to Yi plus Di. Now, this is a simple looking transformation, but the interesting fact is that this implicitly allows us to embed information about the seed in the sequence on the right. Why? Well, let's see that. Suppose that the Yi's are actually distributed as in the real PRG game, and the Zi's are constructed as we said. It turns out that if the bit Si is 0, then it is easy to prove that Zi0 is actually distributed as it should be in the real hinting PRG game. This is because because when Si is 0, there is no contribution from the ith row of the matrix into Zi. And so since it only differs in the diagonal element for which the contribution is 0, so Zi0 is actually well distributed. On the other hand, Zi1 is randomly shifted, and so it is distributed uniformly random. Similarly, when Si is 1, we can argue that Zi1 is now actually distributed as the inner product of the ith row of the matrix and the seed, and Zi0 is distributed uniformly random. Okay. So in some sense, we embed information about the seed into these elements without knowing the seed at all in the first place. And of course, it's we achieve this goal that when the Yi's are distributed as in the real PRG game, the Zi's are distributed as in the real hinting PRG game. And of course, it's easy to see that when the Yi's are distributed uniformly randomly, then so are the Zi's. And so, when the input is random, the output is also random. And so that essentially concludes the proof of the fact that this PRG is in fact a hinting PRG. And this construction is much more simple and direct as opposed to the existing approaches for constructing hinting PRGs. So now I'll very briefly discuss the fact that our simple approach for constructing hinting PRGs readily generalizes to cryptographic group actions, which are commutative and regular. And I think Hart already did an excellent job of introducing group actions, so I won't go into the details, except maybe again recall that group actions are useful because they can be instantiated in plausibly post-quantum secure manner from certain families of isogens. And I'll just throw the construction out there. I won't go into the details, but again, what I would like to sort of stress is the fact that our simple approach allows us to get very simple and direct constructions of hinting PRGs from group actions. And this is essentially a generalization of the construction from plain DDH that we can prove secure under a special assumption called the linear hidden shift assumption that we introduced way back in 2020 in our Asiacrypt paper. I won't have time to go into the details, so I would refer to the paper for more details on the construction and proof. And finally, I would like to provide a very brief overview of hinting weak PRF. So, as I already mentioned earlier, that when we extend the hinting property from PRGs to PRFs, one thing we need to ensure is a multi-evaluation kind of definition, where we now have the key of the PRF, which is an n-bit string, but we also can have a sequence of any polynomially many inputs, which can be either arbitrarily sampled or uniformly sampled for a hinting weak PRF. And then what we do is we basically apply this swap to each of these output sequences. And so in some sense, what we have here is a multi-evaluation hinting property, where each evaluation leaks some information about the secret key, and yet this whole ensemble of outputs across multiple evaluations remains computationally indistinguishable from uniformly random. So this is an informal overview, and I would refer to the paper for the formal definition. And then this is kind of a one-slide summary of the fact that we can actually take our simple approaches for constructing hinting PRGs from DDH and from group actions, and we can very naturally extend them to construct hinting weak PRFs from the same assumptions. In particular, if you look at the left, you can see that our hinting weak PRF from DDH is nothing but the same hinting PRG construction, where the secret key is now acting like the seed, and the public parameter essentially becomes the input. And our proof techniques are also very, very similar. Nonetheless, this is a very kind of high-level overview, and I would refer to the paper for the more detailed constructions and proofs. Right, so now I would like to conclude by summarizing our results and stating some open questions. So we showed how to construct hinting weak PRFs and hinting PRGs, as well as functional hinting weak PRFs and functional hinting PRGs from certain standard assumptions. But we do not have any constructions of hinting PRF or its extension to functional hinting PRF from standard mathematical assumptions. So this is one open question. The other open question is whether we can realize primitives with the functional hinting property from a wider set of quantum safe assumptions such as lattices or isogenies. In particular, our current constructions are kind of specific to DDH, and we believe that some more work will be required in order to be able to build these from lattices or isogeny-based assumptions. And finally, we leave it open to investigate additional applications of these new primitives with hinting property and functional hinting property that we introduce in this paper. Of course, I didn't get time to go into the details of certain results, such as the black box separation result, as well as the results on the functional hinting property. And I would again refer to the paper for more details. Thank you, and I'll be happy to take any questions.
We have time for questions. All right, then let's thank the speaker again. Thank you.
Thanks, Ruth.
All right, so let's move to the last talk of this session. This is a work on SwiftEC by Jorge, Francisco, and Mehdi. And Jorge will give the talk. This is the paper that won the runner-up best paper award and was invited to the Journal of Cryptology.
Okay, good morning, everyone. So I will be talking, oh, can we go full screen? Oh. That's weird. Okay. So I'm going to be talking about SwiftEC, which is the Shalhoub and the Bushstein indifferentiable function to elliptic curves. So the contribution of this work is the most efficient constant time admissible encoding that works for a large set of ordinary elliptic curves. So what does this mean? Well, in particular, it's a big leap for hashing into these curves because it results in the first constant time admissible, indifferentiable hash function that requires a single square root computation. As well as an efficient point representation algorithm, which requires only 2 square root computations. So just as a background, a lot of applications in cryptography are going to require us to hash into a cryptographic group of interest. And if this is something like a finite field, then it can be just as easy as hashing into a long bit string and interpreting this mod Q. But when I'm working with elliptic curves, this can be not trivial at all. So basically, the question that we're trying to tackle is how can we get x and y coordinates that are random among the set of points that satisfy this specific curve equation. So let's first take a look at some naive constructions that don't quite make the cut. So the first one and most obvious that I can think of is I can just hash into an x coordinate. So this is a field element, so I know how to do it. And then I just have to ask whether or not this is the x coordinate of a point in the curve. So the elliptic curve is given by y squared equals some function of x. So I can just evaluate this function of x and try to take the square root, right? So if it exists, then I found a point in the elliptic curve and I am done. But if it does not exist, I have to start over and try with a new x. So I have to implement some kind of try and increment approach. And obviously the problem with this is it's not going to be constant time. And we're going to be open to timing attacks. So just the knowledge of how many times I had to restart can give away valuable information about what was the seed. So we don't like this. Another construction we can think of is you may know that points in the elliptic curves form a group. So I can pick a generator of this group and hash into a random multiple of this generator. So I hash into an integer n, and then I compute the point p equals n times the generator. So this looks like a very good idea, but it's actually a very bad idea. Because it leaks very sensitive information. So whoever computed this hash function not only knows the value of the output p, but in the process, he also learned the value of n. So this is what we call the discrete logarithm, and it's in most applications, it's precisely what we want to keep secret, and we assume that it is hard to compute. So you can easily see how, depending on the application, if we're not careful, this can end up compromising security very, very badly. So we would like to get something that works regardless of the application. And in general, the strategies that tend to work better are based on some kind of modularity. So I assume that I already have a hash function into some set S. It can be something like a finite field or anything different. And then I compose this with something that I call an encoding. So the encoding is just going to be a function from my set of interest, in this case, to the elliptic curve. And I'm going to assume also that I have an inverse function that takes me from the curve back to the set S. Usually we call this the point representation function. And if you're familiar with the alligator construction, for example, this is precisely the idea that it's based on. So in our case, we're going to present algorithms for both of this. We have the encoding function that we call SwiftEC, as well as the point representation function, which we call alligator Swift. All right, so what do we need for this construction to be secure? Basically, if we already have our hash function into S, and compose that with the encoding. When is this composition sure to be a secure hash function itself? It turns out that it is enough for the encoding to satisfy three properties. It has to be efficiently computable, of course. It also has to be regular, meaning that for uniformly random inputs, the distribution of images has to be also statistically close to uniform. And also it has to be sampleable, meaning that I need to have this inverse function that computes per images. And usually the encoding is not a one-to-one function, so there can be more than one per image. So in that case, we just ask that it returns any of the possible per images, but it has to do so uniformly at random. It cannot have any bias for a certain per image. So if the encoding satisfies these three properties, we say that it is an admissible encoding. And it turns out this is enough to allow us to just use it as a black box and not have to worry about compromising security. So let's first look at a very simple example, which is an encoding not to an elliptic curve, but to a conic. So I have plotted here a conic over the real numbers. And conics have this very interesting property that any line that intersects it is going to do so at exactly 2 points. So I can exploit this to build an encoding. What I do is just fix a reference point, P0. And then for any other point in the conic, I can just draw the line connecting P0 to P1 and compute the slope of this line. So for the point P1, it is going to be associated with the slope T1 of this line. And I can do this for any other point in the conic. So this is actually an encoding from slopes, which are real numbers, to points in this conic. It turns out this is, in fact, an admissible encoding. And even better than that, it is a one-to-one function. So it's going to be very well behaved. However, keep in mind that this works only as long as I have pre-computed or somehow know a fixed reference point in this conic. So just keep this in mind because it will be important later on. All right, so now let's move on to encodings to elliptic curves, which turn out to be a little bit more complicated. And the main ingredient that we're going to use is called the Shaloub-Van de Wüstijn map. This is actually a family of encodings. So for each choice of the parameter u, which is a field element, I'm going to get a different encoding. And the way it works is that Shaloub-Van de Wüstijn find a map that goes from a certain conic to a certain hypersurface. So this certain conic is given by this equation, and it's a parameterized conic because the coefficients are given by these polynomials of the parameter u. And this hypersurface is just this hypersurface in a 4-dimensional space given by c squared equals g of x1 times g of x2 times g of x3, where g of x is just the polynomial of the elliptic curve. So these are the explicit equations for the map. You don't need to worry too much about them. Just know that there is a map from here to here. And at this point, you might be wondering, OK, but this is not an elliptic curve, and this is not an elliptic curve. So why am I talking about this? Well, it turns out that from here, we're very close to getting to a point in an elliptic curve. So if you look at the equation for B, I have a square, which is equal to the product of three things. So when this happens, it must be the case that at least one of those three things is a square. And in fact, there's only two possibilities. It can be that exactly one of them is a square, or all three of them are squares. And remember, if I find an x such that g of x is a square, then I have actually found a point in the elliptic curve. So all that we have to do after we get our values for x1, x2, x3 is do a quadratic reciprocity test to determine which one of these is a square and return that value. And in the case that all three are squares, we just have to do any arbitrary choice. So let's say, for example, that I prioritize x3. And by the way, the quadratic reciprocity tests are much cheaper than a real square root computation, at least by an order of magnitude. So in the end, we only ever have to compute a single square root for the value that is, in fact, a square. And this is actually going to be the main cost of the algorithm, a single square root. Now, on the other hand, we already know, we talked about how to encode into this conic. So we can actually build the whole chain that is known as the Shaloub-Van de Wüstijn map. We start with a field element, which is the slope of the line. We use the encoding that we talked about first to get a point in the conic CU. Then we apply the map that I just mentioned to get a point in B. And then we do the quadratic reciprocity tests to figure out which one of those is a point in the elliptic curve. So this whole path is what we know as the Shaloub-Van de Wüstijn encoding. And these are given by very simple formulas, explicit formulas, so it's easy to implement in constant time. And the main cost, as I said, is a square root computation, and this is just to recover the y coordinate. right? So if I don't care about the y coordinate, which is the case in some applications, I can actually skip that. And this works basically for all elliptic curves and almost any choice of the parameter u. However, the disadvantage of this, as beautiful as this all is that for any choice of u, the encoding fu is actually not regular. So this is not an admissible function, and I cannot use it as a hash. So that's too unfortunate, but there is a solution that we call the squared encoding construction. So the way it works is, okay, one evaluation of fu is not regular, but it turns out that if I take two independent evaluations and add them together, then the result actually is regular, okay? So now I'm going to have a domain size that is twice as large, but I'm actually going to get an admissible encoding, and it's an admissible encoding that works for basically all elliptic curves. However, the disadvantage of this is that now I have to compute two copies of f, therefore two square root computations, so it's going to be a little bit more expensive, but this was the best previously known way of doing this. So this is where our new proposal comes into play, what we call SwiftTC. And what we're doing is we're still using a domain size that is twice as large, but now the second variable is going to be u itself. So before, it used to act as a global fixed parameter, but now it's actually going to be another input. So we're computing a capital F of u and t, which is equal to lowercase fu of t. Okay, so if I tell you that this is the whole idea of the construction, maybe it sounds a little bit underwhelming, like we're just changing the notation. But of course, this has very deep implications. So there are theoretical implications because, of course, it sounds reasonable that if I randomize u as well as t, probably I'm going to get more random looking points. But to get a formal proof of regularity is a whole different thing. And there's also practical implications because now I need an algorithm that will be able to evaluate fu of t for any choice of u that will be determined at runtime. Okay, however, over the whole FQ square domain, this construction, we show that it is in fact admissible. And what we gain is that we're back to having to compute a single copy of f, therefore a single square root computation. So this should be, and is in fact, roughly twice as fast as the previous state of the art. Okay, so let's first talk about these practical implications of building this algorithm. And the place where you're going to run into trouble is for the encoding to the conic. So if you remember near the beginning of the talk, I mentioned for this to work, you have to know a reference point in the conic. It can be any point, but you have to have some way of finding at least one point. So this is what I had called P0 before. Now I'm calling it PU because it is, the conic itself is a function of the parameter u. So I need an algorithm that, given the conic CU, will return some reference point PU. And it turns out that this is a problem that had already been studied by Van Hoysch and Cremona, and they showed the following theorem. So if I have this conic that is parameterized by these polynomial coefficients, h of u and g of u, it turns out that there is an efficiently computable point in this conic given by rational equations if and only if two conditions are satisfied. So minus h has to be a square mod f, mod h, sorry. Minus g has to be a square mod h, and minus h has to be a square mod g. So as long as these two conditions are satisfied, their proof is constructive, so I can use their algorithm to output a point pu, and then I just carry on with the rest of the construction exactly as before. Now, in our case, the polynomials h and g are not general, but they have this very specific form. So h is equal to 3u squared plus 4a, and minus g is just the polynomial of the elliptic curve. So in this particular case, we show in the paper that the conditions that I just mentioned are actually equivalent to another set of three conditions, namely that the size of the field has to be equal to 1 mod 3, the discriminant of the curve has to be a square, and the third condition is that at least one of these constants, nu plus or nu minus, has to be a square. So if you look carefully here, condition 1 implies that minus 3 is a square. Condition 2 implies that delta is a square. So this whole thing is always a square. And if I take the square root for at least one of the choices of sign, I should get a quantity that is a square. So that is condition 3. So it's not at all obvious that these conditions are equivalent to the ones that I mentioned before, but it's a much nicer characterization of the curves that are compatible with our construction. So notable curves that are compatible include the NIST P256 curve, as well as 256K1, which is the one used for Bitcoin, and also all the BN and BLS curves, which are used for pairings, Those are all immediately compatible as long as Q is equal to 1 mod 3. And then there's a few other curves which are not compatible, but that we managed to rescue using isogenies. So an isogeny is just a rational map that takes me from points in one curve to points in another curve. And so it may be, in some cases, that the curve itself is not compatible, but I managed to find an isogenous curve that is compatible. So I can just apply the Swift-DC construction to that other curve, and then compose with the isogeny to get back to the curve that I wanted. So this is the case, for instance, for curve 25519. It is not compatible because the discriminant is not a square, but we found a curve that is compatible and is related by an isogeny of degree 2, which is very, very cheap to evaluate. So it has a very negligible overhead. And the same is the case for NIST P521. It is not compatible, but we also managed to rescue it, this time through an isogeny of degree 3. And then unfortunately, there's another case when Q is not equal to 1 mod 3. Here, isogenies don't really help us, and so far we have no good way, no way at all of rescuing these curves. And unfortunately, this does happen for some popular curves, including NIST P384 and the Goldilocks curve. So those are not compatible. Okay, so that covers the computability of Swift-DC. Now let's talk about the second property, which was regularity. And let me be a little bit more specific about what we want to show. So if I have a function that is perfectly random, and I want to compute the number of preimages, on average, this should just be equal to the size of the domain divided by the size of the codomain. So in our case, the size of the domain is Q squared because we have two field elements, U and T. And the size of the codomain is just the order of the curve, in this case divided by 2 because we only care about the x coordinate and not the y coordinate. So there's a popular theorem called Hass's theorem that tells you that the order of the curve is roughly Q. So if you plug this in, you'll find that the number of preimages should be roughly equal to 2Q. So this is the main theoretical contribution in the paper. We show this theorem that if you take this error term, which should be equal to 0 if you plug this in, we show that, of course, it's not exactly 0, but the sum in absolute value is bounded by this epsilon, which is a function that vanishes exponentially fast with the bit size of Q. So asymptotically, the distribution of Swift-DC is going to be very close to a uniform function. And finally, let's talk about the samplability. So remember, this is being able to compute preimages. And what we do is explicitly propose this new algorithm called Alligator Swift, which, given the x coordinate of a point, will return a preimage U and T. And the way it works is basically just you fix a randomly chosen value of U and try to invert FU of T. So when you're trying to invert it, you should ask yourself from what point in the conic could I have come from? And basically, there's 3 different branches. So these are the equations for the map that I had mentioned near the beginning of the talk. So there's 3 choices. Either the square came from x1, in which case I have to invert the first map, or the square came from x2, in which case I have to invert the second map, or it came from x3, in which case I have to invert the third map. So I pick a random value of U, and then I pick one of these 3 cases at random, and I try to invert that corresponding map. So if this works, then I'm done, and I have a preimage. But if it doesn't work, then I just start over. So I pick a new U, I pick another one of these cases at random, I try again. So basically, we're doing some rejection sampling to ensure that the distribution is going to be uniform. And it turns out you can actually reject failed samples by just doing quadratic reciprocity tests before committing to real square root computations. So in the end, you only have to compute square roots for the one successful case. And this is a big improvement over the squared encoding variant, where each failed attempt has the cost of another square root. And then, of course, once you get your point in the conic, remember the encoding to the conic was a one-to-one function, so that is very easy to invert. You can compute t from there, which, remember, was just the slope of the line. So the output is going to be the u that you picked at random and the t that you computed. Okay, so we have just a proof of concept implementation in Sage that is freely available. And what we do is count the number of operations that it takes. So we have the number of additions, squarings, multiplications, Jacobi symbols, which are the quadratic reciprocity tests, as well as inverses and square roots. And as promised, the main feature is that you only have to compute 1 square root, along with 1 inverse, which, by the way, can be computed in batch. And then, of course, if you only care about x-only projective coordinates, then you don't have to do either of them at all. And this is just a little test that we ran with our implementation. So this is counting the number of preimages of every point in the elliptic curve. So each of these bins represents a different point, and we just exhaustively evaluated SwiftTC for every single input. Obviously, this had to be done with a very small prime. So this is only a 10-bit prime, but already for this small size, you can see that the distribution is looking very close to uniform. So it's a very good result. Okay, so just to conclude, SwiftTC is now the most efficient known way for indifferentiable hashing in constant time to a large set of ordinary elliptic curves. And Alligator Swift is the most efficient point representation algorithm for the same set of curves. And some future work that we still want to do for this project is doing an efficient constant time C implementation for reference, as well as theoretical work to further increase the number of curves that are compatible. So with that, I would like to thank you very much for your attention.
Are there any questions? All right, so let's thank the speaker again. We'll now have the coffee break.
Let me announce again that the sponsor area is on the 4th floor, and there is quite a bit of food up there as well. So please support our sponsors. Also, we begged the hotel to raise the temperature by a degree or so. I hope that is satisfactory. Anyway, see you shortly.
Version 2 is the LFSR used for the Turkey TK4. Since a Turkey schedule is linear, we can drive the subturkeys from the same nibble of the master key as a system of linear equations, where Li is a 4 times 4
Okay, welcome to the functional and the witness encryption session. We have 4 talks in this session. The first talk is multi-client functional encryption with the fine-grained access control by Ki Gwen, David Poinsable, Liu Hugh Wang. Ki is going to talk.
Hello. Thank you, Rio, for the introductions. Can you hear me well? Yes, so my name is Ki, and today I would like to present our work on multi-client functional encryption with fine-grained access control. So this is a joint work with Young Hil Fan and David Pashavan. Okay, so first I will give the motivations and the context of our paper, and then the related works in the literature followed by our contributions. And in the second part of the talk, I will give some technical overview of our constructions and some high-level technical ideas. So the starting point is the all-or-nothing nature of a public key encryption. That is, given a secret decryption key that you decrypt and get the whole plain text or nothing. Later, there is the notions of attribute-based encryptions that give some control. If the policy in the key is satisfied, then you can decrypt and get the plain text, else nothing. And more than a decade ago, there is the notion of functional encryptions, in which you control the quantity of information leaked about the plain text through the function evaluation. However, one observation is that on these secret decryption keys, their usage can be unlimited in the way that the decryptor can use them in whatever way he wants. And in this work, we focus on functional encryptions in the multi-user setting. So there are 2 main notable notions, that is the multi-input and the multi-client. So there are various notions of multi-input. So, but in this work, we consider them to be the FE schemes where the plain text can be encrypted component by component, and the components can be combined arbitrarily using a functional decryption key to get a functional evaluation. On the other hand, there's also the notion of multi-client functional encryption. That is, there are multiple clients in the system. Each of them has their own private encryption key, and they can encrypt the individual data independently under some specified tag, which can be some timestamp metadata, for example. And in the end, a functional decryption key allows combining all the ciphertext components only if all the partial ciphertext are encrypted using the same tag. So this limits the arbitrary combinations resulted from the MIFE, for instance. And the problem with the unlimited usage of the decryption keys still persists in this setting. So our goal is to enforce some fine-grained control over the decryption keys. That is, we associate a policy in the key, and at encryption time, each client in the MCAV setting will encrypt their partial ciphertext under some specified attributes. And only when on client's attributes satisfy the keys policy, we will be able to obtain the function evaluation on the jointly combined plain text. Otherwise, we obtain nothing. In particular, in this work, we consider the function class that allows computing inner products, and the asset control can be expressed using linear sequencing schemes, or LSSS, for example. One remark is that this MCFE with fine-grained asset control can be captured by the general notions of MCFE if the class of functions can express the asset control. So one might very well wonder why MCFE, why we focus on the multi-client version. So first of all, in our particular constructions for inner products and LSSS, we treat the tag by hashing them. And so if we fix and publish this hash value, the notion of tag becomes somewhat transparent, and we obtain an MIFE scheme. On the other hand, in the other directions, given an MIFE or inner product with LSSS, if we want to obtain an MCFE scheme, because in the MIP there's no notion of tags whatsoever, so we need to include some equality check for the tags. And it turns out to be infeasible in this case for this particular function class to compute inner products and with the LSSS asset control. Even in the case of simple policy like identity base. And I refer to our paper for more details and discussion on this technical point. So therefore, our goal now becomes constructing MCFE schemes to compute inner products with the asset control using a linear secretary scheme. In the literature at Asiacrypt 20, Abdallah et al. Studied this problem of FE plus asset controls. And they proposed several candidates using pairings and learning with errors, where the asset controls can be expressed using monotone span programs. In the end, they gave also a generic transformation from single client FE scheme to MIE scheme with adaptive security and quadratic total communication. In this works, we study this problem in the setting of MCFE, where the asset control can be expressed using linear secretary schemes. They can be identified with the underlying monotone span programs. And we obtain adaptive security in the random oracle model and linear total communications. And as I've mentioned earlier, we can deduce an MIA scheme by fixing and publishing a hash value, and while preserving all the advantage regarding the security level or the total communication. So let's move on to the formal definitions of MCFE with a parent asset control. So the asset control is expressed using a relations between key policy and the attributes put inside the independent and self-attack components by end clients. So there exists an authority given the function description and the policy. We output the key corresponding to this policy and the functions. And all clients, each of them having their private encryption key. We use their key to encrypt the partial ciphertext. And the correctness requires that only when all client attributes satisfy the key policies, we will be able to obtain the function evaluation. Furthermore, about the security model, it is an interactive security game between an adversary and a challenger who picks a random challenge bit. The adversary is allowed to query for multiple times functional decryption keys corresponding to policies and functions of his choice. Moreover, in this testing of multi-client functional encryption, there are multiple clients. Each of them has the private encryption key. Therefore, the adversary is also able to corrupt a client and receive the corresponding encryption key for multiple times. And the adversary can also demand the challenge ciphertext for two challenge vectors x0, x1, component by component, under some specified tag and attributes to receive the challenge ciphertext. So furthermore, we restrict that the adversary can only use one challenge tag, but we allow him to query an encryption oracle to encrypt data of his choice for arbitrary clients, and he can do this multiple times. So using a standard hybrid argument, this is equivalent to the multi-challenge notion. And in the end, the adversary outputs a guess for the challenge bit. So we can have various weaker notions by restricting the adversary to declare upfront the challenge queries or the corruption queries. And moreover, in this security model, the functional keys might allow the adversary to decrypt the challenge ciphertext. And therefore, if it is the case, we constrain that the two inner products of the two challenge vectors must be the same. So before going into the technical overview, I recall some technical tools that we use. So namely the dual pairing vector spaces introduced by Okamoto and Takashima. So we are in a prime order bilinear group written additively. And we consider some basis matrix of scalars with some public row vectors and private row vectors. So we take it inverse and then transpose to get the dual basis. And we raise these two bases into the corresponding groups, G1 and G2. We get two matrices of elements in G1 and in G2. So these are called the dual bases of the dual pairing vector spaces. And given these two matrices, we can have some notion of vectors of group elements and define their products by simply taking the pairings component by component and adding up together. So in the end, the result is an element in GT whose exponent is the inner product of the two underlying vectors. So being equipped by these tools, let's move on to our single client scheme. So there is only one client, and the ciphertext consists of multiple AOS ciphertext that is from the celebrated in the product functional encryption by Ahwan, Liebeck, and Stelle. Moreover, for the asset control part, we have a vector C0 in the basis H containing the randomness for the AOS ciphertext as well as the asset control. And for each attribute needed in the ciphertext, we have a vectors in the basis F. On the other hand, in the key, we use the AOS to secretly share a random secret A0 put in K0 star to mask the AOS key. And for each attribute, we have a vector K at star in the basis F star. So by using the linearity of the product operations between vectors, if we're summing up the products over attributes in a reconstruction set for the AOS, for the AOS SS, we will have psi times I0 in the exponents of GT. And we can recover the unmasking value of the AOS decryption procedure. And in the end, we can recover the inner product of X and Y using the usual AOS decryption. So about the security, we perform using a game-based proof where the changes are done by basic change in the DPVS framework. And the main idea is to embed a newly generated secret series of another A0 prime secret in the ciphertext and the keys vectors and masked by some random values. Yeah. So some subtlety is that in these scenarios, we can be in two cases where the key can decrypt the channel ciphertext. And in that case, we can apply some ABA techniques such as the dual system method. Or it can decrypt the channel ciphertext, but we constrain that the delta X in the product with Y, where delta X is the difference between the two channel vectors. This inner product must be 0. And in the adaptive security setting, we want to know which case we will be in the course of simulation. So our main idea is if this inner product is non-zero, then this key cannot decrypt the channel ciphertext. And therefore, we embed term by terms the delta xi times yi along with the secret settings in the key and the ciphertext for both the attribute vectors and the C0, K0 vectors. And in the end, thanks to these secret settings and the random mask Z, we can randomize the A0 prime to a newly A0 prime independent secret that allows us to modify the channel ciphertext to be independent of the channel bit. And finally, because we need to embed term by terms the inner products of delta X and Y, we will need at least n coordinates in the key and ciphertext vectors, and therefore the ciphertext size increases to linear in n. and also depending on the number of attributes needed. In particular, if we are in a non-trivial, simple asset control identity base, D can be equal to 1, and we obtain something linear in N. And more details can be found in session 5 of our paper. So that's for the single client. Towards the multi-clients, we use technical ideas that we call compress and duplicate. So namely, if we naively duplicate all the formats of the key and the ciphertext vectors from the single client to the multi-client, then we will have something quadratic in N, because the vectors are already of size linear. So the main observations is that we can compress the attribute vectors into the same basis F star and F for all clients, thanks to the indexing technique in DPVS, also introduced by Okamoto and Takashima. And each client I will be embedded the newly secret shares together with yi only. And we do not need to accommodate all the n terms in one single vectors anymore. And the same thing can be done for the K0 and C0 vectors, where we duplicate the HI and HI star for each client, and then each client I deal with the terms yi times delta xy, delta xi. And we obtain a constant auxiliary number of coordinates for each client and each attribute if needed. And in the end, the total communication reduces to linear in N. So I refer also to the session 5 of paper for more details on this technique. And to conclude, we propose MCP candidates to compute inner products with asset controls using linear sequencing schemes, achieving adaptive security in the random oracle model and linear total communications. And the latter is thanks to the compress and duplicate, which is the technical idea we developed along the process. Thank you for your attention.
Are there any questions? We have plenty of time for questions. Chat, no question. Okay, so I didn't see why do you need the random oracle model. Why do you need hash for? So is it crucial for achieving adaptive security or compressing communication complexity? Both?
Because we use the random oracle to hash the tag and derive the randomness to put in the ciphertext.
So,
yeah,
okay, so from the to deterministically generate common randomness from the tag? Okay, yes. I see.
And in the literature, there also exists works on MCFE that does not require random oracle and is using AWE techniques and not the pairing-based.
I see, thanks. Any other question? No. Okay, then let's speak again.
Thank you.
The next talk is compact FE for unbounded attribute weighted sums for log space from SXDH by Pratish Datta, Tapas Pao, Katsuyuki Takashima. Tapas is going to talk.
Thanks, Ms. Mukesh, for the introduction. I am Tapas, and I will present our paper, Compact FE for Unbounded Attribute-Weighted Sums for Log Space from SX stage. It's a joint work with Potish Datta and Katsuyuki Takashima. So in functional encryption, we have a setup authority who generates a master public MPK and a master secret key MSK. Using MSK, the authority can compute a secret key SKF corresponding to any arbitrary function f and distributes it to the users of the system. Using MPK, a data owner can now encrypt messages and publishes the ciphertext CTM. A user now decrypts CTM using SKF and learns the functional value of the message. So simulation security is the most desired notion of security, at least according to the literature. So it roughly says that given a set of secret keys, SKF1, SKF2, SKF3, so on, the adversary can only recover the functional values of the message M and nothing else about the message M from the ciphertext CTM. In this work, we consider adaptive simulation security, and it is formalized by the following set of algorithms. So here, pre-challenge secret keys are generated using a simulated master secret key MSK star, and the challenge ciphertext is computed using MSK star and state ST, which contains functional values of the message M that are queried till then. The adversary can also query post-challenge secret keys, and these are answered using the functional values of the message M. And we say that FE is adaptively simulation secure if these two sets of algorithm are computationally indistinguishable. So simulation security can also be classified into bounded or full collision resistance setting. In bounded collision resistance, adversary is only restricted to query a bounded number of secret keys, whereas full collision resistance setting gives the adversary of full freedom, where he can query any polynomial number of secret keys both before and after the challenge ciphertext. So FE has been constructed for general class of functions, for example, Turing machines or all circuits. However, these constructions are mostly inefficient and or impractical. These are bounded collision resistant, and security can be based on heavy cryptographic tools such as indistinguishability obfuscation or sub-exponential security of LW. So as a result, community also focused to build FE for specific class of functions, for example, linear, quadratic functions and their variants. And these constructions are efficient, simple, they are full collision resistant, and the security can be based on simple and standard assumptions such as DDH, K-lin, or LW. And more importantly, these constructions can be deployed in practice. So this work focuses to advance the FE for specific class of function, namely attribute-weighted sums, introduced by Abdallah, Gong, and Wee. So here we generate secret key corresponding to a function f, which takes input a vector of length m and outputs a vector of length n. And message consists of a tuple x and z. Here we call x as public attribute and z as private attribute. The functionality outputs in a product between two vectors, fx and z. So the state of the art for AWS, consider function class to be only ABP or arithmetic branching program. Master public key size depends on both x and z. Ciphertext size depends on z. Although the first work of the later consider only semi-adaptive simulation security model, which is little bit weaker than adaptive simulation model, we last year showed that how to achieve adaptive simulation security for AWS, but now ciphertext size depends on both x and z. And why this AWS is interesting? Because it has many applications in the sense that it already captures existing important FE schemes such as IPFE or inner product function encryption, ABE or attribute-based encryption, AB IPFE or attribute-based inner product function encryption. However, the current structure of AWS has several limitations. So it is defined in non-uniform or non-dynamic model. Setup is kind of bounded. That means master public key size not only depends on security parameter lambda, but also both on x and z. And ciphertext is also not input specific. As a result, it captures only bounded FE schemes such as IPFE, ABE, where functions takes input of bounded length. So let's see how we can remove these limitations one by one. So we can consider uniform or dynamic modular computation. For example, function class can be Turing machines. Here, attributes can be added or deleted at any point of time. Setup could be made unbounded. That means master public key size only depends on lambda, which is the security parameter. Ciphertext size can be input specific. And with all these, we can also have adaptive simulation security. So this is exactly our work. And due to the feature of uniformity, we now capture unbounded FE schemes such as unbounded IPFE or unbounded ABE, etc. So in summary, we define FE for unbounded AWS or UAWS, and we construct it for log space Turing machines. And our construction has several exciting features. For example, it has compact ciphertext, meaning that it will not grow with respect to multiple occurrences of a particular attribute in the weight function. Also, our scheme is full collision resistance, and it achieves adaptive simulation security under well-known SX stage assumption. So let's see how to define FE for UAWS. Here we first note that setup only depends on security parameter lambda. Function is a tuple of Turing machines MK, where k runs over an index set I. Message is a tuple of x and z. Here x is a binary string, and z can be any vector of arbitrary length. So for example, let's say n. The functionality outputs sum of mkx times zk, where k runs over I if I is a subset of box n. And as previous, we have x is public and z is private. So as a toy example, if your index set I is 1, 2, and 4, and z has length 5, then the functionality outputs m1x times z1 plus m2x times z2 plus m4x times z4. Okay, so technically we started from a very nice work of Lin and Luo, where they built the primitive of ABE for circuits and Turing machines from IPFE and arithmetic key garbling scheme, in short AKGS. Last year we showed that how to extend their framework from payload hiding to attribute hiding setting in the context of FE for AWS. And now we further extend the framework from non-uniform model of computation to uniform model of computation by adding the feature of unboundedness. So in particular, we use AKGS for Turing machines from LL20, and we also use index encoding mechanism with IPFE, and we devise distributed randomness mechanism to achieve our goal. In the pathway, we first construct one key, one ciphertext secret key FE for UAWS, and then extend it to FE for UAWS in public key setting. In this talk, I will mainly focus on this one key, one ciphertext version of the primitive. So IPFE is an important tool of our construction. Here, function and messages are vectors, and the functionality outputs inner product between the vectors. In this work, we consider IPFE with pairing E, G1 cross G2 to GT. Here, function and messages are encoded in the exponent of the source group G2 and G1, and the functionality computes the inner product in the target group GT. The function hiding security of IPFE says that two sets of secret keys and ciphertext are computationally indistinguishable if inner product between the vectors for the two sets are equal. And AKGS is another important tool. AKGS over ZP is a protocol between two parties. First party garbles a function f with values z and beta and outputs a set of level functions L1 or LT. Second party, given fx and level values at input x, efficiently computes zfx plus beta. So here we want that f and x to be public and z and beta to be private. And this is formalized by a simulator which, given fx and the output value zfx plus beta, simulates the level values L1 or LT. AKGS has a nice property of linearity, which tells that eval is linear in the level values L1 or LT, whereas the level functions are linear in the input x. We consider AKGS with piecewise security, and it has two properties. First property says that given level values from L2 onwards, we can reversely sample the first level value depending on the output value zfx plus beta. The second property says that given level values from L3 onwards, we can replace the second level value with a uniformly random value R2. And it can be continued till the last level. This property is named as marginal randomness, and marginal randomness together with reverse sampleability is called piecewise security. And it is very easy to see that piecewise security implies normal simulation security. Okay, so before going to our construction, let's see the core idea of DP21 for building FE for AWS for ABPs. So for this talk, I consider a simple version of function input and output. Function consists of two ABPs, F1, F2. Input is x and z, where z has length 2, and output will be z1 F1x plus z2 F2x. So in key generation, F1 and F2 are first garbled with z1 beta 1 and z2 beta 2, where z1, z2 are treated as variables. The garbling algorithm outputs some set of vectors v, where vk represents the level functions lk for k less than t, which depends on input x, and vt represents the level function lt, which is a function of either z1 or z2. Accordingly, we consider two IPFE, one for computing the level values for k less than t, and other is for computing the level value for t. The key generation algorithm finally outputs IPFE secret keys corresponding to all these v vectors. In encryption, we first compute IPFE secret ciphertext CTX corresponding to the vector 1, x, and we also compute two IPFE ciphertext CT1, CT2 corresponding to the vectors 1, z1 and 1, z2. In decryption, we first employ the IPFE decryption algorithm to get the level values L1.lt corresponding to the function f1, and then given f1x, we can employ the evaluation algorithm of AKGS to get the output of z1 f1x plus beta 1. Similarly, we can get z2 f2x plus beta 2. Now these two values can be added to get the final result of z1 f1x plus z2 f2x, given the fact that beta 1, beta 2 are secret shares of 0 to hide the partial decryption result. Okay, so keeping this idea in back of our mind, let's see how we can construct FE for AWS for Turing machine. So these are the general form of function input and output. However, for this talk, I only consider a simple version of function which consists of two Turing machines, M1, M2. Input is x and z, where z has length 3, and according to the functionality, we will get an output of z1 M1x plus z2 M2x. Okay, so as previous, we want to garble M1, M2. However, we note that AKGS for ABP will not work here because M1, M2 are Turing machines. So we go for AKGS for Turing machine computation. And let's see how it works for DFA for concreteness. So in deterministic finite automata, we have a set of states, 1 to q. One is the initial state, and although we can have many accepting state, but let's consider only one accepting state, q accept, and in this example, it is 3. In DFA, we also have a transition function delta that defines a map by reading the input bits of the DFA. DFA can also be imagined as a layered branching program. Here, each layer consists of 3 nodes for this toy example, and we have a total of n plus 1 layers if we consider a input length of n. The edges between the layer j and j plus 1 are defined by the transition function delta, and since delta is fixed, so we have the same set of edges for each pair of adjacent layers. We can also consider matrices M0, M1 corresponding to the bit 0 and 1, and we traverse from layer 1 to layer n plus 1 using this following matrix multiplication. Here E1 indicates that it is a first basis vector, and it indicates that we always start from initial state 1. So after we read the n bit of inputs, we multiply it with another vector EQ accept, which represent the accepting state. And finally, we'll get an output of 1 or 0 if the DFA, depending on the DFA accepts the input or not. So therefore, we want to garble z mx plus beta, where mx is this matrix multiplication. So let's consider 1 bit of input, then it can be garbled using the following equation. Here, by sampling random vectors R0, R1. And L0, L1, L2 are the level functions, where L2 depends only on the private input z. If we extend the input length, then we can actually extend the chained equation by sampling more and more random vectors. So for example, if we have n bit of inputs, then the total size of garbling will be nq plus 1. So now let's say we want to apply this strategy into our setting. However, we now see that then we need to generate in q plus 1 many level functions at the time of key generation. However, n is the input length and we do not have it yet when we generate the secret key. So let's look at the qjth level function in a bit more detail. So recall that we sampled many random vectors r0.rn, and each of which has length q. We can represent this matrix by a tensor product between two vectors. And these vectors rm and rx can be sampled independently. In particular, we want to write rj to be rxj times rn, where rxj denotes the jth entry of rx. So this helps us to represent lqxj as inner product between two vectors. One is known to the encryptor and other is known to the key generator. Let's call these vectors as uj and vq. We can similarly represent L0 and the last few level functions LQJ. So basically we distribute the process of garbling between key generator and encryptor. So using this idea, we can now directly encode these Turing machines into some v vectors and then generate IPFE secret keys. In encryption, we encode x and z in some u vectors and we compute IPFE ciphertext. And decryption works as before. However, this simple scheme in this slide is not secure. To see this, let's look at two important steps of the security analysis. So in the first step, we use reverse sampleability to reversely sample L0I depending on the output zi min x plus beta I. And if the secret key is queried before the challenge ciphertext, then we hardwire this L0I in U0 vector. However, we notice that we do not have enough space to place these L0I values for all I. And in the second step, when we try to randomize the other level values Lji for j greater than 1, we do it through the uj vector. And again, we do not have enough space. So what we do, we make multiple copies of u0 and uj depending on the length of z, right? But it opens door to a mix and match kind of attack. Now adversary can compute inner products between vectors related to the Turing machine M2, M1 with vectors related to the input G2 and vice versa. And it will help the adversary to compute an unwanted output Z1 M1X plus Z2 M1X. So to tackle this, we apply index encoding mechanism. So we encode the indices and append it to all the vectors in such a way that if you take inner product between the vectors having the same index, we get a meaningful result. Otherwise, we will get a garbage value. So this prevents mix and match kind of attack. And we hope to get the correct output. So let's see how we can actually use index encoding mechanism in the security analysis. So recall that we need to hardwire L0I in U0 vector. And this can be done using function hiding security of IPFE. Now let's say we have one more Turing machine M4 into the function M. So the inner product between the encodings rho I minus 1I dot pi 44, 1 will not be equal to 0 for I equal to 1, 2, 3. Here 1, 2, 3 means the indices of the input Z. And this additional entropy will be provided by index encoding technique. Using the function hiding security of IPFE, we can now sample beta 4 independent of beta 1 and beta 2. And this makes sure that beta 1 plus beta 2 plus beta 4 will not be equal to 0 with high probability. Therefore, the adversary will not get the output Z1 M1X plus Z2 M2X for such a function M. Right. So in the next step, what we want to do, we try to randomize the other level values, Lji for j greater than 1. Recall that these vectors are encoded in the power of source groups because we considered IPFE with pairing. As a first step, we bring the partial garbling randomness into the UJI vector using the function hiding security of IPFE. And then we again recall that this Rj minus 1 is basically Rxj minus 1 times Rm. And in the next step, we hope to use DDH in G1 to replace all these Rj minus 1 by Sj minus 1, which are uniformly random, independent of Rj minus 1. However, to apply this step, we need to make sure that Rxj minus 1 and Rmk are encoded only in the exponent of G1. Unfortunately, it is not the case because Rmk may appear in VQk, which are encoded in the source group G2. For any k, it will appear, right? Hence, we cannot apply this DDH in G1 in this fashion. So here we devise distributed randomness mechanism, which works well with the framework of UAWS, and it eventually helps us to randomize these level values, LJI, with uniformly random values. And we can do it for other vectors that encode the private input Z. Okay, so the actual proof is much more technical for this, and also for the full-fledged FE scheme, I refer to our full version, which is available at the ePrint. Okay, so I will conclude my talk with a few open problems. So it will be interesting to see a construction for FE for UAWS with succinctness. Means that ciphertext size will only depend on the private input Z, not on X. And also, it will be interesting to have such a scheme with adaptive simulation security. And the next open problem would be to have FE for UAWS from lattice-based assumptions such as LW. Yeah, thanks for your attention.
Are there any questions? We have plenty of time for questions. So, so this is for log space, right?
Yeah.
So, but in the building block, you use AKGS for Turing machine. So Turing machine, but means log.
Yeah. We have used AKGS computation for log space Turing machines.
Log space Turing machine. Yeah. So it is infinite.
Yeah. It is implicit in that AKGS.
I see.
Constant. Yeah.
Any other question? So I have another question.
Yeah.
So this is based on pairings, right? What is the technical hurdle for achieving from lattice-based assumption?
Yeah, I mean, you mean that from LWE, maybe the main problem would be to design the framework of DPVS or function hiding IPFE with LWE.
Okay, so it is, maybe I missed something. So it's, in general, pairings is useful for achieving adaptive security, but here also useful for functionality or for this kind of FE.
Yeah. I mean,
so even if we do not consider adaptive security, is it hard to achieve this kind of FE scheme from LWE?
Yeah, I think so, because we used, I mean, we need function hidings property of IPFE even if we consider selective security, right?
Okay.
So that's why I guess it will be hard.
Okay, I see. Thanks. No question? Okay, let's thank the speaker.
Thanks again.
Okay, the next talk is collision-resistant functional encryption for RAMs by Prabhanjan Anand, Kai-Min Jun, Sean Leo Fan, Lo Wen Chan, and Leo is going to talk online. Are you ready, Leo?
Hello, hi.
We can hear you.
Okay.
Yeah, please start.
Thanks a lot for the introduction. My name is Leo. I'm here to present collision-resistant functional encryption for RAMs. This is joint work with Prabhanjan Kami and Lowen. Okay. Functional encryption is a very useful primitive. It's a generalization of public key encryption, identity-based encryption, attribute-based encryption, and it's very useful to construct other powerful crypto primitives such as IO, or watermarking schemes, and succinct randomized encodings. However, prior works only model the functions mainly as circuits or Turing machines. But in this paper, we focus on RAMs. So what is a RAM model? So RAM stands for random access machine. Suppose there is a huge memory starting from 1 to n, and then there is a step circuit which take the CPU state as input, and also one index of the memory and also the content as input. And after the processing of the step circuit, it will update the internal CPU state and output the let's address to read. So that is only for the read-only RAMs. And think about the binary search. This memory could be a very large sorted array, and you will use this CPU, the RAM, the binary search to search the memory for the desired value. And so the runtime of this binary search is only logarithmic to the size of the memory, so that's a huge benefit of the RAM program. So FE for RAMs, the syntax is something like this. So the setup will take the public parameters as input, and maybe also some other parameters such as the upper bound of the runtime, and it will output the public key and also master secret key. The keygen will take the master secret key as input and also the RAM program as input. It outputs the secret key for the RAM program. The encryption will take the public key, the database, which could be very large as input, and output the ciphertext. And the decryption will take the secret key and the ciphertext and output the actual runtime of the RAM program, actual result of the RAM program. So here we will model this decryption as a RAM program. To avoid some trivial construction, we will have this efficiency requirement, which means the runtime of the keygen is proportional to the polynomial in the size of the program, and the encryption algorithm, the runtime of the encryption algorithm is also polynomial in the size of the database, and the most important one is the decryption only is proportional to the input specific runtime instead of the worst case runtime, or it's independent of the size of the database. So that's the syntax and also the efficiency requirement we want. And for the security, we only consider selective security. So it's an interactive game between the challenger and the adversary. The challenger will set up the scheme by running the setup algorithm, and it will send the public key to the adversary. The adversary will choose a database like D0 and D1, and then send the database to the challenger, who will then pick a random bit B and then encrypt the database according to this random bit B, and then send this as a challenge ciphertext to the adversary, the CT star. And then the adversary can query the challenger as many times as he wants for the function key related to the program, as long as it satisfies the condition P to the D0 equal P to the D1, which means the output of the run program of the query run program on these two challenges database are the same. And he can do this as many times as he wants. And at the end of the security experiment, he needs to guess the random bit B chosen by the adversary. And we say the adversary wins the selective security experiment if he can guess the bit B correctly. And as I mentioned before, prior work only focus on RAM for circuits, where the decryption will depend on the circuit size. And as we know, if you convert a RAM program to a circuit, there will be a huge overhead. The size of the circuit will depend on the size of the database. So that's not desirable. That's something we don't want. And the known approaches to constructing FE for RAMs is like these two work, and there is a very recent work I didn't include here. The first one is like the trivial solution. Like if you have FE functional encryption for circuits, and then you can convert this RAM program to circuits, and then you can use the functional encryption for circuit to construct the functional encryption for RAM. But you will have this like polynomial. So the runtime of this like approach, the decryption will depend on the small t, which is input specific runtime, and also the capital N, which is the size of the database. And if the size of the database is very large, then this is not desirable. And the second approach is by Gentry et al. In 2014. Like they show how to construct single key FE for RAMs. Yeah, so our goal in this paper is to say like whether like how can we like do this like collusion resistant FE for RAMs with succinct decryption. So succinct here means the decryption only depends on the input specific runtime of the RAM program. Okay. Yeah, the starting point is of course the gobble RAM. So gobble RAM, the syntax of the gobble RAM is something like this. So there exists a gobbling for the database, which takes the security parameter, the database, and also the upper bound on the runtime for of the runtime, which is a capital T, and it will output the gobble database that's D prime, and also the secret key, which will be used to gobble the program. The second algorithm, the gobble program, takes the secret key and also the program. It will output the gobble program P prime, and the evaluation, which is treated as a RAM program. So which means it has like random access to the gobble database D prime, and it will take P prime as input, and it will output the P to the D, which is actual output. And so this can be treated as a one-time secret key FE for RAM. And some like normal paradigm in constructing this gobble RAM is to say like, first we construct the gobble RAM in the UMA setting, which is unprotected memory access setting. Then we upgrade it to like full security. So like we use like basically ORAN to cover the random access pattern. We use ORAN to cover the memory access pattern, and we use secret key encryption to cover the actual memory content. So that's a basic paradigm in constructing gobble RAM. And the challenge is like if we want to like go from a gobble RAM to like functional encryption for RAMs, there are some challenges in there. The first thing is like parallel reusability, like as shown by Hamlin et al. In 2019. Like this existing gobble RAMs are insecure in parallel reusability setting. They are only secure in this like a sequential reusability setting. Yeah, so maybe like we can use FE for circuits to achieve this parallel reusability, which means like it can be like run by several like decryptor in parallel, and we still can achieve security. And second part is like succinct. So for succinctness, we require the parameters neither grow with the database length nor the worst case runtime, and the decryption time only goes like proportional to the input specific time. So we can perhaps use succinct gobble RAM, which will be used here, but it doesn't have this like parallel reusability. So our high-level idea is like we can like combine this FE for circuits and also succinct gobble RAM like with some special properties to achieve FE for RAM. So that's a high-level idea. Yeah, so we start from this like non-succinct gobble RAM, and yeah, and using some tricks like IO, we can get succinct gobble RAM, and then from the succinct gobble RAM, we can get the succinct and also reusable gobble RAM, and then combining this succinct reusable gobble RAM with like FE for circuit, we can get FE for RAM. So that's the roadmap to achieve this FE for RAM construction. Okay, let's start from the beginning. Yeah, so we start from the non-succinct gobble RAM, and this means the parameters in the scheme could grow with the worst case runtime of the RAM program. And for the evaluation, actually we require the time needed. Here is like only proportional to the actual runtime of the computation, and is independent of the database. And such a scheme can be constructed from a gobble circuit, which can be constructed from one-way function. And for each step, like a blueprint for constructed this non-succinct gabble runs to something like this. Like for each step, like we evaluate the ith gabble circuit to get the ith step of the execution for the P to the D, which is a random execution. And then we compute the recoding step, like we go from the ith output encoding to the I+1 wire labels. So through this way, we can use a gabble circuit to translate from the current step to the next step. And for full security, we can use ORAN, as I said before, to hide the memory access pattern. And we use secret key encryption to hide the memory content, basically. Okay, so like succinct, like go from a non-succinct gabble run to a succinct gabble run, we'll use like the obfuscation to delegate the execution of this non-succinct part. And succinct gabble run means like the size of the gabble program is independent of the worst case runtime T, capital T. As recorded in the last slide, like for each step, we need to generate a gabble circuit, which means the size of the gabble run depends on the upper bound of the runtime, which is capital D. So the idea here is we use obfuscated circuits that will produce a non-succinct gabbling of the program, and then but just obfuscating the non-succinct gabbling procedure doesn't work, since the size of the obfuscated circuit will be as large as the size of the non-succinct gabbling program. So we need some property, like we need to decompose the gabble program into many small components, such as the obfuscated circuit will only produce one component at a time. And yes, so these two properties we need here is like the first place, like we can decompose the program into these small independent components. And to argue the security, we need to carry out the hybrid of the non-succinct gabbling scheme by hardwiring just a small subset of the component at a time. And by the local simulatability, we can guarantee that in each hybrid, the amount of the hardwired information is never too large, and therefore we can achieve succinctness. So that's two necessary properties to go from the non-succinct gabble run to succinct gabble run. Yeah, so like for UMA security, like so as I said before, the paradigm, like we first constructed the UMA security, then we go from the UMA security to full security. And for the UMA security, we can actually use the network in GOS 18 to satisfy. They already satisfy the two properties I mentioned before. And for full security, we need this like ORAN with strong localness, the randomness, which will be used to achieve this local simulatability. And then we use this like a time encryption. So time encryption, like at high level, is just an encryption scheme that allows you to issue the encryption and decryption keys with growing power as the evaluation goes on. So like a key at a time t can be decrypted anything that was encrypted under time t, but it cannot decrypt anything like upper that is larger than t. So using this like two additional components, the ORAN with strong localness, the randomness, and the time encryption, we can achieve full security. So that's for the succinct gabble run part. But the succinct gabble run itself is not going to be sufficient to construct the FE for RAMs. Like record, like in FE for RAMs, the adversary, he can get like many functional keys as he wants, and he can do this like do this decryption in parallel. So we need this like reusable, parallel reusable gabble RAM. So this means like given this like gabble database D prime and also multiple gabble program P1 prime to PK prime, we can only learn this like P1 to the D, to PK to the D. And we only learn this like output instead of like anything about the database. Yeah, so like to construct this like succinct and also reusable gabble RAM, we also it is like very useful to split this thing into two parts. In the first part, we need to construct this like succinct reusable gabble RAM with UMA, which is secure in the UMA setting. And And note, like in this like UM setting, like essentially what we need to do is to protect the memory execution, and we do not face any like trouble in adapting the scheme, like the GOS18 scheme, into the reusable setting. So the first part is easy, the UMA part is easy. And the second part is like we need to use this like UMA secure double RAN to construct a fully secure, succinct, reusable double RAN. So that's the second step. Okay, yeah, so there are some challenges in the second step. The first one is like we need to protect the memory content. So to protect the content of the memory, we need to encrypt the encryption key into our Gabble program. But however, like if we are giving out one Gabble program, we can no longer invoke the security of the encryption scheme to say that the adversary has no information about the underlying database. So since the Gabble program contains a hardware secret key. So therefore, we need to remove the encryption scheme in the hybrid very carefully. So on a high level, the idea is to like remove the encryption scheme one by one in each hybrid. Like we start from the encryption scheme for the last Gabble program, and we just write this like junk in the database instead, and then we use the IND security to argue that this is indistinguishable from the previous the second last hybrid, and then we move from the last hybrid to the second last hybrid, and so on and so forth. Yeah, but this like the security proof doesn't work in the reusable case, since like when we try to equivocate the output or the database writes and remove the encryption key, the adversary actually like he can in principle still be able to distinguish the two distributions, as like the same time encryption will appear in the other Gabble program. So that's like one issue like we need to tackle. And the second issue like is like how to protect the memory access pattern. Like we need to like somehow change the access pattern without hardwiring like too much information. So for that, we need to use the rewindable ORAN with strong localized randomness. Yeah, so like we designed this like a rewindable ORAN scheme satisfies this like strong localized randomness, which will be relying on the public key double efficient peer. Okay, so to put things together, like we show, like we can construct the FE for RAMs like this. So it is a combination of FE for circuits and also the succinct reusable Gabble RAM. So to encrypt a database D, we first use the succinct and reusable Gabble RAM to gobble the database, and then we get the D prime, which is a Gabble database and a secret key. And then we use a functional encryption for circuit to encrypt this secret key and to generate a ciphertext. And the ciphertext for the FE for RAM will be this like two components, the Gabble database D prime and the ciphertext for the functional encryption scheme for circuits. Okay, so that's the encryption part. And to generate the function key for RAM program P, we first define this circuit G to be the Gabble to be the gobbling of the program, which has a P hardwired, but will take the secret key as input, and then we generate the secret key for this newly defined circuit, and the secret key for the RAM program will be the secret key, the SK sub G. Okay, to decrypt, we first need to recover the Gabble program P prime, which will be done by using the decryption algorithm for the functional encryption for circuits. And then we can use the Gabble evaluation for the Gabble program, for the Gabble RAM to do the actual evaluation. And the security proof will we first hardwire the Gabble program, and then we use a reusable security of the Gabble RAM to argue the security proof on, I won't talk about the security proof here. Okay, so in summary, our results, we show FE for circuits plus succinct reusable Gabble RAM, then we can get FE for RAM. And compare with a trivial solution, which is the combination of FE for circuit with the RAM to circuit conversion, our work achieves the succinct like in every perspective. So yeah, so that's our result. And there are many missing details in this talk, and we also show like actually you can do bounded key for bounded KFE for brands also like in our paper. Like if you are interested, please take a look at our paper. Thank you. I'm happy to take any question.
The time for question. Are there any question?
My question is, so finally you use I/O in the construction, right? Can you go to the previous slide?
Yeah, like.
Yeah,
like in,
no, just the
in addition
second
to-
last, the second last slide.
Yeah,
So
in addition to-
for succinct reusable garbled RAM, I believe you're using, you need I/O. Is that correct?
Actually, in addition to I/O, you also need the VBB obfuscation. Yeah, to achieve the rewindable ORAN with some like the strong localized randomness. So like yeah.
You
yeah,
need
so, like, we
VBB
thought
obfuscation for which class of circuits?
For the we need VBB for the like the I guess the logarithmic depth of circuits. Yeah, since we need to use that to construct this rewindable ORAN with some special like the strong localized randomness property. Yeah, we also think about whether this is like avoidable. Yeah, but we don't know how to do it without VBB obfuscation. But as like in the FHE for RAM's paper, they also use the VBB obfuscation to construct FHE for RAM. So yeah, we didn't make much progress on that front.
All right, thank you.
Thank you.
Are there any question? So is the proposed scheme is adaptively secure or selectively secure?
It's selectively secure.
Okay, so okay, I see. Okay.
Yeah, and we also don't know how to do adaptive security.
Mm-hmm. Thanks. No other question? Okay, let's thank the speaker again.
Thank you.
The last talk of this session is knowledge encryption and its applications to simulatable protocols with low round complexity by Yi Deng, Xin-Xiong Zhang, and Xin-Xiong is going to talk online.
Can you hear me?
Yeah, we can hear you.
Okay. Thank you for introduction. In this talk, I would like to present our paper. I'm Xin Zhang. It's a joint work with Yi Deng. In this talk, I will first introduce our motivations, and second, I will show the notion we put forward called knowledge encryption. Then I will present a high-level idea about how to construct knowledge encryption, and finally, I will give a simple introduction about its applications. First, let's consider the following simple protocol. Roughly, the welfare sends it publicly to the approver, and the approver will encrypt its double approve, proving that it knows the secret key or some other statements. That's a toy example. And let's ignore the soundness issue here and only concentrate on simulating the approval. Now, as you can see, if the welfare doesn't know the secret key, and it can decrypt or distinguish subtext, it can't distinguish or decrypt subtext, then the simulator can encrypt domain message to conclude the simulation. And if the welfare knows the secret key, which means that it can decrypt or distinguish subtext, Then the simulator can use the secret key as a trapdoor to generate the double proofs via individual extraction. However, this requires the underlying encryption scheme, satisfying that the ability of distinguishing or decrypting the subtext means the knowledge of the secret key. In other words, one can efficiently extract the secret key from any decryption algorithm or distinguishing algorithm. Then consider the following two encryption schemes closing to our requirements. That's witness encryption and the conditional disclosure scheme. Witness encryption allows one to use an NP instance as public key and the corresponding witness as secret key. And CDS allows one to generate key pairs from an NP instance and its witness. Their security requires that if the instance is invalid, no efficient algorithms can decrypt or distinguish subtext. However, neither of them provides any security when using a valid instance. In other words, the decryption algorithm provides only a sound proof that the corresponding public key is valid. Now we have a question. Can we construct a public key encryption for which only algorithm that knows the secret key can decrypt subtext? In other words, the decryption algorithm provides a proof of knowledge of the secret key. Unfortunately, most of existing encryption schemes fail to satisfy this requirement without knowledge assumptions. The only exception we're aware of is a variant of Robin's encryption, of which security is based on the factoring assumption. As shown in DOM 20, this conception is useful in constructing typical security protocols, such as selective opening secure commitment and concurrent zero knowledge protocol. Well, motivated by this question, we put forward the notion of knowledge encryption. Like CDS, a knowledge encryption is associated with an NP language. The key pairs are generated from an instance and its witness. We let the public key and the secret key contain the instance X and the witness W respectively. Knowledge encryption should satisfy the witness extractability, indistinguishability, and the public key simulation properties. Witness extractability claims that if an efficient adversary can distinguish decrypt subtext, then there is an efficient algorithm extracting the witness, which is also part of the secret key from the adversary. This should hold even for malicious generated public key. Indistinguishability requires that for any fixed instance and its witness, no efficient algorithm can distinguish subtext without the secret key. And the public key simulation requires that one can efficiently simulate a public key for any valid instance without knowing its witness. In our paper, we present two constructions for knowledge encryption. The first is based on CDS and random self-reducible encryption, and the second is based on CDS only. It means that the knowledge encryption can be constructed from two-round game-based secure oblivious transfer, which is known from DDH, QR, or LW assumptions. Here, we only give a high-level idea about the second construction. Remind that a CDS scheme can be regarded as a special two-message secure function evaluation. It can be constructed from a two-round oblivious transfer with scheme-based security and a governing security scheme for the security C shown on the slides. Here, this security takes input the instance X, witness W, and a message M, and outputs the message if and only if W is a valid witness for X. On input X and W, the key generation algorithm runs the first round of oblivious transfer to encode the witness bit by bit. It outputs X and the OT messages as the public key and outputs W and the randomness used in OT as the secret key. To encrypt a message, the sender first gobbles the secret and sends the gobbled secret and the corresponding labels for X and M directly, and sends the labels for W via OT protocols. Finally, by retrieving the labels for W from OT and evaluating the garbled circuit, one can obtain the message encrypted. So to construct a knowledge encryption scheme, we embed a simple decoding mechanism in the secure C. As shown on the slide, C has an extra input Y, and Y equals all zero string. C works in the same manner as before. When Y doesn't equal all zero string and W is a valid witness, C outputs the sum of Y, WI. We modify the encryption and decryption algorithms naturally. Notice that the honest encryption algorithm always chooses Y as all zero string. Here we only present a high-level idea about the witness extractability property of this construction. A key observation here is that, as shown on the slide, when choose Y as a string of 0, except the J's position, the result subtext will be indistinguishable from the encryption of J's position of witness. So an extractor can extract the complete witness bit by bit by checking that in the view of adversary, this subtext is closer to the subtext of which bit. We refer to our paper for more details. Now, as shown on the slides, knowledge encryption is useful in the construction of the first 3 round T-epsilon simulatable oblivious transfer and lots of other protocols achieving T-epsilon security, such as delayed input zero knowledge argument and two-party computation for independent input functionalities. And here we only present a simple introduction about the first construction. And we refer to our paper for more details about other constructions. A various transfer is a protocol between a sender holding 2 messages and a receiver holding a choice bit. At the end of the protocol, the receiver should learn the message of his choice, but learn nothing about the other message. The sender, on the other hand, should learn nothing about the receiver's choice bit. Using knowledge encryption, we construct the first 3 round T-epsilon simulatable oblivious transfer, satisfying the full simulatable security for the receiver and the T-epsilon simulatable security for the sender. Our construction relies on the techniques including Wayman construction and individual reductions put forward by Deng. A natural idea here is to have the receiver generate a pair of public keys, pick0 and pick1 of knowledge encryption from 2 NP instances, x0 and x1. And the receiver knows witnesses for one and only one of these 2 instances. And so that it can receive one and only one message encrypted by the sender. Here among these 2 public keys, one public key is generated using the key generation algorithm, and the other is generated using the public key simulator. Then for the sender, it doesn't know which one is simulated. Therefore, it doesn't know the input bit B of the receiver. Now, there are 2 major challenges. First, we need to make sure that the receiver knows witness for only one of these 2 instances. And second, the simulator needs to extract the input of the adversaries. To solve the first challenge, we require the sender to generate and send a hard NP instance Y, and the receiver uses the Sigma protocol to generate these 2 instances, X0 and X1. Remember that a Sigma protocol is a 3 round public coin protocol satisfying the special soundness and the special honest welfare zero knowledge properties. The special soundness property requires that given 2 acceptable proofs with the same first round message and different challenges, one can efficiently extract the witness for the instance. And the special honest welfare zero knowledge property requires that given challenge E is easy to compute an accepting transcript, which is indistinguishable from an honest one. Now go back to our construction. Given Y and input B, the receiver prepares two instances, X0 and X1, in the following way. It first generates a random challenge EB and runs the honest welfare zero knowledge simulator to obtain an acceptable proof AEBC for Y. It chooses another random challenge if Y must be not equaling to EB and sets instances xi in the form of YAEI. We call xi a yes instance if and only if there is a string z such that AEIZ is a acceptable proof for Y. And from the special soundness of Sigma protocol, without the knowledge, without the witness of Y, anyone cannot generate two acceptable proofs with the same first round message but different challenges. Therefore, the receiver knows witnesses for only one of X0 and X1. As for the choice of Y, in our paper, we let Y equals Y0, Y1, where Y0 and Y1 are images of a one-way function F. Y is said to be a yes instance if there is R such that FR equals Y0 or FR equals Y1. And finally, the sender proves to the receiver that it knows one prime image of Y0 or Y1 by a WI protocol satisfying special soundness. This step is used for the following security proof. To simulate the receiver, roughly the simulator first extracts a witness for Y from the WI protocol by rewinding. Then it can generate two yes instances, X0, X1, and therefore to valid the public keys, PK1, PK0, PK1 with their secret keys. When receiving the two ciphertexts from the sender, it can decrypt to obtain both messages and send them to the functionality to conclude the simulation. From the fact that a simulated public key is indistinguishable from an honest one, the messages extracted by the simulator in the ideal world are indistinguishable from the output of the receiver in the real world. Remember that that's a non-traditional extraction strategy. The simulator obtains message by decrypting rather than rewinding. To simulate the sender, the simulator needs to extract the input bit of the malicious receiver. Here we will use the individual reduction technique put forward in DEN 20. Roughly, this technique shows that for any R star, there is a good extractor E outperforms all other algorithms in extracting secret keys or witnesses. The simulator runs this nearly optimal extractor E to extract the secret key, or in other words, the witness of the instance KE public keys generated by the malicious receiver. According to the result of extraction, the simulator runs in different manners. In the case that it succeeds to extract only one witness, WB prime, the simulator sets B equals B prime and sends it to the OT of OT functionality. After obtaining the message MB, the simulator encrypts it using both public keys, respectively, to conclude the simulation. In the case that it fails to extract any secret key, the simulator just sets B equals 0 and continues. And if it succeeds to extract both secret keys, then the simulator just aborts. Now, in the first case, it means that the adversary can only decrypt the ciphertext under the public key PKB. Otherwise, suppose the adversary can distinguish the ciphertext under public key PK1 minus B. Then from the witness extractability of knowledge encryption, there is an efficient algorithm extracting WE1 minus B, breaking the optimality property of the extractor. Therefore, remember that the only difference between an ideal execution and a real one in this case is the message encrypted using PK1 minus B. The adversary cannot distinguish them. In the second case, it means that the adultery cannot describe or distinguish both subtexts. Following a similar analysis with the first case, it's easy to show that the simulator can successfully conclude the simulation in this case. And in the third case, if it extracts two witnesses, then from the special signage of sigma particle, one can efficiently extract a preimage of Y0 or Y1, which is inferable from the fact that A prime, E prime, D prime is a witness hiding. Therefore, the simulator will succeed in all these cases. In other words, no matter which strategy the adversary chooses, the simulator will always win. That's a win-win structure. At the end, we present a summary of our paper. In our paper, we first introduced the notion of nudging encryption and present its definition. Then we present two constructions for nudging encryption, which shows that nudging encryption can be conducted from any two-round game-based oblivious transfer. And finally, we present some applications of nudging encryption, including the first three-round typical simulatable oblivious transfer and a variety of protocols achieving typical simulatable security, which outperform prior works in either relying assumption or security. That's all. Thank you for your attention.
Are there any questions? So knowledge encryption is very similar to extractable witness encryption, but the difference is knowledge encryption has key generation phase. Is right? Is it right?
Yes, the knowledge encryption will have an actual key generation algorithm, and it rely better assumptions than extractable witness encryption.
Okay, so on the does extractable witness encryption imply knowledge encryption? Is there any relationship between extractable witness encryption and knowledge encryption?
Well, extractable witness encryption are very close to the knowledge encryption, except the indistinguishability properties. And in some cases, you can use extractable witness encryption as a replacement. And the main idea of our paper is to conduct low-round complexity protocols with more standard assumptions such as TDH or QR. And I think extractable witness encryption is hard to conduct from these assumptions.
Thanks. Are there any questions? No? Okay, thanks to speak again. This is the end of this session, and we have lunch break.
Hi everyone, welcome to the first session on multi-party computation. This session has 3 talks. The first one is random sources in private computation, which is joint work between Geoffroy Couteau and Adi Rosen, and Geoffroy will give the talk.
Yeah, thank you very much. Can you hear me well? Does it work?
Works.
Yeah, perfect. So, hi everyone. This talk is going to be about random sources in secure computation, a joint work with Adi Rosen. So, our model is a model of information theoretic secure computation. You have n parties with inputs x1 to xn. There is an adversary who corrupts at most t parties, where t is at most half of the parties, typically in this setting, and your goal is to compute some public function f without revealing anything more than the result of the function. Okay, so information theoretic computation has been well studied, and among the many things that are well known, we know that it's impossible to securely compute a function if you don't use randomness. Right? Deterministic secure computation is not possible. You need the ability for the parties to toss cryptographically secure random coins. So a well-studied question is to understand how much randomness do we need to securely compute some arbitrary function f. And the motivation for that is that it's not always easy in the real world to produce high-quality cryptographic randomness. You need to use the proper piece of code. You need to use a good randomness generation strategy. So it's natural to treat randomness as a scarce resource and to attempt to minimize how much of it we need. In this work, we ask a different but related question, which to our knowledge was never asked in the past. What we ask is, what is the minimum number of parties in a protocol that need to have the ability to toss coins in order to be able to evaluate an arbitrary function f? So the motivation for this related question is slightly similar. In the real world, our randomness generation abilities might differ. Some might be using a powerful server with a proper implementation of the cryptographic mechanism. And so this server might be able to produce reliably high quality randomness, and everyone might be okay trusting this randomness, but others might be using less trusted software or less powerful devices. And we might not want to trust their ability to generate high quality randomness throughout the protocol. So for example, in my example, we might want to ask the 2 parties that use their cell phone to participate to the protocol to not produce random coins during the protocol. We don't want to trust their ability to toss cryptographically secure random coins. So is it possible to run the protocol without having them tossing any coins? So that's the question we ask. And our main result is a complete characterization of what we call the random source complexity of T-private computation, where T stands for the number of corrupted parties. So I'm giving you the picture here. What was known before was this result by Kushilevitz and Mensur from PODC 96, which shows that T parties need to have the ability to toss coins to be able to T-privately compute some functions, and in particular the XOR function, where the parties want to obtain the XOR of all their inputs. So actually, at the time, Kushilevitz and Mensur wanted to prove a lower bound on the number of bits you need to toss to compute the XOR functionality, but sorry, actually their lower bound is proven by showing that you need at least T different parties to have the ability to toss random coins. So we observe that in particular, it extends to the stronger result that you need at least T sources for any function, for some simple functionality such as XOR. So that's our previous work. So we start with 2 relatively easy results. We show that you can actually slightly straighten the Kushilevitz and Mensur lower bound. For some randomized functionalities, you can show that you actually need T+1 parties with the ability to toss random coins. And furthermore, there is a matching upper bound showing that T+1 parties is sufficient to T-privately compute any functionality. So in the sense, I call that the easy results because that's what makes sense, right? If the parties can corrupt up to T players, then if you have T plus 1 parties who can toss coins, you will always have one non-corrupted party who can toss randomness. So someone will produce randomness which cannot be corrupted. And if you do it the right way, you can use this randomness for everyone in the protocol. So that makes sense, and that's actually not too hard to prove. However, the really non-trivial and interesting result, which is our core result, is this one on the bottom left. We show that if we only look at deterministic functionalities, so which is still a huge class of functionalities, it actually suffices that T parties have the ability to toss coins to T privately compute any deterministic functionality. So I want to I want to let a minute to let this sink in, because it should be surprising. So what I'm saying is, we know that secure computation is impossible if the parties are deterministic, but here I'm claiming that secure computation for all deterministic functionalities becomes feasible, even in a world where the adversary could potentially corrupt all the parties who can toss random coins. So somehow it's possible to do secure computation with a randomness that could potentially be entirely seen by the adversary. And I don't know for you, but to me, it really sounds surprising at first sight. So that's for our first result. Okay. Yeah, so our second result is to try to understand a bit better the relation between the randomness complexity and the random source complexity. So in particular, if you want to use a minimal amount of random sources, can you do it while using not too much randomness, or do you need to blow up the amount of randomness you need to use? Okay. So it's typically very, very hard to prove randomness lower bounds in cryptography, and in general, tight lower bounds have only been proven for very simple functionalities. So as is the standard in the literature, we focus on some very simple functionalities. XOR has been handled by Kushilevich and Mansour. So we look into the end functionality, and we look at the simplest case of one privacy. And even in this very simple case, we don't have tight upper and lower bounds. It's a hard problem. It has been looked at a few times in the past. So currently, the best known protocol for one private n party end is a TCC 19 paper that securely compute the n party end using 8 bits of randomness and 2 sources. So we ask, well, if you want to use a minimum number of sources, which by our previous result is 1, is it possible to match this lower bound? And surprisingly, we actually managed to improve simultaneously the randomness complexity of the protocol. We lower it to 6 bits and to use a single source. So it's a result which is also of independent interest as a study of randomness complexity for some simple functionalities. So, as a starting point, as a warm-up, I'll explain why if you have T plus 1 sources, you can T privately compute all functionalities, which is a result that you should expect to hold. And then I'll devote most of the presentation to our core result, the fact that if for deterministic functionalities, actually T parties tossing coins are necessary. If you want to see the lower bound, I encourage you to see the paper. So, assume you have T plus 1 sources. So here I take 5 parties. I assume that T is 2, so we have a honest majority. And so we have 3 parties who can toss random coins, depicted here with those little coins, and we want to compute some function f. Okay. So the ID is just to let all the parties which can toss random coins, we just want to let them all send a random tape to each party who cannot toss random coins, right? So my party here will send a random tape to the 2 parties here who cannot toss random coins, and so we'll do everyone with the ability to toss coins. And in the end, all the parties who did not have a random tape set their random tape to the XOR of all random tape you received from all parties who can toss coins. And of course, afterwards, with all these random tapes, they can run any information theoretic secure computation they like, for example, BGW. And this works fine because since there are T plus 1 sources, there will always be an uncorrupted source, So when you XOR the random tapes from the viewpoint of the adversary, these random tapes will be truly random, so we can just invoke the security, for example, of BGW, right? So that's simple. Now, how do we do if we actually want to have only T sources? So now I go back to the setting of computing F, but I want to compute a deterministic function, and I only have two parties who can toss random coins. And here, I have to deal with the fact that the adversary could potentially corrupt all the sources, in which case you will see all the randomness ever used in the protocol. So if I want to defend against that, I have to isolate the sources. In a sense, I have to shield the adversary from seeing things that these sources could see throughout the protocol. So we put the sources aside, right? And because we don't want them to participate to the protocol, we will let them share their inputs between the deterministic parties, so that the deterministic parties will have all the information necessary to compute everything without using the sources, which we want to keep isolated. So the two sources share their inputs, and then the three deterministic parties here will replace the initial functionality by a new functionality f prime that will first reconstruct the shared inputs of the sources, and then apply the function f on the reconstructed input plus the joint inputs of the deterministic parties. So what you would expect. Now, our three parties need to be able to compute the function, and they will do so using GMW. So a very important thing to know is, to observe, is that now that we've isolated the sources, here, there might be, there might not be a honest majority anymore among those guys. But among those deterministic parties, we know that there will always be at least one uncorrupted party. So we use a protocol like GMW that can tolerate up to n-1 corruptions out of n. So what's GMW? It's a well-known secure computation protocol that allows you to securely compute any Boolean circuit. And I'm skipping a few details, but the core thing here is that the parties maintain as invariant the fact that they have shares of the computation through the wires of the circuit. Computing XOR gates only involve local computation, and computing AND gates can be done by consuming what's called the Beaver triple. So this is combining the standard GMW protocol with the well-known observation of Beaver. So none of this uses any randomness, except the part where we want to compute an AND gate, which is done by consuming a Beaver triple. So what we use is we use an inner protocol, which will of course use the sources because that they are the one who can produce randomness to compute those Beaver triples. So whenever we want to compute the Beaver triples, we invoke this inner protocol where first the source will send random tapes to the deterministic parties. So as in my warm-up example, the parties XOR the tapes in order to have their own random tape. And then all parties together run a distributed BGW protocol where everyone, for the randomized functionality, that outputs random Beaver triples only to the three deterministic parties here. So that's exactly like our warm-up protocol, the T+1 source protocol. But the crucial thing is that now I'm only applying this protocol in a safe context because this functionality here is independent of the inputs. So even in a world where the two sources will be corrupted, nothing too bad can happen because nothing in this protocol will ever depend on the private inputs. Okay? So the deterministic parties use GMW. They do everything among themselves, but whenever they need a Beaver triple, they go back to the sources, they run a BGW protocol all together, and at the end of this BGW protocol, they get a Beaver triple, and they can use this Beaver triple in GMW. They do that until they get the output, and then they send the output back to the sources. Why is this secure? There are two cases to study. The first one is the case where at least one of the sources is honest, and the second is the case where no sources are honest, in which case we know that the adversary did corrupt all the sources, but also only the sources. So for the first case, two observations. If there is one honest source, then in this third phase of the protocol here, we know that the BGW protocol was secure because the adversary cannot control all sources, so the shared tapes are truly random, so we can invoke the security of BGW. So the beaver triples, we can think of the beaver triple used in the GMW protocol as coming from a trusted source of beaver triples. And also we know, since there is a honest majority of parties, because T is below n/2, that there will be at least one honest party. So we can invoke the security of GMW in the outer protocol, and security follows. In the other setting, where the adversary will corrupt all sources, then we know that the adversary corrupts only the sources. And in this case, we simply observe that no source ever sees anything dangerous. Right? In the input sharing phase, only the source communicate to the players. In the outer protocol, the sources are never involved. In the tape sharing phase, only the sources communicate to the players. And the BGW protocol, as I said, is input independent. So here, nothing bad can happen. The only thing they get is the output in the end. That was for security. Now in the 5 or 4 minutes that I have left, maybe 3 minutes, I want to talk a bit about the second result. So one private n party end with 6 bits and 1 source. So the motivation is that n is a basic building block of MPC. And for the other basic building block, which is XOR, we already have tight lower bounds. The randomness complexity of one private end has been studied in previous works, and we know that you can do it with 8 bits and 2 sources. So that's our setting. Parties have a single bit each, and they want to compute the end of all their bits. So we have a budget of 6 random bits. And the way we do it is we'll have P0 toss all random coins throughout the protocol. The parties will communicate in a line where P0 will communicate with P1 and P2, P1 will communicate with P2 and P3, and so on. And we'll proceed as follows. The protocol starts by having P0 share X0 and X0 times some mask, which is a random mask that it produces. So producing the mask and sharing X0 and X0 times the mask, that uses already 3 random bits. And those 2 things here, they will be our invariant throughout the protocol. Meaning that the parties will always have shares of the products of all xi's so far, and the product of all xi's so far times a mask. So now we just have P0 send the right hand side of the shares to P1 and the left hand side of the shares to P2. So now P1 and P2 have the shares of this invariant, and he also sends the mask to P1. And we have P1 mask his input x1 using the mask, so that's why we call it the mask, and send this to P2. And the 2 parties do this local computation. So they do some kind of linear combination with this new mask. This is what that masks x1 and the shares that they have. And trust me on that, if you write the calculation, you can see that those 2 things here, they form additive shares of x0, x1 and x0, x1 times a new mask. So we successfully managed to maintain this invariant because now the parties P1 and P2 have shares of the product of the xi's and the product of the xi's times a masks, where we only added the new xi, like the x1, to this invariant. However, what goes wrong is that the first here is perfectly fine, but the second one is biased because it was computed by doing a local product of values. So the shares are not uniformly random, they are biased towards 0. So to randomize them, we let P0 sample an additional randomizer bit, which uses 1 more random coin from our budget, and we let P1 and P2 use this random bit to randomize this share. And if you do all of that, you notice that that one of the shares, this one here, was never used. I mean, its randomness was never used anymore, so we can reuse it, recycle it, to define it as the next randomizer bit, so as to maintain the invariant. So that's how we propagate the share. We propagate everything throughout the protocol until the end. In the end, what's left to do is just multiplying the last inputs of the last party to this product. And if you look closely at what we want to do exactly, what we want to do is exactly do an oblivious transfer, actually. And we know that oblivious transfer can be done with 3 random bits. So we could do that. And we actually also observed that the last randomizer bit is never used anymore, so we can recycle it for the oblivious transfer. Hence, we do the full oblivious transfer only using 2 additional random bits, and this way all parties get the output. Yeah, so that's the end of my talk, and I'll be happy to answer any question.
questions? Okay, so I have a couple of questions. The last result that you showed was pretty interesting, the trade-off between the number of sources and the amount of randomness that you need. I'm curious if you can say anything more general other than this specific case of one private and n party.
So so more general, yeah. So we actually do have a conjecture in the paper. I did not mention it in the talk because it's only this, meaning it's a pure conjecture based on, say, a somewhat educated guess, because we tried to do the best we can and we don't see an obvious reason why we should be able to do better. So let me tell you what's a conjecture. What I will conjecture, but I'm not 100% sure that my co-author will conjecture exactly the same thing, but what was stated in the paper seems to work, is that if you want to use a minimum number of sources, which is t sources, then you need a factor t blow up in the randomness complexity. Meaning, if you take any non-trivial functionality, so sufficiently non-trivial functionality, so for example, something that will involve multiplication gates and the like, so not just a simple linear functionality, and you call R the best randomness complexity that you could possibly achieve in a world where everyone can toss random coins, then if you only want the minimum number t of parties to toss random coins, you will need an amount of randomness proportional to t times R to securely compute it. And we know that t times R can be achieved because this is what our protocol achieves, the one for t sources for all deterministic functionalities, and we conjecture that it's the best you can do. And that here, that means that in the setting of one privacy, we're expecting to be able to match actually the best possible randomness lower bounds, because the factor t is just a factor 1.
Interesting. Thanks, that's pretty cool. Also, I was wondering if you considered a model. So if I understand correctly, in this model, you sort of know ahead of time which parties are not going to be random sources and which ones are. So I was wondering if you could say something about a model in which you don't know who's going to have bad randomness and so on.
Yeah, so if you have no idea, it's a very natural question. If you don't know in advance who could have bad randomness, actually, I don't think, I'm pretty sure we can't say anything better than the easy results. Meaning, there is no way to do this strategy of isolating the sources. So isolating the sources is also separating the people who could have bad randomness and making them compute the function on a side. And if you can't do that, then there is nothing non-trivial you can do. Meaning, those upper bounds with t plus 1, they also hold if you don't know in advance who can toss random coins, right? So you will also have the ability to compute any functionality with t plus 1 random source just by using this warmer protocol where everyone will share, all parties, there you would ask all parties to share random tapes with everyone, and then everyone will define his own random tape to be the XOR of all random tapes received by all parties. This way, if at least t plus 1 sources can produce high quality randomness, then you will have re-randomized properly all random tapes of everyone, and that's the best you can do. You cannot hope for better if you don't know who are the parties with the low quality randomness. So yeah, it's a setting where you can't say much. The setting that we consider is also well motivated by the fact that in the real world, you might have a good idea of who's using a trusted device and who's using, I don't know, his cell phone.
Much. Thanks for the talk. Okay. So the next talk will again be given by Shofra. It's going to be on non-interactive secure computation of inner product from LPN and LWE. This is joint work between Shofra Koto and Mariam Zalezadeh.
So hi again, everyone. I'm following directly with a second talk. As was said in the introduction, it's a joint work with Mariam Zalezadeh, and I'll be talking about non-interactive secure computation of inner products from LPN and LWE. So let me start by recalling briefly non-interactive key exchange. Non-interactive key exchange, you all know what it is. It's protocol where n parties will simultaneously broadcast their public key. I'm looking only at like non-interactive key exchange between pairs of parties. So, and so n parties will simultaneously broadcast a single message. And then after broadcasting their single public key, any pair of party without further interaction can locally compute from its state and the other party public key their shared key. Right? So you can do it here between P1 and P4, but you can also do it between any other pairs of parties. And this is a very appealing interaction pattern. You use really only one round of broadcast, which is nice. And also you avoid the n squared cost that you would have if you are using naive pairwise exchange. So you're shaving a quadratic amount of communication compared to non-interactive solutions. So a natural question is to wonder, would it be possible to obtain a similar appealing interaction pattern for some simple MPC functionality that go beyond simply doing key exchange? So here what I would want would be to have n parties who broadcast an encoding of their inputs, and then any pair of parties could securely, locally compute without any further interaction their output from their pairwise output, right? So for some pre-specified function, fi of xiaj and fj of xiaj. And again, if you could do that, then you would have this nice feature of avoiding the n square overhead of having each pair of parties securely compute the function. And in this work, we show that it's possible to do non-interactive secure computation for shares of inner products between vectors held by the parties. So where now the functions fi and fj will form additive shares of the inner product between xi and xj over any field f of your choice. And so this is quite appealing because even if you want to securely compute the inner product in the end, then you don't have to send something whose lengths depend on the vectors xi and aj anymore. You only have to send a single element of f to reconstruct the output. So really it's one round of broadcast, you avoid the n square overhead on the big inputs, and then if you want to reconstruct the output, you just need to send a single field element. So why non-interactive inner products beyond the fact that we can do it? Well, it has many natural applications. It's a simple but super useful function. I'm listing a few here, biometric authentication, pattern matching, and many more. Just as quick example, let's look into what you could do for biometric authentication. So it's known that inner product and Hamming distance, that's basically the same thing, right? You can locally reduce Hamming distance to the computation of an inner product. So that suffices for computing Hamming distance between strings. So you could imagine that you have n clients and m servers, each with their fingerprint stored. And ahead of time, each party will publish an encoding of its fingerprint, right? So the clients will send their own fingerprint and the server will send the fingerprints that are stored. And afterwards, after this single round of publishing and encoding online, any client and server pair can locally compute additive shares of the Hamming distance between the two fingerprints. And afterwards, to authenticate to the server, the client only now has to send a single field element, which is his share of the Hamming distance, from which the server can check whether by reconstructing the Hamming distance is below the threshold or not, and allow for the authentication. So, and that's quite appealing interaction pattern in a setting where you would do like biometric authentication between multiple clients and multiple servers with a minimal interaction pattern and a low communication. So how do we do that? We'll use LPN and LWE. So I'm briefly recalling the assumptions in a somewhat semi-abstract way. So what I call the primal form of LPN and LWE is the following. You have some random matrix, and you have some noisy system of linear equations. And the assumption will be that this noisy system of linear equations is indistinguishable from random. Now, if you set, for example, random matrix to be random over F2, and you set the short secret to be also over F2, and the noise to be sampled from a Bernoulli distribution, meaning that it will have mostly zero entries and a few non-zero entries, then you get the LPN assumption, and you can actually define natural variants of LPN over FP, where everything's over FP, and now the noise is from a Bernoulli distribution over FP. So mostly zeros, but a few random field elements here and there. So that's what I'll call LPN, where the noise is sparse, and you recover LWE, by setting the noise to have small magnitude instead. I'm here giving the example of picking the noise uniformly between some bounds, but of course many other distributions are standard. And I said primal form because you can also consider a dual form for LPN and LWE. In coding theoretic terms, you can view G as a generator matrix of some linear code, and you can multiply it on the left by its parity check matrix, which will cancel the matrix, and then you'll be only left with some kind of random but now compressive matrix, H. And your assumption is that if you multiply this compressive matrix H by a noise, which can be sparse for LPN or short for LWE, then you get something that looks random. And actually, I mean, this is really for the sake of being abstract, because in the case of LWE, generally this will be an information theoretically secure result by the leftover hash lemma. But for LPN, this will be an assumption which is equivalent to LPN. Okay, so our starting point is Alekhnovich key exchange. So what I promise is that we want to do non-interactive key exchange. I mean, we want to do secure computation as easy as non-interactive key exchange. So we start from a non-interactive key exchange, and we look at Alekhnovich, which is a celebrated key exchange from LPN. Here, Alice and Bob will both compute public keys. Bob will do that as some dual LPN sample, and Alice will compute it as some primal LPN sample, using the primal form and the dual form. Okay, so let me show you how correctness works. We just compute the keys K and K prime by just doing the inner product between the public key and the random, the sparse random vectors locally kept by the parties. And to look at correctness, we just open everything. And so if you open everything, what you get is just exactly the key of Alice here, plus some inner product between two sparse vectors. And because this is sparse, you can just view that as a noise term, because this inner product will be 0 with high probability. So roughly, if those two things here have Hamming weight T, and this thing is of size n, then the probability is that this noise term is 1 is roughly T squared over n, which for a sufficiently large n and a sufficiently small T is much smaller than 1. So that's Alekhnovich key exchange. Of course, if you want perfect correctness afterwards, you need to do some reconciliation protocol to amplify the correctness of your output key, but that's a high-level idea. So for security, we invoke the dual LPN assumption, which is equivalent to LPN on Bob's side, and the primal LPN assumption on Alice's side. Proof is standard, I'm skipping it. So now our core question is the following. We know that in order to compute their keys, the parties are already computing an inner product. So could we somehow use the fact that we have already this nice inner product computation that's taking place in Alekhnovich key exchange to embed a more complex functionality inside our key exchange? Could we possibly embed the computation of an inner product inside Alekhnovich key exchange? So let's do a warm-up attempt. Bob can have some vector of input and can just add it to his public key, right? So now if we again open the computation, we open everything, and we have the same thing as before, except that now we have this S times X term here, and I added a minus sign for simplicity. So now if you add Alice and Bob's results, the K terms cancel, you have this noise term, and you have this inner product here. So now K and K prime form noisy additive shares of the inner product between X and S. So this is getting somewhere, but this is still not an inner product because this S here is not something that can be Alice's input, because it has to be truly random if you want to ever invoke the security of LPN. So you can't use S as the input of Alice. So how do we embed Alice's input inside this S? Well, the second idea is just to split H vertically as the vertical concatenation of two matrices H0 and H1. Here, the idea is the following. If you write it this way, then when you open the computation, you can simply use the randomness inside S0 to prove that everything here is secure, is indistinguishable from random, because you will have a term H0 times S0 plus R1, which is a primal form LPN sample. So you can invoke LPN at the cost of losing a factor 2 in the rate of your code here. And now this other part here is a part where you can put something. And this something does not need to be random anymore. So you can decide that it will be the input of Alice. And then when you open the entire computation here, you actually have this S0 term here, but just by padding Bob's input with zeros on the top, then you can cancel the part that involves S0. And so now you just get some noisy additive shares of the inner product between X and Y, so the inputs of Alice and Bob. And so that's for the LPN-based protocol. It's a protocol that gives you non-interactive inner product with some inverse polynomial noise that you can make as small as you want by increasing, for large enough vectors. What about efficiency? Well, communication-wise, if you pick standard parameters, you'll have something like 2 mbits from Bob and 4 mbits from Alice with reasonable parameters. So just exchanging the inputs in the clear will be 2 mbits of communication. Here we're around 6 mbits of communication, so just a factor of 3 overhead over just exchanging the inputs in the clear. And asymptotically, when the size m goes to infinity, it actually suffices to send 1 plus epsilon m bits from each party, and you get nearly optimal communication overhead for this inner product protocol. So that's quite good. And in computation, the cost is of course dominated by the big matrix multiplication. If you take standard variants of LPN, such as LPN using quasi-cyclic codes, it's a standard variant that has been used in a bunch of NIST submissions and many other works, then you get quasi-linear computation in M. And using some slightly more exotic variants of LPN, such as LPN for Drake-Ishai codes, you can actually make it strictly linear in M. So actually a strictly linear computation, which is also a nice feature that's not easy to have with other protocols. And security is exactly as in Alex-Novich key exchange. So that's good, but the protocol has t² over n correctness error. And now if we go back to for example, our example of biometric authentication, if you want to use this protocol in an n-party setting, this correctness error will actually translate to a security error because each time an error occurs, then the server that sees the error will learn a linear equation of the form v times r, where v is a non-vector and r is a noise vector. So the server will, for each error, accumulate one linear equation about the noise. So if many servers were to join their forces, they could accumulate many linear equations about the noise. As long as the number of servers is not too big, so you won't have too many errors overall, then this is still a secure protocol. But the security now only holds under some variant of LPN, which is an LPN with leakage assumption. And this variant can be reduced to a standard LPN assumption, but there is a loss. Alternatively, if you might have a large number of errors, or if you don't want a correctness error, for example, for biometric authentication, maybe you don't want a failure with a 1% probability, then we give two alternatives: either an LWE-based protocol that directly achieves negligible error probability at the cost of more communication, or a way to remove errors via a sublinear preprocessing phase. So I'm going to describe both alternatives. So, let me just state also that, so this preprocessing phase adds more interaction, so it's not fully non-interactive anymore, but it's independent of the inputs. So this interaction only takes place ahead of time. And the amount of communication and computation there is also logarithmic in the input side. So it's a very small amount of communication and computation to do the preprocessing. And then everything is local work in the online non-interactive phase. So it's still quite interesting. So we start again from this Alex-Novich-based inner product protocol, and we convert it to be an LWE-based protocol. So we now have X over ZP. The matrix is over some field ZQ, some ring ZQ, and we scale the X and Y by Q over P. And now when you open up everything, you have the same thing as before, except that this thing here has been scaled by a Q over P. Actually, probably only one of them should have been scaled. Whatever. So now what you have is additive shares of some inner product scaled by some factor plus some noise term. And now this noise term is small in magnitude. because it was computed as the inner product between two noise terms, which are small in magnitude. And we can invoke at this stage a well-known lemma from which is called the rounding lemma, which states that if Q is sufficiently larger than P and the noise magnitude, then the parties can just locally round their noisy shares of the inner product and directly recover additive shares of the inner product without any noise, with overwhelming probability and without using any additional communication. So the bonus is that by doing so, you achieve directly negligible correctness or n leakage while staying fully non-interactive. One run on broadcast, and then you get those additive shares of inner product. The downside is that you get to use a larger communication overhead because you need Q to be sufficiently larger than P and the noise bound. So that's for the LWA-based protocol. As for preprocessing, the key idea is, so back to LPN, the key idea is that we want to use preprocessing to pre-sample the sparse vectors R0 and R1 together with shares of these sparse vectors. So that later when we do the online phase, if you look at the noise term is the inner product between R0 and R1. So if the parties already have additive shares of R0 and R1, by adding these additive shares to their output, they can just cancel this noise and obtain noise-free output. So the only thing they need is, prior to executing the online phase, to obtain via this preprocessing functionality shares of two sparse vectors together with the corresponding sparse vectors. And the cool thing about that is that if you just open what a sparse vector is, this can be done with very low communication. So if you just write a sparse vector as a sum of unit vector and you open everything, you get that this inner product can be written as a big sum of products between coordinates multiplied by something which is 0 or 1, depending on whether the coordinates are at the same position. And this can be securely computed using some simple secure computation using a bunch of equality tests to test equality with the positions and obvious linear evaluation for these products. So overall, you can compute this functionality using only t² times log n communication when the size of the things are proportional to n. So you gain an exponential factor compared to doing things naively. And actually, if you use a variant of LPN, which is also a standard variant of LPN used in many previous work, which is LPN with regular noise, where the noise is broken in blocks with a noisy coordinate in each block, then you can further bring the cost down to t times log n. So you can shave an additional factor of t and get a truly low communication for this preprocessing. And the last thing I wanted to briefly mention is that we also looked at malicious security. And if you break things down the right way, the thing we would need for malicious security would be to have the ability to prove that Alice and Bob correctly generated their public keys. So we want a zero knowledge proof of knowledge of some sparse vectors that satisfy some appropriate linear equation. And we do introduce a new efficient zero knowledge proof of knowledge for such LPN relation, which has communication which is exponentially smaller than the dimension of the LPN instance, because it's only proportional to t times log n, where t is the amount of noise and n is the dimension of the LPN instance. And so, and the key idea here is that we build on recent work on pseudo-random correlation generators, which showed that it's possible to generate with very low communication additive shares of things of the form delta times r, where delta is an element of an extension field and r is some random sparse vector. So we use a protocol like that to share a delta times r protocol using a function secret sharing, which can be done very efficiently using a length doubling to the random generator. So it exists assuming any one-way function. And then we can use just standard secure computation technique like speeds-like technique to view this as a MAC authentication of the noise vector R. So now delta is an information theoretic MAC that authenticates the noise vector, and we can use this MAC to check the correctness of the computation of the public keys, and overall we only used some logarithmic communication. And that's all for my talk. I'll be happy to answer any question.
Are there questions? Okay, I have a quick question. I mean, maybe this is just superficial, but it seems like this non-interactive secure computation paradigm looks a bit like this, like public key PCF type thing. I'm curious if there's any connection there, or if there are other ways to solve the same problem.
Yeah, so public key PCF for the audience will be that everyone will broadcast their public key, and then parties can, so for example, two parties will broadcast their public key, and then the two parties can then locally compute long pseudo-random correlated randomness. So the question can go in two directions. So first, can you use PCFs, public key PCF, to do non-interactive key exchange? That's actually a good question, and I'm not so sure, because you would first need to generate the correlated. So you would use the PCF to generate shares of a random inner product in the first round, and then you will need the second round of interaction to de-randomize these random shares of inner products. And to get really real shares of your input vectors. So that naturally that would be two rounds. Maybe there is a clever way to do it in one round. I'm not sure. What's sure is that the best known construction of public key PCF so far is they are considerably less efficient than what we can do here. The other way is whether we could see this actually as some kind of pseudo-random correlation generator or a PCF. And actually, it doesn't seem so. I tried a bit to see whether I could view it as a way to generate some inner product correlated randomness, but that would not be a good way to generate inner product correlated randomness, because it has communication linear in the size of the vectors, right? So the magic of a PCF is that the communication is almost independent of the size of the correlated randomness that you will share between the parties. If we're using our protocol to generate inner product correlated randomness, the communication will be linear in the size of the vectors, which will be much less appealing than having communication, say, logarithmic in the size of the vector, which is what you will get with PCF. So really what we gain here is not some kind of PCF-like advantage of being sublinear, but it's really the fact that we can directly, without any further interaction, compute an inner product between true inputs. So not an inner product between pseudo-random inputs. So the two are not directly comparable, I would say. Even though, yeah, we used fairly similar ideas and techniques, right? Using LPN inside MPC, using some kind of function secret sharing in the end to handle malicious behavior. It really comes from the same set of techniques and ideas, but the results are somewhat incomparable.
I see. Thanks a lot for the answer and for the talks. Thank the speaker again.
You're welcome.
All right, so now we have our next talk, which is Efficient Adaptively Secure Byzantine Agreement for Long Messages. This is a joint work between Ame Bhangle, Chenda Liu Zhang, Julian Loss, and Karthik Nayak. And Karthik will give the talk.
Are you guys able to hear me?
Yes.
All right. Thank you so much, Yashwant, for the introduction. I'm very happy to be here. So today I'll be talking about our work on communication complexity of Byzantine agreement under adaptive adversaries. This joint work with Amay, Chenda, and Julian. So this work actually follows a rich line of work. So I'll spend the first 30% of my time trying to explain some of these prior ideas, because it's all actually very helpful to know these ideas, because they are used in our work as well. So the problem that we are talking about is Byzantine agreement. And the core idea is for N generals or N parties to agree on some value, agree on a battle plan in this example. So at the end of it, you want all of these Byzantine generals who are surrounding a castle to either attack or to retreat. And you want to do this even if some of these parties or some of these generals can be malicious, or what we call as Byzantine over here. So up to T of them can be Byzantine, and yet you want the rest of them to agree on one of these actions. So said as different properties, you need three properties to hold. The first one is agreement, which says that no two honest generals should disagree. Second is validity, which says that if all generals start off with the same value, let's say all of them want to attack, then you actually output that value, that is, you actually attack. And finally, you want termination, which means that all of these parties eventually take one of these two actions. So Byzantine agreement actually finds applications in modern day blockchains. And with modern day blockchains, you have a large number of parties trying to achieve consensus among them. So one of the key properties that you're looking for is to reduce the amount of communication or the number of messages that are sent by honest parties, or the communication complexity of the entire protocol. Moreover, the parties who speak typically hold some position of power. So if an adaptive adversary can actually corrupt some of these parties, then potentially they can hurt the agreement validity or termination properties of the overall protocol. So what you would want in such protocols is for you to have security under adaptive adversaries. There may be other properties that you're also looking for example, better latency, dynamic availability, and so on and so forth. But for the context of this talk and with respect to this work, we are primarily concerned with these two properties on communication complexity and adaptive adversary. And very coarsely speaking, the goal that we want to achieve is the following. The question we are asking is the following. Can we achieve a protocol, a BA protocol, with low communication complexity while still being secure under an adaptive adversary? Okay, so I'll qualify what I mean by low communication complexity in the next few slides. So as far as communication complexity is concerned, even 40 years ago, there was a very strong statement made by Dolev and Rashek, who said that, any deterministic BA protocol needs honest parties to send at least T-squared messages. Over here, T is the number of Byzantine parties, which typically is of the order of n. So you're expecting communication complexity to be order n squared. And they basically showed that if fewer messages are sent, then there exists some honest party who would receive no messages, and at that point, you would have a safety violation. So does this mean we cannot do better? Turns out we can, and the keyword that we're looking for over here is deterministic. So the bound applies for deterministic protocols. If we use randomization instead, we can actually have a protocol with subquadratic number of messages. So how do we go about doing something like this? The key idea behind achieving a protocol with subquadratic messages is the following. So you basically elect randomly a committee of some size kappa. So let's say your original population is size n, this entire grid of parties where each dot represents a party. You elect a small committee of size kappa, and so if you have a minority corruption in the overall population, even after you elect, except for some slack, you will still have a minority corruption in the overall committee. So if I'm glossing over some of the slack parameters over here, but the minority corruption would translate to the committee as well. So at that point, what you can do is just require these parties in the committee to send messages to everyone else, and they would actually run the agreement protocol for you. And eventually, you'll have only communication between, you'll only have kappa parties sending messages to all n parties, and the overall communication complexity that can then be bounded by n poly kappa. The reason why you have a poly over here is because of the number of rounds of communication, which may be kappa or poly kappa in such protocols. Well, what if you have an adaptive adversary? Note that kappa, which you're thinking of as a security parameter, is typically much smaller than n or much smaller than t. So an adaptive adversary actually has the capability of corrupting the entire committee. How do we address this concern? There was this very, very nice solution by Chen and Mikali in their work on Algorand, where they introduced this property called player replaceability, where they said, instead of having one fixed static committee, let's keep changing this committee after every round. So in a given round R among n parties, you can have a committee of size kappa. These committee members would send messages to everyone, all the parties. And in the next round, the role of these parties would be played by a different set of parties. So the committee would be replaced and hence player replaceable to a different set of parties. So in R+1, you'll have a new committee who would be sending messages to everyone, and you would keep electing newer and newer committees each time. So if you're thinking of this from the perspective of communication complexity, you still have kappa parties sending messages to all n people, so you still have n poly kappa communication. The advantage here, though, is that if the adversary does not know who to corrupt or who is going to speak at any given round before the round starts or before these parties speak, then you can use this to your advantage. So in particular, if parties in round R, the committee members in round R speak and they would send all of these messages, then even if an adversary actually corrupts these parties subsequently, these parties are no longer useful from the adversary standpoint, because in the next round, someone else is going to speak and someone else is going to hold this position of power. And if the adversary does not know who is going to be going to speak in round R+1, then you have security under an active adversary. So what you do need though is, for parties to know that they can self-select themselves and they can prove to the world that they are indeed in the committee. And it turns out that you can actually achieve this using verifiable random functions. Well, now we do have an adaptively secure BA protocol with order n polycapa messages, right? So are we done? Well, it turns out we are not. I still have about 10 minutes to speak in this talk. So what else can go wrong over here? Well, let's think about the size of your input value to begin with. So if we have an L-bit input, so we have n polycapa number of messages, but if we have an L-bit input, the communication complexity trivially would be NL polycapa bits. What happens if this L is, your input size is large, for example, L is omega n squared, or if you're thinking of it in a blockchain sense, your L is your block size, and if it is a large block, 10 megabyte size block, then this multiplicative overhead of n times polycapa can actually be very large. So this is actually addressed in a different line of work called BA extension protocols, where you're trying to split the agreement of the block with the size of the message itself. So you're trying to express Byzantine agreement of a large message as a function of Byzantine agreement for small messages. So the key intuition over here is to break the problem in 2 steps. One, you agree on a kappa bit accumulator value corresponding to one of the inputs. And this typically, using a standard Byzantine agreement protocol, the state of the art, would require kappa n squared communication. And second, you would share the L-bit value separately using erasure coding techniques. So you need to ensure that the L-bit value that you're sharing, corresponds to the kappa bit accumulator value that you're agreeing upon. And these details I'm glossing over here. But the key idea is you want to share this L-bit value efficiently, because L can be large. How do you go about doing that? So note that erasure coding techniques allow you to split a message into smaller chunks in such a way that even if you receive some subset of these chunks, for example, a majority of the chunks or some parameter value that you set, so if you receive sufficiently many chunks, you can reconstruct this message. So a sender can just create sufficiently many chunks, let's say n different shares of these messages, S1 to Sn, each of size order L over n. And these parties in a separate step, in the next step, let's call it a reshare step, can share this message with everyone else. Okay, so at the end of the reshare step, if you're thinking of a party, so far as it receives sufficiently many shares, it can reconstruct this value. And note that, even if some parties are Byzantine and they do not share this value, it is okay, because you do not need all of the shares to reconstruct. So how much communication do we need in such a protocol? So if you're thinking of the distribute phase, the first phase over here, each party is sharing with n different parties a message of size L over n. So the communication is order L, but n different parties can actually be running the distribute phase in parallel. So your communication is Ln bits. In the reshare phase, you're engaging in an all-to-all communication, and the message that you're sharing is of size L over n. So the total communication that you're incurring is Ln. And you're also incurring a kappa n squared communication for agreeing on the accumulator value. So the total communication that you have is Ln plus kappa n squared bits. So note that the first term over here is optimal, because if you're sharing an L-bit message with n different parties, you have to incur a communication of at least Ln. So what you're trying to improve upon is the second term over here. So what have we learned? So here's what the state of the art looks like. So on the one hand, you have subquadratic communication complexity protocols under adaptive adversaries, which require sending Ln polycapa bits. So this is not optimal when L is very large. On the other hand, we have BA extension protocols specifically designed for long messages. right? So the communication complexity is ln plus kappa n squared bits. And when L is very large, actually the kappa n squared actually gets folded into ln. But when L is large but not that large, this is not optimal. So the natural question is, well, can we get the best of both worlds? That is, can we have a BA protocol with the communication complexity of ln poly kappa n bits while still being secure under an adaptive adversary? So the ln term is optimal over here, and the second term over here is the best you can get as of now. So in the next sequence of slides, I'll present a high-level idea of how we actually achieve this. And I think what we learned until now would be very useful in understanding what we're trying to do. So we'll start off with using the BA extension protocol line of work as the baseline way of thinking. So we'll still break down the problem into two steps. The first part, agreeing on kappa bit accumulator value. Now, instead of using a protocol with kappa n squared communication, we can use a Chen-Micali-like protocol, which would require order poly kappa n communication. So that's easy. The concern is, how will you share this L bit value, L bit input with all parties using erasure coding? Observe that with the approach earlier, if we concentrate on, let's say we concentrate on the reshare step. So reshare step requires an all-to-all communication. And even if each of these parties send at least one bit value, then the total communication incurred is omega n squared. And that's too high for us. We want everything to be subquadratic. So in general, if there are n different shares, this is always going to happen, right? So a key learning over here is, the number of shares should be smaller than n. So maybe the number of shares, we split the message into some kappa number of shares, and then ensure that this is, in the reshare phase, it is reshared with sufficiently many parties. In particular, there's at least some honest party who would be resharing it for us. One approach to actually achieving this is to use a kappa-sized committee for resharing each share. Okay, the intuition behind a kappa-sized committee is the following: you want some honest party to reshare a share, and if you elect a kappa-sized committee, hopefully one of these parties is going to be honest, and the reshare will be successful. But while this is one of the approaches that we thought of, it turns out that it actually does not do the job for us. In particular, it actually just does not achieve the communication complexity goal that we sought after. Right? So if you're thinking of kappa parties sending to n messages of size L over kappa, that in itself for each share incurs NL communication. And if you extend it to kappa shares, your communication complexity has blown up by a factor of kappa than what we are looking for. Moreover, it's unclear as to how these committees are formed and how do we distribute these shares with the kappa different committees, because in the sharing phase we do not know who these committee members are. Otherwise, an adaptive adversary would just corrupt all of these committee members. It turns out that we can address both of these questions or challenges in a rather clean fashion. And here's exactly what we do in our approach. We publicly split all of the parties into kappa different buckets, each of size n over kappa. So in this grid over here, the grid represents all of the n parties. Each of these rows represent kappa different buckets, B1 to B kappa, and each bucket has size n over kappa. In the distribute phase, we require share I to be shared with parties in bucket I. Okay, so we're splitting the message into kappa different shares, S1 to S kappa, and each share I, Si, is being shared with all parties in bucket Bi. In the reshare phase, we elect a single, that we elect just one committee of size order kappa, and these committee members would reshare the shares that they have received with everyone else. So in particular, if I'm a party in bucket I, and I'm also in this order kappa sized committee, then I would engage in the reshare step for share Si. Okay, so in the graphic over here, we're representing all of the committee members in squares, honest parties in black squares, and Byzantine parties in dotted red squares. So first, let us convince ourselves that the solution actually gives us better communication complexity. So if you're looking at the distribute phase in particular, then you have a set of parties who are distributing, and this can be bounded to order kappa. So you have order kappa parties sharing L over kappa size shares to N over kappa parties for a given share. And that by itself will incur Ln over kappa bits per share. And if we do this for kappa different shares, it will incur a communication complexity of order Ln bits. So we're good there. In the reshare phase, you have just a single committee of size order kappa, and they are sharing an L over kappa sized message to all N parties. So that would incur a communication complexity of Ln bits. So that's good too. But if you're thinking through this, then you may think of, hey, are there potential concerns over here? In particular, we are electing one committee of size order kappa, which means each bucket I has in expectation only order 1 parties who can reshare I. And there may be, because of the stochasticity, there may be buckets which have no honest parties, and there may be buckets which have only Byzantine members in them. And moreover, if you're thinking of this from the perspective of the adversary can actually perhaps adaptively corrupt parties in different public buckets so that not enough shares are reshared. So if you're thinking of this from the adversary standpoint, observe that for any bucket, if some honest party reshares a message, then all honest parties are satisfied. That's no good for the adversary. But what the adversary is trying to maximize is the total number of buckets where there exist no honest parties who can perform this reshare step. It turns out that we actually address these concerns using a very subtle analysis of a balls and bins analysis using McD-Armits inequality. So the balls and bins analysis essentially says that if you throw C kappa balls, referring to these committee members, into kappa bins in such a way that a minority of them can be corrupt, then our goal is to ensure that there exists some constant C such that you have sufficiently many buckets or members in sufficiently many buckets that are honest, and these members can perform the necessary reshare step. And I invite you to take a look at our work to understand these details. So I must also mention that I'm glossing a lot of other details and other subtleties in the protocol over here. As an example, when you're performing this distribute step, there are these committees that are performing these distribute step, and you want to ensure that the committee, so when you're agreeing upon these messages in a BA protocol, you're agreeing upon one of the inputs, right? So if a committee is sending these messages to everyone, you want to ensure that at least one committee member knows or has access to the message who is to distribute in the first place. So there are subtleties involved with how different sub-protocols are invoked and so on. And again, for those aspects, I invite you to look at our work. So let me conclude by presenting the key result that we achieve. So we say that for any epsilon greater than 0, we show that there exists an adaptively secure BA protocol achieving a communication complexity of NL plus N poly kappa for L bit inputs. And we show it under two different conditions. Under a synchronous network, we can show that we can tolerate a minority corruption. And under an asynchronous network, we can show that we can tolerate an N over 3 corruption. So there's an epsilon slack over here, which we get because of the sampling process. And note that all through the talk, I never spoke about the network condition, synchronous or asynchronous, partly because all of these complexities related to synchrony or asynchrony is kind of absorbed by the underlying BA protocol. And it does not really affect the core content of the core ideas that we are presenting over here. So with that, I'd be happy to take questions, and here's a link to our paper. Thank you.
Thanks for the talk, Karthik. Are there questions? Okay, I have a question. So, I mean, a fairly minor one. I'm curious where the poly K comes from. Is it from your combinatorial analysis, or is it some sort of cryptography that's hiding there?
That's a good question. So under asynchrony, there is cryptography hidden over there. So it basically comes from the underlying BA protocol. The state of the art for asynchrony is the poly is actually kappa to the 6. For synchrony, it comes from so the actual poly is kappa cubed. And I think it comes from the size of the message because we're talking about the number of bits. So if you're sending VRF values, so that's kappa bits, as well as the number of rounds of communication. So it's kappa people sending kappa sized messages. I believe for kappa rounds or not, but I think so those are the two kappas. I don't remember off the top of my head what the third is.
In terms of cryptographic assumptions, you presented your work as like combining two different approaches. Are the assumptions that you use basically just a combination of those two, or is there something new in this?
It kind of comes in from the underlying BA protocol. So in the case of synchrony, you would use whatever setup assumption is required for a VRF. Under asynchrony, I think the best underlying BA protocol requires a lot of other assumptions. So, but everything comes from underneath. We're not introducing anything more.
Yeah. Thanks for the answers and thanks for the talk.
Thank you so much.
And that wraps up this session. Let's thank Karthik again. Okay, now break.
This is bound to happen at some point. And like Mr. Edward Hauck tested positive, and he kindly let us disclose his name. So if you were in close contact with him, please take a rapid test. I mean, you do not need to do anything else right now. I mean, so the person who tests positive is basically confined for 5 days. But if you have contact with him, you do not need to do anything more than what you are doing now. You should take a test today and do a test every 2 days after that, just like we announced during the information email. So if you need any tests, please come to the registration desk and get yourself tested, and kindly inform us if you are positive, of course, and try not to get into contact with more people. Otherwise, I mean, sorry to bring this news, but I mean, it's a commonplace happenstance nowadays. So, we try to continue with the conference. Thanks, everybody. Okay, I mean, there's refreshments outside as usual.
Green light. Okay, great. So welcome everybody to the session on blockchain and cryptocurrency. I'm Joseph Bonneau. I'll be chairing the session. So we have 2 talks in the first slot that will be about half the normal length, and then 2 full-length talks after that. So to start us off, we have a talk on non-interactive Mimblewimble transactions, revisited, and the speaker is Michele Oru. So if you're online, you can take it away.
Hello, hi, can you hear me okay?
Yes, we can hear you.
Okay, hello. So, hi, my name is Michele, and this talk is going to be about Mimblewimble non-interactive transactions. It's a joint work with Georg Fuchsbauer. Mimblewimble is a cryptocurrency initially proposed in 2016 by an anonymous author going by the name of Tom Elvis Jedusor, the name of Voldemort in the French edition of Harry Potter. It is based off 3 main ideas from Gregory Maxwell, initially envisioned for Bitcoin, namely confidential transactions, which add security on the top of Bitcoin by replacing plain text values with homomorphic commitments, coin join, which adds anonymity by allowing to merge the transactions together and shuffle inputs and outputs, so to destroy the link that there is between the two, and the transaction cut-through, which allows for scalability by removing unnecessary information from the blockchain. For this talk, we will use another key idea that was initially envisioned for CryptoNote and is now in use by other cryptocurrencies like Monero, that is stealth addresses. Now, since 2016, a number of cryptocurrencies have started to adopt Mimblewimble, namely Beam, Green, and more recently Mimblewimble Coin and an extension of Litecoin called MWeb. In 2018, together with Georg and Yannick Serron, we published a formal security model called Aggregate Cash System that sort of encapsulates the properties of Mimblewimble, and we proved that this initial protocol described in 2016 is secure under this model. In this work, what we do is we strengthen this model by providing stronger security guarantees and stronger anonymity guarantees. Then we provide a new scheme that satisfies these properties and in addition supports non-interactive transactions. Small variation of our scheme are now in use by Mimblewimble Coin and by Litecoin. We're the first one to provide non-interactive transactions in Mimblewimble and to have it deployed in the real world. Now, the breakthrough idea of Mimblewimble will make it so different from other cryptocurrencies is that it is possible non-interactively to aggregate transactions while preserving its security. For instance, I can take a transaction, transaction 1, another transaction, transaction 2, and mix them together into a new transaction that contains the information from both. And this is the second thing that's very peculiar of Mimblewimble. If an output is being spent as a new input in transaction 2, then these entries in both transactions can be removed once the transaction is merged. So we can really remove information that is not necessary for holding the information. This is the cut-through thing that I was mentioning before. And this is really peculiar. We don't have anything like this in other cryptocurrencies. However, one of the problems with Mimblewimble is that despite its aggregation is non-interactive, both parties, sender and recipient, need to be online when we make a simple transaction. There is no concept of address or wallet to send money to. And this is also very different from other cryptocurrencies, and it's the first problem that we tackle. The second problem is that some metadata information in transactions that we call the excess, that essentially says the transaction is balanced. The sum of the outputs minus the sum of the inputs. Well, when we merge transactions together, this excess holds information about the composing transactions and it leaks information about them. This is the second problem that we tackle in terms of adding privacy on the top of Mimblewimble. More specifically, we give 2 new security definitions. One of them is transaction binding, which covers something that was not really thought of in the first model in our work of Asiacrypt 2019. What happens to a transaction before it goes to the ledger? With transaction binding, we say essentially that once a transaction is broadcasted, only the intended recipient can spend an output that was honestly generated. This protects, for example, against malicious miners that might try to tamper with transactions before they reach the ledger and are in the mempools. Or for instance, against adversaries that might change their mind about the transaction that they sent, and they might want to spend the output before the honest recipient will. Additionally, we introduced this new notion of transaction privacy, where essentially we say that from a transaction, you cannot learn anything about the transaction amount, so the values are hidden, the recipient addresses, or which inputs and outputs belong to the same constituent transaction once aggregated with another transaction. In order to do so, we use two key ideas. One of them is stealth addresses, and the second one is transaction offsets. Stealth addresses are key for non-interactive transactions. They work roughly as follows. When Alice wants to send some money to Bob, it will use the public key of Bob to derive a new one-time public key. An observer cannot learn this cannot link this one-time public key to the public key of Bob. Now, Bob, on the other hand, has associated to the public key a secret key and a view key. From the view key, it is possible to regenerate the one-time public key. So Bob just has to scan the blockchain in order to find outputs that are destinated to him using the view key. And using the secret key, it is possible to generate a one-time secret key that will be able to spend the output associated to the one-time public key. Now, transaction offset instead add privacy to this feature of Mimblewimble called non-interactive coin join, this aggregation. The idea is simply to add some random offset that I'm displaying here in yellow. And when we aggregate transaction, we will simply re-randomize this offset in such a way that no information about the component transaction is leaked. This feature was already available in Green for a few years, but we provide the first study that guarantees its security properties in Mimblewimble. The resulting transactions in our new scheme look like the following, pretty much. We have these one-time public keys that are introduced by stealth addresses, and we have signatures authorizing the spending under these public keys. Now, these signatures do not link input and output together as one would normally imagine in Bitcoin. Instead, we opt for something very similar to the excess equations that we saw before, and we introduce a new excess that depends on these public keys called stealth excess. Now, this stealth excess slightly weakens, unfortunately, another property of Mimblewimble called the cut-through. We, however, discuss in the paper trade-offs that can be made so that some sort of cut-through can still be achieved. We also have the offset that, just as we saw, provide privacy. And finally, as normal in Bitcoin, in Bitcoin's confidential transaction and in vanilla Mimblewimble, we don't have plaintext values that credit public key. Instead, we have commitments to those values together with range proofs that attest that these values are small and they don't wrap around the integer arithmetic. To conclude, in this work, we strengthen notions of security and anonymity that we provided in Asiacrypt 2019, and we provide a new scheme that satisfies those and that supports non-interactive transactions. Our scheme is now in use both by Mimblewimble Coin and by Litecoin. Thank you.
Okay, thanks. Do we have any questions from the audience? Okay, looks like we don't have any questions, so we'll move to the next speaker, who's going to be talking about universally composable non-interactive aggregate cache. And that speaker is Yan Shui Jia, who hopefully is online. You can.
Yeah, I'm online.
Okay, great. We can hear you, so you can take it away.
Okay. Okay. And can you see my slides?
Yes, we can see your slides.
Okay. Oh, okay. I will start. Okay. Hello everyone. I'm Yan Xuejia from Shanghai Jiao Tong University, and I will present our work, a universally composable non-interactive aggregate cache system. This is a joint work with Shi Fengsun, Hongsheng Zhou, and Da Wu. I'm breaking my presentation down into 4 parts, and because Michele has introduced the Mimble-Wimble, so here I just mentioned something related to our paper. And I will summarize our contributions and give more details about our scheme and the ideal functionality. Oh, I will skip this part, okay. I will mention that the Mimble has a beautiful feature called cash-through, and which means that if this coin is by this coin, then the 2 coins can be deleted in the aggregate transaction, and which is called cash-through, and it can save the on-chain storage cost. However, the Mimble-Wimble has a drawback, and it might impact the usage in practice. More specifically, the sender and the receiver must interact to generate a transaction, which means that the 2 parties have to be online at the same time. This is because in Mimble-Wimble, in each transaction, there must be a signature under the XSE. However, each party holds a part of the signing key. So our work aims to avoid the drawback of Mimble-Wimble. So we design a non-interactive aggregate cache system. We call it NIACS for short. And we formalize an ideal functionality for NIACS. And finally, we prove that our protocol can easily realize our ideal functionality in a hybrid model. In the original Mimble-Wimble, the essential reason why each party holds a part of the signing key is the sender cannot know the randomness of the output commitments because the randomness act as the spanning key of the output points. And the excise E computed from the input commitments and output commitments. And the signature has 2 functions. The first is to prove that the transaction is balanced, and the second is to prove that the sender knows the spanning keys of the input coins. So the core idea of our work is to add the notion of address to achieve non-interaction, such that the secret key of address acts as the spanning key, and the sender can know the randomness of the output points. So the sender can generate the signature under excise alone, and this signature just used to prove that the transaction is balanced, and the signature under the address is used to prove that the sender knows the spanning key of the input point. Given the initial idea of adding address to achieve non-interaction, there are also some challenges. First, how to bind a commitment and an address. Second, how to bind the proof of the ownership of the input coins with the transaction. And how to non-interactively transfer the private information of the output coins to the receiver. Finally, how to maintain the important feature cash-through. Let's first see how to bind a commitment and an address. Because the holder of the secret key of the address can span the coin, so we must guarantee that for each commitment, its address cannot be changed by others. In the privacy-preserving cryptocurrencies, the range proof is necessary. So in our work, we modify the range proof into a signature of knowledge. The signature of knowledge is a generalized notion of signature, where the verification key is a statement and the signing key is the witness. In our work, we use the commitment as the verification key, and the randomness and value as the signing key. And the sender can use the signing key to sign on the address. In other words, the address is the message. So we can generate the signature of knowledge to bind the commitment and the address. The sender needs to prove that he knows the spending key of each input coin. However, if the sender just generates these proofs, then others may steal these proofs and use them in other transactions. So we need to bind the proofs and the transaction. And our first attempt is to let the sender to sign the whole transaction use these spending keys. However, if the transaction is signed as a whole, then it cannot be aggregated with other transactions to break the linkability, because others can figure out that there is an individual transaction. So we want to let the sender to sign an abstract of the transaction, and we found that the exercise is computed from the input commitments and output commitments. So we can regard the exercise as the abstract of the transaction. So we let the sender sign the exercise using these spending keys. However, if in this way, others can find that these input coins belong to the same transaction. Finally, we split the exercise into n parts, where n is the number of input coins, and let the sender sign each part by using a spending key. Then because the sender generates the transaction alone, and the receiver needs to obtain the private information so that the receiver can spend these output coins later. More specifically, the receiver needs to obtain the randomness and value and the spending key. As for the spending key, we directly use the use address such that the receiver can use the permanent secret key to recover the one-time spending key. As for the randomness and value, we propose a new variant of L gamma. The ciphertext includes two parts, and the second part is the Peterson commitment, and the first part, and the receiver can use the first part and the description key to obtain the G2R and then obtain the randomness alpha. And given the commitment and the alpha, the receiver can obtain the H2V. And once the message space is small enough, the receiver can recover the value V from H2V. Okay, finally, let's see how to still spot the cut-through. In the original Mimblewimble, for example, we assume that E1 is the transaction 1's exercise, and E2 is the exercise of transaction 2. And we assume that C1 hat is equal to C3. Then if the transaction 1 and transaction 2 are aggregated into a big aggregate transaction, then the exercise of the aggregate transaction is E1 times E2. Then the C1 hat and C3 can be cut. Then the output coins can be deleted from the aggregate transaction, so which is called cut-through. In our work, the exercise is computed in the same way, so our scheme still supports the cut-through. Moreover, we define an ideal functionality for NIACS to capture its security. Unlike the original ledger, in our NIACS functionality, this functionality submits the aggregate transaction to the ledger, not the individual transaction. And our ideal functionality can capture the security properties proposed before, and also our ideal functionality can additionally capture the unlinkability because we define the coin ID. The coin ID is pseudo-random. So in an aggregate transaction, there are just some pseudo-random coin identifiers. which hides the values and the relevant parties. So others cannot figure out which coins belong to the same transaction, so which means the unlinkability. And we can use the ideal functionality to analyze the security of NIACS in complex execution environment, which is important in blockchain. That's all. Thank you.
Okay, I guess we don't have a very inquisitive crowd today. So thanks again for the talk. And our next speaker is actually in person. Yeah, you're next, right? Oh, okay. Sorry. Yeah, sorry. I thought you were third. Okay, indeed in person. So, yeah, all good. Okay. Well, our next speaker is Soren Thompson.
All right, so hi, my name is Søren Thomsen, and I'm going to present the next work, which is Practical Provably Secure Flooding for Blockchains. This is joint work with Chenda Liu Zhang, Christian Matt, Uli Maurer, and Guillermo Rito. So to motivate this work, I would like to use blockchain as an example. And for the purpose of this talk, a blockchain protocol is just a protocol where a group of parties interact in order to build a total order. However, such blockchain protocols does not guarantee this total order under all circumstances. It only guarantees that the order is built when each party owns some resource and a majority of these resources. And here you can think of resources as being either computing power or stake. And it only works when the majority of these resources actually behaves honestly. However, there's one often overlooked assumption for blockchain protocols. That is, they run on top of a flooding network. So, for them to function correctly, we need both the majority of stake or resources assumption and that such flooding network actually exists. So, let's have a look at what this flooding protocol actually is. So, a flooding protocol, or in this case a delta flooding protocol, is a very simple protocol which ensures that any party is allowed to input a message and that this message will be spread out to all other parties within delta time. And this is what is assumed to prove the security of blockchains in a wide range of work. So such flooding networks are in practice implemented by a very simple procedure where each party, now for example P1, if P1 wishes to forward the message, he will select a subset of the parties as his neighbors, and then forward the message only to those parties. Then again, those parties will forward the message to a random chosen neighborhood of their choice until all parties have received the message. This works all well and good as long as all parties remain honest. However, if a lot of the parties are corrupted, then either P1 has to send to a lot of parties, or otherwise there will be some parties that does not receive the message. Okay, so looking back to our blockchain example from before, this means that when we actually wish to realize such flooding network, then we need to rely on some assumption on the number of parties being honest. And that is, to build the total order, you will need to rely on both assumptions. Really would be better if you could just do with one assumption, namely the majority of honest resources. So in this work, we asked the question, can efficient flooding be realized assuming a constant fraction of honest resources or weight? And give an affirmative answer, yes we can. In a bit more detail, our contributions are, we present a new flooding protocol called weighted fan-out flooding, and we will abbreviate this WFF. This is secure, assuming any constant fraction of resources being honest. It has a logarithmic diameter for n parties, and it has a message complexity that is comparable to state-of-the-art. Furthermore, we do extensive simulations of this new flooding protocol, which confirms that this in fact is practical. All right, so the model we use for our results is where we have a static set of parties, where each party is assigned some positive number of weight. Now, as before, an adversary is allowed to corrupt a subset of the parties. But the adversary will only, but our assumption is that the adversary is only able to corrupt corrupt parties such that a majority of the resources is left honest. And this very formally, right, there exists some gamma such that this fraction of resources owned by honest party is larger than the total fraction of total number of resources. And we note that this is implied by the standard proof of stake assumption. All right. So now let's try to develop a protocol that actually realizes flooding in this setting. So as a warm-up, we will do a very simple but inefficient protocol. And we will use the idea, well, how about we could take some existing flooding protocol and actually try to amend this to make parties behave proportionate to their weight. And as an existing flooding protocol, we chose the protocol by Matt Nelson and Thompson from 2022, where each party forward to each other party with a probability rho. And as we know, this will ensure a logarithmic diameter for reasonable parameters, or a reasonable parameter rho. So we can depict this as this thing, right? So P1 forwards the message to P2 with probability rho. Now to accommodate this to the weighted setting, what we could do is to let each party behave proportionally, meaning that P1 will instantiate 4 sub-parties, 1 for each discrete unit of weight P1 owns, and P2 will do the same thing. And now when P1 wishes to decide whether or not to forward a message to P2, what P1 can do is to let each party behave as a party in the existing protocol. So that is, each sub-party will flip a coin for each sub-party of P2. Now the total probability to forward will be 1 minus 1 minus rho to the power of the weight of the two parties multiplied together. However, this has a few unfortunate properties. So if we double the total amount of weight in the system, then this probability will increase by quite a bit. So what we intuitively want is that even though that we double the amount of weight, this probability shouldn't change. So our protocol should be invariant to scaling of weights. Okay, so let's try to develop this idea a bit. So instead of letting each party directly emulate a number of nodes proportional to their weight, what we'll do is to introduce a function which we'll call the emulation function to decide how many parties each node should emulate. So if this was the picture before, what we now have is that P1 will use this emulation function to decide how many nodes he should emulate, and he will forward only to flip a coin to forward for each of P2's emulated nodes as well. The total probability will be something like this. Okay, so let's think about what property we would like from such a emulation function if it should induce a practical protocol. So as we established before, we need that the emulation function should be invariant to scaling of weights. We want that all parties should emulate at least one node, and that is because we want each party to inherit the delivery guarantees from the original protocol. And then if you have a closer look at this Matt Nielsen-Thompson 2022 paper, then we note that the message complexity is linear in the number of nodes. In this case, it will be in the number of emulated nodes. So we also want that the number of emulated nodes are low in order to keep the message complexity low. And then this message complexity is also linear in the fraction of honest weight, sorry, in the inverse of the fraction of the honest weight. So we kind of want that fraction of honestly emulated nodes should also be high. Okay, so what candidates do we have? Well, we had a look at this, just assigning each party to emulate the number of weight they had before. This was, however, not invariant to scaling of weight. So to fix this, what we could do is to let each party emulate just a fraction of weight owned by a party P. So this is naturally invariant to scaling of weight. If we double the weight, the fraction remains the same. However, it doesn't fulfill the requirement that each party should emulate at least one node. So what could we do? Well, we could take the ceiling. It's still invariant to scaling of weight. And any party now emulates at least one node. Furthermore, the number of emulated nodes are reasonably low. In fact, this is just n. However, it fails to comply with the last requirement. The fraction of honestly emulated nodes are not high. In fact, this is similar to just let each party emulate one node. So that doesn't work either, right? Then we're back to the non-weighted setting. Okay, so as a final thing, we could try to take the ceiling of the fraction of stake owned by party P, now multiply this by the number of parties. So what do we get? Well, it's still invariant to scaling of weight. All parties emulate at least one node. The number of nodes is reasonably low. This is less than 2n. But now the fraction of honestly emulated nodes are now less than, if gamma here is the fraction of honest weight, then the fraction of honestly emulated nodes will now be larger than or equal to gamma divided by 2. So this actually constitutes a fairly good protocol. However, there is a few issues remaining. First of all, to select the neighbors, well, P1 needs to flip a coin that comes out heads with this probability for each of his neighbors. This is kind of impractical, as we have heard before, that randomness is a scarce resource. Furthermore, it's not very practical that there's an unknown number of neighbors for each message. So in order to remedy this, we introduced this weighted fan-out flooding, which uses some of the same intuition as we had before. Again, we use an emulation function for each party, which will use the same one which we just gained intuition for. But then we will let each party select a fixed number of neighbors. This will be some parameter of our protocol k times the number of nodes this party should emulate. Now, neighbors of a party are selected by weighted sampling without replacement, where each party again is weighted by the emulation function. Let's just have a quick look at how this works. So if P1 wishes to send a message, well, then he'll decide his neighborhood by first calculating how many nodes each party should emulate. So in this case, P1 emulates 2 nodes, P2 emulates 5 nodes, and so on and so forth. And now, at random, let's just do it for lowercase k being equal to 1. Well, then P1 initially selects one node, one sub-node party at random, and then chooses to send the message to the party emulating this sub-party. Then the next one is selected by disregarding those, the nodes emulated by the party that already has been selected as a neighbor, and then selecting a new node at random. Then the final neighborhood will be just those parties. Okay, so the main result of our theorem, of our paper, is that if we set this parameter of the protocol k to be logarithmic in the number of neighbors plus some security parameter, and we divide by the fraction of weight, then we actually achieve a delta flooding protocol for a delivery time delta that is logarithmic in the number of parties. And this has a message complexity, which is just this lowercase k times n. And each party will have roughly k times this emulation function, number of emulated nodes as their neighbors. Okay, so in order to test the practicality of our protocol, what we did was to implement it, and then among 1,000 nodes, simulate how often all parties had the message delivered for an increasing parameter lowercase k, and then counted how many neighbors each party on average had to choose, And this is what is depicted here. And additionally, we had an adversary that corrupted half of the weight, and the weight was assigned to an exponential distribution where the heaviest party weighted a million times the weight of the lowest party. Then we varied the corruption strategy by the adversary to either be random corruptions, corrupt the heaviest parties first, or corrupt the light parties first. And what we see here is that independently of all these parameters, then if each party on average sends to roughly 45 parties, then the protocol succeeds with roughly 100% success rate. This number may seem, I don't know if it says anything to you, but what we could do is to compare this with existing protocols, which we will refer to as weight-oblivious protocols. So we did the same experiment. We had an exponential distribution, which now had a parameter where the parameter refers to how the amount of time the heaviest party, the weight of the heaviest party is compared to the lightest party. And what we see that if we actually just have a constant distribution of weight corresponding to the non-weighted setting, well, then our protocol performs exactly equal to the original weight-oblivious flooding protocol where each party simply sends to k neighbors. But as the weight distribution gets more and more skewed, well, then the success probability of the weight-oblivious flooding protocol drops dramatically. However, our weighted fan-out flooding protocol remains secure for these 45 parties that are sent to on average. All right, so in conclusion, we present the first provably secure flooding protocol in the weighted setting and demonstrate its practicality using probabilistic simulations. And there are many more details and additional results. Among those are necessity of increasing neighborhood for heavy parties, necessity of logarithmic numbered neighborhood for fan-out flooding. We show how to deliver the message to parties even with zero weight, and we do additional simulations. Thank you for your attention.
We're running ahead of schedule, so somebody should ask a question and get us back on track. Well, maybe I'll ask actually, like, how does this, I mean, have you thought about kind of incentives and economic analysis of this and people potentially like manipulating their weight or not reporting it truthfully?
Right. So you're right. This protocol depends on the weights being accurate, and therefore we kind of need to realize this somehow from an existing assumption. So I think that it's fairly easy to see how to do this from a proof of stake assumption, where all parties already know how many coins each party owns. But this is more difficult for, say, a proof of computational power, or proof of work, where you would have to estimate this in some reliable manner, as otherwise you will not guarantee security of the protocol.
Thanks. Okay, well, let's thank Soren again. Yeah, we'll move on to our last talk. Our last talk is snacks with Hamza Absallah, who hopefully is ready to share. Okay,
see
great.
My screen?
Yeah, if you're ready, Hamza, we can see your slides and hear you. So please go on.
Do you actually also see me? I don't.
Yes, we see you and your slides.
Okay,
You looks great.
Okay, great. Okay, so welcome everybody to my talk about snacks. This work is jointly done with Georg Fox-Power, Vita Gaggi, and Karin Klein. I'll start off by talking about light client blockchain bootstrapping as a problem, and then define snacks, succinct and interactive arguments of chain knowledge, construct snacks generically from proofs of sequential work schemes, and then get back to bootstrapping and show you how to realize them generically from snacks. In light client blockchain protocols, you have full node provers that store the entirety of the blockchain, and you have light client verifiers that have minimal information about the blockchain, optimally the genesis block. The protocol, we would like it to satisfy a few properties. We would like the verifier to have sublinear effort, the communication to be sublinear, and the protocol non-interactive. If additionally the protocol achieves sublinear prover and no set of assumptions, that's a plus, and our protocol achieves all of these properties. So informally, in a bootstrapping protocol, the verifier depicted here on the right side, who has the genesis block B0 of the blockchain in question, potentially after reading a bunch of proofs from different provers, its goal is to output phi I, a commitment to the stable prefix of the blockchain. Why this is interesting? Well, this verifier can become a full miner itself if it wishes to. Okay, assume that it went asleep for some time and then now it catches up with the state of the blockchain and can continue mining. But additionally, assume that you have a bootstrap verifier and say for different blockchains, so you have a proof of work Bitcoin blockchain and a proof of space Chia blockchain, and we have a bootstrap verifier that has commitments to these blockchains, then any prover can prove statements about, say, the transactions in the ith Bitcoin block and the jth Chia block by opening commitments to these blocks and then carrying out the proofs. So the idea of having a commitment to a blockchain is a very powerful tool. So this problem has a few solutions. So there's the generic snark solution, and there is the non-interactive proofs of work, NIPA-POWs, and there's a fly client. Some limitations of these works exist. Some of them require a set of assumptions. Some of them have limited applicability, say apply for proof of work blockchains, but say don't, or we don't know how to do them for proof of space blockchains. Some of them have limited usefulness, or even the notion of commitment doesn't come up in the construction. But more interestingly, for NIPA-POWs and fly client, they work in a non-standard model where you assume that you're interacting with multiple provers, one of them is honest. If you are outside of this model, there are no provable guarantees. And that's a limitation. In this work, we define a classical proof system that underlies some light client blockchain applications, in particular bootstrapping. We construct snacks from graph labeling proof of sequential work schemes. And along the way, we give a new construction and generalize and unify existing ones. And we then show how these snacks as a tool can be used to realize bootstrapping. The advantage of this work is that you have a classical soundness guarantees, in the sense that if the verifier is reading a malicious proof, then it has a meaningful, measurable guarantees that I will talk about in a bit. This is in contrast to the NIPA-POW and fly client protocols. Our protocol is simple, generic, and modular, and it allows for exchange of ideas from the area of proof of sequential work schemes and light client blockchains. So in one slide, pictorially, how do we do this? So we assume that we start with a blockchain depicted here. It has the typical chain that you expect and a few extra edges. And if we start with the graph of any graph labeling proof of sequential work scheme, here's an example, then what we show is that we build an augmented blockchain. We started from the chain on top, and we get the chain on the bottom, which is the union of these two graphs, essentially. And then we show how to build an augmented mining that labels the graph. So the mining for this talk will be generating the labels of the nodes of the graph. Then we define some witness relation, and then we define a proof system over this graph. And the proof system will be very similar to the underlying proof of sequential work proof system. So the idea is that we absorb the blockchain data into the computation of the proof of sequential work scheme, such that the sequentiality guarantees of the proof of sequential work scheme translate into sequentiality guarantees on the blockchain. So this is the main general idea. So with this slide in mind, let's dig into it. So before defining proofs of sequential work schemes, we need this notion of graph labeling. So you have a graph like this, and to label the graph, we generally use a hash function modeled as a random oracle, depicted here as tau. And the label of a vertex is the label of the is the hash of the labels of its parents concatenated with its index. So, for example, the label of 5 will be the hash of 5 concatenated with the labels of its parents, namely the label of 4 and the label of 1. Very standard notation. So graph labeling proof of sequential work schemes were introduced by Mahmoud et al. It's an interactive protocol between a prover and verifier, where completeness says that an honest prover that makes n sequential queries to its oracle makes the verifier accept with probability 1. Succinctness is what you expect. Proofs are Boolean logarithmic and they can be verified in Boolean logarithmic time. The interesting property is soundness. Alpha epsilon soundness says even a massively parallel malicious prover that makes an alpha fraction sequential queries for alpha between 0 and 1, then it will make the verifier fail with a very large probability, 1 minus epsilon. So that says that parallelism does not help a malicious prover in convincing the verifier unless it actually did the sequential work that it was supposed to do. Okay, so this is kind of intuitively what the notion of sequentiality is. A simple proof of sequential work scheme that we give in this work, and it's a simple variation on existing scheme and on an existing scheme, is this, where the scheme is parameterized by a family of graphs that look like this, a skipless graph. The prover, upon receiving chi from the verifier, will use it to solve its hash function and build, and then here will be tau, and then compute the labels of the graph in topological order using this salted hash function, and then sends the label of the sink to the verifier, which will serve as a position binding commitment to the labels of the graph. And then these two parties run a challenge response phase for t many times. In each round, say here, for example, the verifier sends, okay, give me something related to the index 5. What the prover does in this particular proof of sequential work scheme is that it locates the shortest path that goes from the source to the sink and passing through the challenge 5 here. And then it gives the verifier the labels of this path and its parents. Okay. In particular, we say it opens this path. And the verifier will check the consistency of the labels of this path. And this path, although in this picture it looks like the prover is giving the entirety of the graph, it's actually still Boolean logarithmic. And notice that the shortest path is logarithmic, and the in degree of the graph is logarithmic. So all is good, but this is just a small example. Okay, so succinctness is achieved, and soundness is actually also achieved with. I would not bother reading the whole theorem statement, but we'll highlight epsilon in the previous slide, the probability of failure. It depends on alpha and t, as expected, which is alpha to the power of t plus some negligible term that amounts to finding collisions in the hash function, the random oracle here, in q many queries in total. Okay, so this is a simple proof of sequential work scheme that I will carry on with me for the rest of the talk. So we're coming close to defining snacks and then materializing them. We need one more notion. For that, we use the notion of weighted graphs, where a graph, say just an example like this, each node has a weight, and the sum of the weights of all the nodes is 1. Okay. And because we intended to absorb the blockchain data into the computation of the proof sequential work scheme, now the labeling, the graph labeling, we need to adapt it a bit, and we absorb the blue data here, xi's, which will be blockchain data that I will show in a bit, into the computation of the label of the vertex in a very simple way. But now, the verifier in the previous slide, the proof sequential work scheme, was verifying the consistency of the opened path. But now we have an arbitrary data that we need to be able to verify its consistency. And, and we assume that this arbitrary blue data can be verified for validity by a relation arp-psi. Arp-psi is a relation that comes with a blockchain. Say you have the initial blockchain is a proof of work blockchain, and to verify the validity of the ith block or the ith label, you have a relation that tells you, okay, given the label of the ith block and the label of the parent blocks, you should be able to verify whether this block is valid or not. Say if it's a proof of work, you verify that the proof of work is valid. Okay, very simple. And with the notion of valid labels, you can define a valid path. A valid path, we call it alpha R valid if it's valid with respect to this relation R and it has weight alpha. Small details for the definition, and now we're ready to define snacks. And the way I'm building it up is that you see that a snack is essentially a generalization of a proof of sequential work scheme. It is as we define it non-interactively, so there's a proof bias in from the proof to the verifier, and we define it with respect to this witness relation, where the statement is a tuple phi n, where phi is a position binding commitment to a chain of length n, and the witness is an alpha R valid path in this graph, and an opening of the labels on this path with respect to the commitment phi. Okay, so this is our witness relation. And completeness says what is that an honest prover that has the labels of the entirety of the blockchain for alpha is equal to 1, the path is full weight, will manage to convince the verifier. Of course, you can think of it as the label blockchain or any graph. So the blockchain is just an example of it. Succinctness is what we expect. Soundness is also what we expect, but here we would like to define knowledge soundness. Alpha epsilon knowledge soundness is for every convincing prover, we can extract a path in this relation that is alpha R valid with very high probability 1 minus epsilon. Okay, so here I'm giving an example again. The blue thing is something that you can extract. And I would highlight the extractability guarantees are important because this witness relation is polynomial time relation. So ordinary soundness would be vacuous. We need to be able to extract from any convincing prover. Okay. So now coming back to the construction, so we started, remember, with a blockchain that was simple, and now we enriched it, gave it this rich structure inherited from the proof of sequential work scheme. This is an example, and I wanted to show you how to do the labeling or the augmented mining. So assume you're a miner and you want to mine the fifth block, given the blockchain so far, and more important, the layers of the blockchain and the data, the transactions that you need to include in your block. So you want to compute G5 and H5. G will have two components, L, which will be a hash of the parents, and phi will be the commitment to the blockchain so far, including this hash. Okay, easy computation. And then you need to do what the original blockchain wanted you to do, generate a publicly verifiable proof. Say in a proof of work, you need to generate a proof of work that is valid. In a proof of space, you need to generate a proof of space that is valid, and so on. And this is by, and this is valid with respect to arp-psi. Once you have that, you have your label, and you propose your new block. Okay. So I would like to say that in the efficient proof of sequential work schemes that you could potentially use to realize the snack, namely this construction that I show, or the CP construction, you have the LI, the hash of the parents, serve as the commitment. So you don't really need the extra commitment part. So this treatment is just generic, but in these particular schemes, you don't need an extra phi I. So the cost of this augmentation is an extra hash value in each block. If at the cost of this enrichment of the structure of the blockchain and an additional, say, 256 bits in each block, you will have a rich structure that allows you to build proofs of chain knowledge. So the prover and verifier, as said, they're almost identical to the underlying proof of sequential work scheme, prover and verifier, except for a small change that one has to be a bit careful with these extra edges that kind of become part of the proof of sequential work scheme graph, and they come from the blockchain. They may allow for shortcuts and to violate soundness, so one has to treat them carefully, and this can be done easily and simply. This is the only small change between the snack prover verifier system and its underlying proof of sequential work scheme. But this can be done. And what we prove is that if the underlying proof of sequential work scheme is alpha epsilon knowledge sound, then so is the snack. And this is not by accident, it's by design. And the security of our scheme is in the random oracle model. We apply the fiat Shamir to the interactive proof of sequential work protocol. And anyway, the graph labeling proof of sequential work schemes are also in the random oracle, so there's no extra assumptions there. So this is the construction of the snack and how we augment the blockchain. And now we go back to essentially my last two slides about how to solve bootstrapping from this abstract object. So this object is interesting on its own, and you can potentially use it in other applications. Here is one motivating application that we wanted to use. So here's where we started, and now if you have, I'll show you how an honest prover generates a proof in the bootstrapping protocol. So here the honest guy is the green guy, the green bird. So what it does, it looks at, it has a blockchain of some length, n and I. It looks at the L suffix of the blockchain. L is a fixed number that I will talk about in a bit. And it sends these L blocks in the clear. This is SI. And for the rest of the blockchain, it generates a snack proof. Okay, so this is, you know, a blockchain that is labeled like I showed before, and you can generate a snack proof for it generically. And that will be the honest proof. And what does the verifier get from this proof? Completeness says if at least one of these provers is honest, then it will end up, the verifier will end up outputting a commitment to the honest L common prefix of the blockchain. And L is a number bigger than, a fixed number bigger than K, kappa, where kappa is the K common prefix property of the underlying blockchain, which we assume that it's satisfied. How large is this L and what kind of number is that? So this comes from an assumption that we make on the adversary and its computational power. This assumption was initially made by the Fly Client protocol. It's called the CL assumption. We refine it and adapt it to our work. And it essentially says that an adversary cannot create a fork of length L such that a C fraction of the fork is valid. So you can see if C is 1, for example, this collapses to the L common prefix violation assumption. But the generality of this, the range of the parameters for which this assumption holds is not really that well understood, and it will be interesting to analyze. But with this assumption and the guarantees that we get from the proof of sequential work scheme, we get to the crux of the soundness guarantees that we have here, which, as I promised, they are classical soundness guarantees, and their knowledge in terms of alpha epsilon knowledge soundness. What it says is that assume that all these provers that are controlled by a malicious prover, that is respecting the CL assumption, then from any verifying proof, we can extract a path that is of weight alpha n here. And this alpha depends, I'm just showing the formula without needing to discussing it here. It depends on n, the length of the blockchain, depends on the C and L from the CL assumption. We can extract such a path except with probability epsilon. And of course, the closer alpha to 1, the better. You can, if somebody's claiming that they know the entirety of blockchain, then you can extract the entirety of the blockchain. But you can probably afford extracting 95% or whatever the number is that you need to plug in it here. And the larger alpha is, the stronger the CL assumption should become. So these guarantees are essentially almost best possible. They're extractability guarantees, except that alpha is not 1, but it's close to 1. And this is actually what allows us to have a much more efficient construction than SNARKs. The provers are sublinear. They do just lookup table. And finally, I would like to say that the guarantees of the SNAK system are extraction guarantees, correct? But what do they say? How meaningful they are in different blockchains? If the blockchain is moderately hard to mine, then these guarantees are meaningful. Say in a proof of work blockchain, we're generating a sequence of blocks, a long sequence of blocks that are computed sequentially and have valid proof of work is a heavy computation, and it's a heavy price to pay if you want to cheat a verifier. And this is so this is kind of has value and meaning. But if your blockchain is proof of stake, then it's not clear if the SNAK system that we develop, although it applies for it, the construction does not care about the underlying blockchain, what it is, as long as it has a witness relation that verifies validity in polynomial time. It applies, but the guarantees, I don't see that they have any meaningful guarantees for, say, proof of stake blockchain. So with this, I thank you very much, and I will be happy to take some questions. Thank you.
Okay, thanks a lot. And yeah, we have time for questions. Okay. Looks like, again, there's no questions from the floor. So that was our last speaker. So we will conclude there. The next session starts in about 10 minutes. So it's, I guess, not a full break. And if you, let's see, so if you stay here, there's a session on homomorphic encryption, and proofs and snarks is in the other ballroom. Thanks a lot.
So what do I have to do? So of course we have to check if they are if they are here. Aida, yeah, verschieden. Aida. Yeah. Okay. Good. Can we check her? Yeah. She was moved. Okay. Thank you for the she doesn't reply. But they have a pretty cool video.
Oh, they have a
in
pretty-
yeah, in case it will come on. We can first listen.
Yeah.
And in the end, it will.
Okay.
And therefore, only. Yes.
From her. From online, no?
Online.
Online.
Only one person, and his slides already. Already here. And I will. I think. If you here, I will complete the.
Okay. So I don't have to do anything with it, right?
No.
Okay.
Yes. No.
Hey, can you hear me?
Yes.
Okay. I'm not sure, like, to present. Do I just share my screen?
You can share
Alright,
your
okay.
screen and present later, maybe in 5 minutes.
Okay.
Okay, thank you.
Cool, thanks.
Ida, did you try
Yeah.
to share your screen or?
No, not yet. I'm doing it now.
Okay.
Sorry.
Did you try Ida or it's still? I mean, we can't see anything here.
Okay, hi everyone. So welcome to this session on fully homomorphic encryption. So the first talk will be on a paper whose title is Threshold Linearly Homomorphic Encryption on Z over 2 to the KZ. And the speaker will be Ida Tucker. So Ida, the floor is yours.
Hi, thank you for the introduction. So yeah, I'm going to tell you about a scheme that we developed, which is for threshold linearly homomorphic encryption, where the message space is Z over 2 to KZ, and this is joint work with Guillaume Castaños and Fabien Laguillons. So I'll start by explaining at a high level what threshold public key encryption is. So the idea is it's just a public key encryption scheme where the secret decryption key is shared according to some decryption policy among various decryption servers. And as any public key encryption scheme, the public key is public. And so anyone can encrypt a message M with this public encryption key to produce a ciphertext of M. So the ciphertext here is the red M. And then in threshold public key encryption, we have a partial decryption where each server is going to use their partial decryption key in order to compute partial decryption shares. And in order to recover the initial plaintext, we have another final decryption protocol, which is public, so anyone can perform this. And if you have a number of ciphertexts from secret keys which satisfy the decryption policy, so we'll say they're part of a qualified set, then combining these ciphertexts will allow you to recover the message. And if the secret keys don't satisfy the policy, the decryption will return an empty set, not an error, it should be an empty set. If we want this threshold public key encryption scheme to further be linearly homomorphic, I mean, this means that one should also be able to perform, by performing operations on the ciphertext, you can perform linear operations on the underlying plaintext. So we have two efficient algorithms, one which, given a ciphertext of M and a ciphertext decrypting to M star, you can produce another ciphertext which will decrypt to M plus M star. And an algorithm called eval-scal, which takes a ciphertext which decrypts to M, a scalar alpha, and produces a new ciphertext which will decrypt to alpha times M star. And linearly homomorphic threshold public key encryption on Z over 2 to the KZ is basically the above.
Aida, we can't hear you anymore.
Okay, and so why is this interesting?
Just a sec, so your
there are
slides.
various applications, but I'm going to just describe one of them, how this can be applied to multi-party computation modulo 2 to the K. So briefly, the idea of a secure multi-party computation is that we have like various parties. Here we have 4. They all have secret inputs, say x1, x2, x3, and x4, and they all want to compute a function of all of their inputs put together, but they don't trust the other parties and they don't want to reveal their secret inputs to the other parties. So one way of doing this would be having a trusted party like this angel here, and all the parties send their secret inputs to this person that they all trust. The trusted person computes the result of the function and sends it back to everyone. But of course, in real life, angels are kind of hard to come across. And so the idea of secure multi-party computation is achieving the same goal, but without a trusted party. So all the participants should keep their secret inputs secret, but at the end of the day, they all want the result of this function on their private inputs. And there's been a lot of interest recently, fairly recently, for multi-party computation modulo 2 to the K. And this is mainly because on standard CPUs, integer arithmetic is performed modulo 2 to the K. So for instance, 32 or 64-bit chips. And if we have secure multi-party computation modulo 2 to the k, we mirror this design. And it means that one has simplified implementation of these MPC protocols. We don't need to perform modular arithmetic or compensate for modular reductions. And it also means that programmers that are implementing these protocols can use optimizations for CPUs directly. And so how does one go about building multi-party computation modulo 2 to the k? Well, there's a kind of common blueprint which is used to build maliciously secure multi-party computation protocols. It divides the process in two phases. So we have a pre-processing phase, which is offline. So this means the participants can do it without knowing the inputs that they're going to use for their computation or even the function that they're going to compute. And it's slow. And the idea is to compute many shares of triplets of the form A, B, A, B, where A and B are random in Z over 2 to the KZ. And these triplets are then going to be used to speed up the fast online phase. And they're basically used as masks during this, this protocol. And so this online phase is fast and information theoretically secure. So we'd like a way to improve the slow phase, the pre-processing phase, because the online phase is already very efficient. Techniques that were used in the past are notably oblivious transfer, which was used in SPDZ2K to create these triples. So oblivious transfer yields a fast solution, but the bandwidth consumption is quite high. Then in Overdrive 2K, they use somewhat homomorphic encryption. So this does improve the bandwidth consumption, but the actual protocol itself is quite complex. And so implementing it for developers is quite hard, and there's more risk of there being mistakes. And then another solution, which is much closer to what I'm going to talk about, is one by, they develop in Monza, which uses linearly homomorphic encryption modulo 2 to decay to produce this raw material. And in particular, the scheme that they use is the Joly-Liver encryption scheme, which is linearly homomorphic and has a message space of Z over 2 to the KZ, which is great. But there's no known threshold decryption for this scheme. And under standard assumptions. And in particular, this means that in Monza, they only have a two-party MPC protocol. And because each party has their own secret and public key, instead of sharing the decryption key, they need to use zero-knowledge proofs to prove to other parties that the other party that what they're doing is correct. And so obviously these zero-knowledge proofs have a negative impact on bandwidth. And so the efficiency gains that one would have expected compared to, say, speeds 2K are not as big as we would like. And so in our work, what we do is we create a threshold linearly homomorphic encryption scheme with a message space Z over 2 to the KZ, which is exactly what we need to fill this gap and efficiently produce these triples and save on bandwidth. So I'll first kind of give an abstract view of the tools that we use to build our construction and how we build our scheme from these abstract tools. And later on, I'll explain briefly how we realize this framework from class groups. So the framework is quite similar to that of Castañas and Lagioni from CTRSA 2015. We have a cyclic group G of order S times 2 to the K, where the GCD of S and 2 to the K is 1. We have a subgroup of G called F, which is the 2 to the k, which is 2 to the k roots of unity of G, and is of order 2 to the k. And there also exists an efficient algorithm for computing discrete logarithms in f. So it means computing x given f to the power x. And finally, we have another group H, which is the subgroup of 2 to the k powers of G and is of unknown order S. And it holds that G is isomorphic to the direct product of F and H. And finally, even though we don't know the order of S, the order S, which is the order of H, and hence the order of G is also unknown, we do know an upper bound S tilde for S. And the security assumption that we use in this framework is a hard subgroup membership assumption, which essentially states that if one samples a random element from the subgroup H or a random element from the subgroup H multiplied by the generator F raised to the power some invertible elements modulo 2 to the k, then both elements should be computationally indistinguishable. And so to build a public key encryption scheme on Z over 2 to the KZ from this, the scheme is fairly simple. It looks like L gamma in the exponent. So we sample the secret key from a distribution which is close to uniform, which induces a distribution close to uniform over H. And the public key is just the generator of H raised to the power of the secret key. To encrypt a message M in Z over 2 to the KZ, we sample a random element R in this distribution DH. And then we compute a first ciphertext element, which is H to the power R, and in the second part of the ciphertext, we encode the message in the exponent of the generator F, and we mask this with the public key raised to the power R, and the ciphertext is both elements, C1 and C2. Finally, to decrypt, one multiplies the second part of the component C2 by C1 raised to the power minus SK, and this should be equal, if this is a correct ciphertext, to F to the power M. And so here we check if the resulting capital M is in the subgroup F. If not, then the ciphertext is badly formed and the ciphertext is rejected. And if so, we return the discrete logarithm in base F of capital M, which, as I mentioned earlier, is efficiently computable. And so it's quite easy to see that this scheme is also linearly homomorphic. In order to add plaintexts which are underlying to ciphertexts, you just multiply the two ciphertexts component-wise and then re-randomize the resulting ciphertext. And similarly, to perform scalar multiplication, one just raises each ciphertext component to the power of the scalar alpha and then re-randomizes the resulting ciphertext. For security, I'm basically going to follow a kind of game-based approach. So I'm going to perform little changes to the original encryption scheme, which I'm going to justify are unnoticeable to anyone who's looking at the scheme from an outsider's perspective, who doesn't know the secret key. And then I'll get to a point where the message is statistically hidden. And since if we have a simulated game, a simulated like encryption scheme where the message is statistically hidden and that's undistinguishable from the real scheme, then we'll be convinced that the real encryption scheme is secure. So the first change that we do from our original encryption scheme is instead of sampling the secret key from a distribution which induces a uniform distribution over H, we're going to sample it from a distribution which is close to uniform modulo s times 2 to the k, and so induces a distribution uniform over G. And because the order of H divides the order of G, S divides S times 2 to the K, this change is unnoticeable given only the public key and the rest of the scheme. The next change we do is purely conceptual. So we compute C2 in a different way. Instead of computing the second part of the ciphertext as f to the power m times pk to the power r, we're going to compute it as f to the power m times c1 to the power sk. But these are actually exactly the same. They're just computed in a different way because c1 is h to the power r and pk is h to the power sk. So pk to the power r and c1 to the power sk are the same thing. The final change we do is we sample an extra element u in z over 2 to the k, in the invertibles of z over 2 to the kz, and we multiply the first part of the ciphertext, h, which was h to the r, by f to the power u. And so now we can notice that the first part of the ciphertext in our previous game and the first part of the ciphertext now are so basically the two elements that one tries to distinguish in the HSM2K problem. And so if this HSM2K assumption holds, which we assume it does, we're ensured that this change is indistinguishable. So now we're in this like final simulation game, which we've established is like indistinguishable from the real encryption scheme. And here we can see that the information that can potentially be leaked on the message is contained in C2, which is f to the power m plus u times sk times pk to the power r. I've just rewritten this by developing C1. And so an unbounded adversary would at most be able to deduce from this the value of m plus u times sk modulo 2 to the power k. And here the secret key sk was sampled from a distribution which was close to uniform modulo s times 2 to the k. So even though the value of sk is information theoretically fixed modulo s, because of the public key, which reveals h to the power sk, the value of sk remains close to uniform modulo 2 to the k because s and 2 to the k are co-prime, and 2 to the k divides the order of G. So we have sk, which is close to uniform modulo 2k. We have u, which is chosen to be invertible modulo 2k, and so the product of u times sk is close to uniform modulo 2k, and so perfectly masks our message, or statistically masks our message m, and this is what we wanted to prove security. And finally, to make this scheme, to obtain a threshold decryption for our scheme, we just noticed that the decryption key sk is only used in decryption for exponentiation to this secret key in the group of unknown order H. And so we use linear integer secret sharing to share the decryption key over the integers. And so our resulting scheme allows any access structure for the decryption policy, and in particular threshold decryption. And so how do we realize this abstract framework from class groups? Well, we start from the original CL framework. In their framework, they provide us very similar abstraction, the main difference being that the subgroup F, which encodes messages, is of prime order Q. In their work, they have two class groups, one with the fundamental discriminant delta K, which is set to minus P times Q, where P and Q are prime, and the class group of non-maximal order of discriminant minus P times Q cubed. In this setting, we can create a surjection between the class group of the maximal order and the class group of the the class group of the non-maximal order and the class group of the maximal order, and whose kernel is of order Q, and we're going to set the subgroup F to be this kernel of order Q. And it would be great if we could just plug Q equals 2 to the K and get our resulting scheme, setting, but that unfortunately doesn't work for various reasons. But the main problem is that if you know the factorization of the discriminant, which is the case in the original CL, you can compute square roots and you can decide if elements are squares. And if that's the case, our hardness assumption, HSM2K, doesn't hold at all. It's completely broken. So we need to have a setting where computing square roots is hard. And so that means that the factorization of the discriminant cannot be known. And so we build our discriminant from an RSA integer n. But we can't choose any n, we have to be careful. In particular, if we're looking into the genus theory associated to class groups, one can see that some genera can leak information on discrete logarithms. And so we have to carefully select the discriminants and hence the RSA integer n, which will allow us to securely work with the group of squares of the class group. Okay, last but not least, performance. So we did do an implementation in our paper, but since then, Bouvier, Castagnos, Imbert, and Laguillaume have implemented a library from scratch in C and C++ called Bicycle, which improves our timings. So I'm providing these better timings. Yeah, as you can see, decryption is for like a message space 2 to the 64 and 128 bits of security. Our decryption is only like 40 milliseconds, which is very efficient. So yeah, that's basically it. Thank you very much for your attention. And if you have any questions, I'd be happy to try and answer them.
So we are a bit short on time. If you have if there is a quick question, we can take it. No question online. Okay, so let's thank Aida again.
Or maybe there's not much time for questions because I went over time.
Don't worry. Actually, we don't have the next speaker yet. So if there is a question, it's a good time. Okay, thank you, Aida. Can you hear us? We see the slides. We can't hear you.
Hi.
Excellent. We can hear you. Hi. Okay, so the next talk will be about large precision homomorphic sign evaluation using few and TFHE bootstrapping. And the talk will be given by Zeyu Liu. So Zeyu, the floor is yours.
Hello? Okay, I guess you can hear me. Okay, thanks. Okay, hi, I'm Zeyu Liu. Today I'm gonna present large precision homomorphic sign evaluation using few TFHE bootstrapping. This is joint work with Daniela Michancho and Yuri Polakov. Let me start by some background information. So what's functional or programmable bootstrapping? Basically means that we can evaluate a cyclic function through lookup table for free while also performing some bootstrapping over some LWE ciphertext. This is first introduced in DM15. And it has two requirements or two constraints. The first one is that it requires the function to be negacyclic. And what does it mean by negacyclic? Basically means that for an input in ZQ, the function needs to satisfy that f of x equals to negative of f of x plus q over 2. The second constraint is that it can only evaluate functions over messages with up to k bits of precision, and usually k is equal to 5 or 6. The reason is that its runtime is exponential in the number of bits, and for the number of bits beyond 5 or 6, the runtime will become quite impractical. And we will use this notation for bootstrapping. So basically we use boot for some function f over x, and it will output the ciphertext that's encrypting f of x for some negacyclic function f from zp to zq. And this p and q can be different, but for simplicity, you may assume that p and q are the same number. There are two bootstrapping methods available now. And the first one is a few introduced in DM15. It efficiently supports arbitrary secrets, but the bootstrapping key size is relatively large. And the second is TFHE, introduced in CDGI16. It provides better runtime performance for small secrets like binary or ternary secret, and the bootstrapping key size is much smaller. Please see MP21 for a more detailed comparison. And we use these functional bootstrapping methods as a black box. So either of the two would work for us. It serves the exact same functionality. There's another bootstrapping method that's recently developed and can be applied as well, but it's not included in this work, but because the paper is published before the new method is proposed. So the main results of our work. So at a very high level, we introduced some new tools to this few TFHE line of work to make the schemes more powerful. More specifically, first we introduced some large precision comparisons. So why comparisons? Comparisons are widely used in machine learning, like in CNN inference or DTT training, and in data science. And comparisons are usually considered hard for FHE schemes, and privacy-preserving ML or DS is an essential case for FHE. Currently, the runtime for this is exponential with the bits of precision, and we want to make the runtime linear scale. The second tool is more general and more powerful. We provide the way to do a large precision arbitrary function evaluation. As mentioned before, now it only supports for negacyclic function and only supports for small precision. We have implemented our schemes, and the implementation is open sourced in OpenFHE and Palisade libraries. So let's start from some high-level ideas. One observation we have is that the comparison is equivalent to sign evaluation. To compare two numbers A and B, we just need to find the sign of A minus B. And another observation is that the sign evaluation is equivalent to computing the most significant bit. Computing the most significant bit is the central part of few or TFHE bootstrapping, but as mentioned, that it only supports for up to, say, k bits. Therefore, our key technique is that we try to remove the large number of digits gradually. For example, if you take a look at this 18-bit number, we just remove the last 6 bits and then remove the middle 6 bits. When we have only 6 bits left, we can perform some few or TFHE bootstrapping to extract the most significant bit. So to do large precision comparison, we first used a floor function, first to round down the last k bits. So if we have this 12-bit number, we just make the last 6 bits zeros. And then we divide this result by 2 to the k, where 2 to the k is equal to 6 here, using modulo switching, and this will make this 12-bit number into a 6-bit number. We cannot directly use modulo switching to round down the original 12-bit number because modulo switching is performing a rounding instead of flooring, which will cause errors for some values near the boundary. And then we repeat this procedure for each digit as mentioned before. After there are at most like k bits left, we can perform a regular few bootstrapping to extract the most significant bit. This one question remains is that the floor function is not negacyclic. So how can we evaluate it? So let me ask a question. What is really a floor function? A floor function is basically we give you a number and you make the last k bits 0. So we achieve this functionality by invoking the functional bootstrapping twice with 2 different negacyclic functions. We first clear the most significant bit of the last k bits. So for an n-bit number from B1 to Bn, the last k bits are from here to here, and we just clear the most significant bits of the last k bits. We clear this by using the follow function. You can double check that this is indeed negacyclic. So this can be achieved by invoking one functional bootstrapping with this function. And then we clear the rest of the k-1 bits, i.e. the bits here. And we achieve this by using the second function here. And again, you can double check this is indeed negacyclic. This is our pseudocode. As mentioned before, for the floor function, we first use the F0 to remove the most significant bit of the last k bits, and then we used F1 to remove the last k-1 bits. And we process this, we use this floor function digit by digit until we have only log q bits, i.e. the k bits left, and then we can use the original few or TFHE bootstrapping to extract the most significant bit. Now let's talk about the more general tool, the arbitrary function evaluation. Let's start with some small plain text modulo. The first constraint we need to get rid of is that the few or TFHE bootstrapping will require the input function to be negacyclic. So can we make the function arbitrary, like remove the negacyclic property requirement? Similar to the floor function, we can use 2 functions to achieve this functionality. We first remove the most significant bits of the input. Sorry. And then for the rest of the bits, we'll be able to evaluate an arbitrary function upon. Because after removing the most significant bit, we can just use a negacyclic function to with k bits to represent an arbitrary function with k-1 bits. But then how about the most significant bit? It turns out that we can raise the modulus from q to 2q, then it will introduce a random most significant bit to the input. So basically with a k-bit input, we will raise the modulus to from q to 2q, and then the input will become k+1 bit, and then we remove this redundant random bit, and then we can perform a negacyclic function, an arbitrary function evaluation using the original few or TFHE bootstrapping. Here's the pseudocode. This is the function we use to remove the most significant bit. Again, you can check that this is indeed negacyclic. And for the input function, we'll use a negacyclic function to represent it. But since the most significant bit is clear to 0, one of the branches will not be used at all. And here we first remove the 1 bit, and then we evaluate this arbitrary function on the input. So now let's talk about how can we make this the small precision into large precision. We do this first by breaking a large precision ciphertext into several small ciphertexts. This is done through what we call a ciphertext decomposition or homomorphic digit decomposition. This can be achieved by calling the large precision sign evaluation, as I mentioned before, and we just need to collect the bits removed. If you recall that in the large precision sign evaluation, we need to remove k bits at a time. We just need to collect the k bits. Then we end up with several small ciphertexts that each encrypting k bits of message. This essentially has the same cost as the large precision sign evaluation. Then we can evaluate each small ciphertext sequentially using a chain shape method or tree shape method. Both of these methods are first introduced in GBE 21. For the chain shape method, as you can see, it's like a chain. So if we first use a few functional bootstrapping to evaluate C0, and we will get a result out. This carry result will be processed with the second input, and together it will be evaluated using the second functional bootstrapping, and sequentially we will get some results. But this method is relatively restrictive because not all functions can be expressed in this way. So they have the second method, which is the tree method. The tree method basically is saying that for the first input, instead of outputting a LW ciphertext, it outputs some lookup table. And this lookup table will be used to evaluate the second ciphertext, and so on and so forth. This is much more general and much more powerful. All of the functions can be expressed in this way. But the catch is that the runtime will be much worse than the first method. But to sum up, using the ciphertext decomposition, we can use these two methods to achieve arbitrary function evaluation over large precision. There are two concurrent and independent works. Both of the approaches use the observation that -1 times -m equals to m, and the extraction of most significant bits using few TFHE bootstrapping. Both of these algorithms use multiplication and requires at least 2 bootstrapping invocations. CROT21 uses a BFE-like multiplication, and KS21 uses a GSW-like multiplication. And we will omit the details. We refer the audience to those 2 papers to find out the details. But our approach does not require any multiplication and can be instantiated using only addition and few TFHE bootstrapping. Here's an asymptotic comparisons. As you can see, the noise growth, our noise growth is the smallest, and also we have less number of bootstrapping invocations compared to KS21, and the same compared to CROT21. Now let's talk about the experimental result and applications. We have implemented our algorithms in Palisade and OpenFG libraries, and we evaluate the large precision comparison for precision ranging from 5 bits to 21 bits. The result is single-threaded and with TFHE bootstrapping using G++ 9.3.0. Here's the result. I will not go into detail of all of them, but as you can see, the runtime basically scales linearly with the number of bits. We have also implemented the arbitrary function evaluation just to prove that it indeed works for only small precision. We have also applied our techniques to heaviside activation function over 256 slots by using CKKS few TFHE scheme switching technique. More generally, one can use our large precision comparison to perform an encrypted branch evaluation. There's another important line of work that uses CKKS to perform comparisons, and those results are all based on polynomial approximation of the sign function. And I would like to at a very high level compare those two lines of work, but the detailed comparison, of course, may benefit from a more detailed survey paper. So for state-of-the-art CKS-based comparisons, it takes roughly 30 seconds to compare for 64K slots, while our method is 6 seconds for one slot. So if the number of comparisons needed is very small, our method will be faster. Also, our method is easily parallelizable, while CKKS supports only limited parallelization, which means that if we have multiple cores, that even if the number of comparisons are larger, our method may still be preferred. Another point is that higher precision of CKS method, like 50 bits, can be very hard to support because the log Q can easily exceed, the log Q is the ciphertext modulus for CKS schemes, can easily exceed like 3000, and this will also cause the ring dimension to grow, which will cause the performance to be much worse. Also, to perform like a 50-bit precision comparison, the scaling factor of CKKS also needs to be increased from 64 bits to 128 bits, which will further reduce the performance. According to our benchmark using Palisade, it can be as bad as like 8 times slower. And of course, our method is much simpler to implement and use. And if multiple invocations of sign evaluation is needed, CKKS-based method needs bootstrapping in between, which will further reduce the runtime, while ours do not. There are, of course, some challenges and potential promising and interesting future directions. The main bottleneck here for the runtime is the TFHE or functional bootstrapping. Each comparison has to be done separately. There's no CRT packing support, and performance can be improved only by parallelization and like using multiple threads or GPU-like parallelization. So one very interesting question that can be asked is that can we develop other methods for functional bootstrapping with better efficiency? And can we leverage BGB or BFE bootstrapping for this? Let me finish today's talk with some conclusions and remarks. So first, in this work, for the few TFHE line of work, we have provided so far the most efficient large precision comparison and more generally large precision arbitrary function evaluation. And moreover, this algorithm can be combined with CKKS. One can use CKKS for polynomial function evaluation and use our algorithms for non-polynomial function evaluation, like comparisons or like activation functions and so on. Of course, this will need some switching technique between CKKS and FEW, and this can be done from using CKKS FEW TFHE scheme switching technique, first introduced in Kimela paper and later improved in Paxos. And OpenFHE is planning to include this scheme switching technique, scheme switching feature in version 1.1. So after this is published, or one can simply use the and as mentioned that our algorithm and also CKKS are both included in OpenFHE already, which means that if this feature is public, one can simply use the OpenFHE library to perform what I mentioned above to incorporate our algorithm with the CKKS scheme. And these are the references, and that's pretty much it for my today's talk. Thank you all very much, and I'm open to take questions.
Are there questions from the audience or online? Huh? No, I don't see any question. Okay, so let's thank the speaker again.
Thank you.
Is in person. Do we have the speaker? Ah, excellent. Please go. So the next talk is on the eval round algorithm in CKKS bootstrapping, and the talk will be given by Seong-Hak Kim.
Thank you for introducing. My name is Seong-Hak Kim, and I'm going to introduce our paper of eval round algorithm in CKKS bootstrapping. So let me start by giving a brief overview of this talk. The main topic is CKKS, which is a representative homomorphic encryption scheme, which is widely known for its ability to deal with real numbers. CKKS bootstrapping is later suggests an operation which recovers modulus of a ciphertext so it can be evaluated arbitrary times. So a problem of this CKKS bootstrapping is it is an operation of recovering the ciphertext modulus, but it consumes modulus at the same time. What I meant is that it is another big combination of addition and multiplication, so it consumes modulus and it directly determines how many evaluation depths are left after after bootstrapping. So we are focusing on reducing such modulus consumption by proposing a simple yet effective variant of CKKS bootstrapping, which consumes less modulus and which can be implemented with a negligible cost on the existing conventional bootstrapping algorithm implementation. The contents will be given as follows. I'll start by giving a background, focusing on this modulus consumption of CKKS. And as our algorithm is constructed tightly on the conventional bootstrapping algorithm, I'll spend some time on reviewing the conventional algorithm, and I'll introduce the eval round algorithm. In this talk, I'm focusing on delivering high-level ideas, so please check details on our paper. I'll not explain the whole concept of homomorphic encryption, but homomorphic encryption scheme can be characterized with three operations, namely encryption, decryption, and a method to evaluate our desired function on homomorphically on a ciphertext. So let me look close in the case of CKKS. CKKS provides three spaces: message, plaintext, and ciphertext, with encoding and encrypting. So focusing on the plaintext and on the ciphertext, these are constructed on the well-known problem called RLWE. So the CKKS can utilize its homomorphic structure, which is constructed on the polynomial with finite field coefficients. With this RLWE problem, the encryption of the plaintext is given as the equation below. On focusing on the message and plaintext, the encoding and decoding map is defined by discrete Fourier transform. It is natural to define the map by this, since they are polynomials and vectors. And then one more thing on the CKKS is that the message are complex vectors and plaintext are integer polynomials, so we have to scaling up to encode the message and scale down to decode the plaintext. So in short, the encoding and decoding map is given as the below. One problem arises from the scaling up. It is the size of encrypted plaintext is growing by each multiplications. In brief, suppose the plaintext 1 is scaled up by scale factor 1, delta 1, and plaintext 2 is scaled by delta 2. Then the simple multiplicated result will be scaled by delta 1 multiplied by delta 2. So if we naively execute the evaluation circuit, the size of the encrypted plaintext will grow exponentially. Actually, main feature of CKKS is dealing with dealing with the size of encrypted plain text efficiently, it supports the operation of rescaling to maintain the size of encrypted plain text, which is an operation of dividing the ciphertext modulus and the encrypted plain text at the same time. So rescaling deals with the size of encrypted plain text in exchange of consuming modulus. And the amount of modulus consumed is exactly the same as the encrypted plain text has scaled down. It is often visualized by the diagram on the right side. So we have some plain text of size M1, and we have another plain text of size M2. Then the multiplicated result will be size of M1 multiplied by M2. And we just cut out the LSBs by rescaling. And the cut out amount is equals to the modulus consumption. Such a rescaling is a brilliant way to deal with the size of encrypted plain text, but still there is a challenge. The challenge of all these CKS is that through evaluating the circuit, the ciphertext will eventually run out the ciphertext modulus, so it cannot be evaluated any further. So bootstrapping is later suggests to recover the ciphertext modulus. So we just bootstrap the ciphertext at the bottom modulus and continue the evaluating ciphertext. So it completes the CKCAS at the fully homomorphic encryption scheme. The problem we are focusing on this CKCAS bootstrapping is that it consumes modulus. Actually, the first step of bootstrapping is projecting to the higher modulus, so its modulus is already recovered. But we have to adjust the value of projected ciphertext to the original message, so it consumes modulus from that. So after bootstrapping, the ciphertext modulus way goes down from the fresh modulus. And the size of the ciphertext modulus after bootstrap directly determines the possible evaluation depth till another bootstrap. So we'll go on reviewing the conventional bootstrapping algorithm. The input and desired output of bootstrap can be defined as shown. So input is the ciphertext which is encrypting a desired plain text, but it is on the bottom modulus. We desire on bootstrap output to be on another ciphertext which is encrypting the same plain text, ignoring the encryption error, but on the greater ring of greater ciphertext modulus. So the conventional bootstrapping algorithm is proposed with 4 steps, namely mod rates, coif slot, even mode, and slot coif. So I'll go on briefly explaining each steps. The first step of mod rates is just projection. Note that ciphertext of bottom modulus is also an element of higher modulus. So we just regard it as another modulus on the ring of higher modulus. Recalling the definition of decryption, we can know that the decrypted plain text of moderated ciphertext is somewhat deteriorated with Q0i term. So the problem becomes to remove this superfluous Q0i term from the deteriorated ciphertext and recover the original encrypted plain text. The following steps deals with it, but there is a problem that we want to manipulate the coefficients plain text directly, but we have only methods for manipulating and encrypting messages. It's also known as dots. And the operations deals with encrypted message are plain homomorphic operations. But we can think of sending those coefficients to slots by applying homomorphic encoding. So recalling the definition of encoding, this is a linear map, so we can just homomorphically evaluate this. So after sending those coefficients to slots, we just deal with the PT plus Q0R term by homomorphic evaluation and recover the space by applying inverse of the coefficient slot. So on the following step, we apply homomorphic operation on PT plus Q0I to compute the original encrypted plain text by applying modular reduction. This modular reduction is simply approximated by sign function, so it is not hard to approximate this function. And there have been various approaches to enhance this. But I will not cover those approaches because our suggestion can be applied on any of the implementations of Eber mode. So I'll go and explain Eber round algorithm. The construction of Eber round algorithm is consisted of two minor modifications on the conventional bootstrapping algorithm. The first modification is on the coefficient slot step by alternating it to its variant, which is computing imprecise result in exchange of consuming less modulus. By changing the step of coefficient slot to coefficient slot sharp, we get an erroneous result. But on the following modification of alternating Eber mode to Eber round, we can deal with the error effectively. So we'll look how can it be done. The first modification is coefficient slot, which can be done by just adjusting parameter. In detail, we use lower scale factors to scale up less on encoding IDFT metrics. So looking on the coefficient slot, which is an homomorphic matrix multiplication, so it is an inner product with encoded diagonals and rotated plain text. So what I want to point out is that it is encoding such diagonals. By adjusting its scale factors, we can adjust its valid bits or precision of the IDFT coefficients. So by using lower scale factor, we can expect the imprecise result. But at the same time, because the rescaling consumes modulus as much as the scale factor scaled down, we consume less modulus, which is a desired behavior of our algorithm. So after taking advantage of consuming less modulus, we have to deal with such error by alternating Eber mode to Eber round. Eber round is semantically it is an homomorphic evaluation of modular rounding, and it can be formally defined by identity subtracted by Eber mode. So simply defining by this equation, hence, since Eber mode is a homomorphic evaluation of modular reduction, the identity minus Eber mode is mapping to the value to the closest multiple of a wanted integer. So applying eval round can completely alternate the existing step, and the proof is given as below. So the left side is the step 2, 3, 4 of the conventional bootstrapping algorithm. And we utilize the homomorphic structure of the slot coef and eval mode as coef to slot. So if we rewrite the eval mode by identity minus eval round, the identity can be evaluated separately with eval round. So we get the equation of identity minus eval mode slot coef eval round coef to slot bootstrap is the same, computes the same result from the conventional one. Although the eval round stack computes the same result of the conventional one, there is an advantage of that eval round is much more stable to the input error. So it can be directly seen that as the input changes, the modular reduction, the result of modular reduction changes directly, but modular rounding does not. So it is much more stable to the input error. So we can take advantage from the stability to consume less modulus. By applying the algorithm described so far, we evaluated as on the table. We developed our own CKKS code to test the algorithm on practical parameters. So we give the size of message and bit size of modulus with practical means. But we, maintaining the precision, we obtained less modulus consumption by 84 bits. So it is sufficient amount to increase evaluation depth after the bootstrap. It becomes more and more effective when it is applied on the parameters with heavy bootstrap circuits. So the original evaluation depth is small. The great advantage of this algorithm is that it does not require such assumption or effort to evaluate or implement. So it is easy to upgrade on the original bootstrapping algorithm, and it is superior to the existing one. What I want to point out is that the hard thing is to set the scale factor of coef to slot. Hence, this determines how much error on the coef to slot shop step is occurred. But the firm setting on the scale factor will be described on the paper. So, summing up, we have implemented, so we have suggested a novel algorithm of conventional bootstrap, novel variant of conventional bootstrap to consume less modulus, and it is to implement on the conventional bootstrap implementation. Thank you for listening.
Are there any questions?
Thank you for your presentation. I have a question about eval round. So can you show again the definition of eval round? So Okay, this is the second question. Anyway, so what I don't know is that I don't know about the role of identity function. So if I change the identity function by some non-preserving functions, such as some automorphism in CKKS, so you know that automorphism just change the index of the coefficient. Then do you think it happens the same effects as the identity function? What do you think about that?
I think there will be no problem on changing such functions, but if you are talking about the programmable bootstrapping,
yeah, that's right. Well, just the automorphism. So you define the Libel round as an identity minus Libel mode. So then we can redefine some such functions such as automorphism minus Libel mode. So we make a new function and we can plug this function into the parentheses, and we obtain a new equation and. So the left side is replaced. Left identity function is replaced by some automorphism, and right side is some modification is occurred. But I think the effect. So what I want to know is there is some differences between what I talking and your works. So,
as I understand, your question is to comparing your question that this work is another instance of programmable bootstrapping. Am I right? I think identity function just the role of identity function is it's just my thinking, but just non-preserving function. So it just do nothing. So some non-preserving function. I think the same work because they just preserve the ROM. So there's no error implication. So I think I can change the identity function to some non-preserving function. So such as so there are some famous non-preserving function in CKKS. So the automorphism. So I just curious about there are some possibility to optimize this your ideas. Yes, I also think that applying such technique on the Iber round is also available, same as the conventional bootstrapping. So Iber round can be applied to the programmable bootstrapping. Yeah.
Okay, thank you.
Any other question from the audience? There was a question online, yeah. So let me get it. Okay, so it's a question by Hilder Vitor Lima Pereira. Please, could you comment more about the column bootstrap bits precision on slide 22? If we start with scaling 2 to the 60, what is the final precision? Okay, so then there is an addition to the question, which is then starting with small scaling factor, what is the final precision?
I'm not remembering the exact value, but it is much higher than the conventional bootstrapping one. It is natural because on this diagram, we only dealt with error of coefficient slash up, but actually there is some existing rounding of coefficient slot. And there is a polynomial evaluation error on model reduction. So the blue graph is not exactly evaluated by error mode. So error round, defined by the identity minus error mode, is not exactly same to the given red graph. So the bootstrap precision will be somehow a little higher to the proposed current proposed evaluation.
I think we can thank the speaker again. Okay, so the next talk is an online talk.
Hello.
We can hear you, but we don't see your slides yet.
Yeah, okay. Let me try again. Well. I'm not sure. Maybe you could stop this sharing that is going on already. I don't know if this is blocking me somehow.
Okay, just a sec.
Thank you.
We can see your slides. Are you still here?
Can you see the slides? Okay.
And we can hear you. Excellent.
Okay, sorry for the technical problems.
Yeah, sure, no problem. So, okay, so the last talk of this session will be on a paper titled Final Faster FHE Instantiated with Ntrue and LWE. And the talk will be given by Hilder Pereira. Hilder, the floor is yours.
Thank you very much for the introduction. So this paper is a joint work with Charlotte Bonte, Ilya Ilyashenko, Junghyun Park, and Nigel Smart. Please, if there is any problem, you just tell me. You can turn on your microphone and tell me, okay? So the starting point here is essentially a comparison between these two hard problems, the RLWE, the ring learning with errors, and the N-true problem, right? So the ring learning with errors is very famous, and it's used to construct basically most of the fully homomorphic encryption schemes that we have. And what the RLWE allow us to do is to sample pairs of polynomials from a polynomial ring, so we can define these integer polynomials with degree bounded by some parameter n, and then we can sample pairs of polynomials where this second element here has a hidden structure. It actually hides the secret S, but they look uniformly random, right? If we don't know S. But we have a kind of similar problem, the N-true problem, that also allow us to hide a small polynomial into another element of this ring, so another polynomial.
Hilder,
this,
Hilder, just
yes?
a sec. Yeah, so we were stuck on the first slide. Okay, thank you. So now we can see the second slide.
Okay, if I do this, is it moving?
No. Yes. Yeah, there seems to be
okay.
some delay. So now we're on the ring LWE and N-true problem slide. Huh?
Yes, okay.
Okay,
Thank you. So I was just saying that the N-true kind of give us the same. We can construct this polynomial B, a ring element, that hides this small secret, and at the same time it looks random. But the difference is that for the RLWE, we need a pair of ring elements, while for the N-true, we just have one polynomial, right? So if we could somehow, it looks like these slides are stuck again. Okay, so if we could somehow replace the RLWE problem by the N-true problem, in the FHE schemes, we should, like, the intuition is that we would be able to use half of the memory and half of the ciphertext, because of, instead of working with pairs of polynomials, we would work with a single polynomial, right? These slides are not passing, right?
We are still on slide number 3 with ring LW and N-true.
Oh man, this is not going. Okay, I will just try one thing, please. Let me just put this. You are not seeing it, no?
Hilder, do you see
Yes.
how to solve the problem, or?
No, I'm sorry. I'm trying to share, but I click on share and it's not sharing.
Otherwise, I've been told that you gave us a pre-recorded
Yeah, yeah,
video.
yeah.
So in the worst case, we can just.
Yeah, maybe it's better. I'm sorry about this.
Yeah, sure, that happens. Huh? I mean, so yeah, so
I will stay online. After this, we can answer the questions, at least if people have any question.
Yeah, okay. So let's do this. Huh?
final, faster fully homomorphic encryption instantiated with N-true and LWE. This is a joint work with Charlotte Bonte, Ilya Ilyashenko, Jung-Yoon Park, and Professor Nigel Smart. So most FHE schemes are based on the ring learning with errors problem. This problem allows us to sample pairs of polynomials from a polynomial ring, so a ring with integer polynomials with degree smaller than some parameter n, and although this pair of polynomials hide the secret value s, they look random. But actually there is another problem defined over polynomial rings, which is well known. It's the N-true problem, and with this problem we can hide a secret polynomial f into one single polynomial that also looks random. So you can see that the N-true allow us to use one single polynomial instead of a pair of polynomials. So if we could somehow replace the RWE problem by the N-true problem in these FHE schemes, the intuition is that we should be able to use half of the memory and maybe half of the running time. And actually this observation has already been used in the past, so some authors tried to construct FHE schemes using the N-true problem. For example, there was this scheme Yash that was more efficient than the corresponding RLWE based schemes at the time. But the problem is that the ciphertext modulus, this parameter q, that these schemes based on the N-true used were super polynomial in n, while the first N-true ciphers, they used like N-true encryption, N-true crypt, they used very small values of q, just linear in n. And it turns out that the N-true problem is insecure when q is too big in comparison to n. Now we understand well why this is the case. So before we essentially just knew these q recovery attacks, which have time exponential in n. But there are new attacks called sublattice attacks that whose hardness depends very strongly on q. So the situation is the following: when q is linear in n, the sublattice attacks are more expensive than the q recovery attacks, and then because the q recovery attack is already exponential time, the N-true problem is very hard. But as we increase q, the sublattice attacks becomes easier and easier, and at this point, if q is exponential in n, then the sublattice attack becomes polynomial. So if you have an attack that runs in polynomial time, this means that N-true problem is very easy. So the sublattice attacks become easier at some point it costs essentially the same as the q recovery attack, and this point is called the fatigue point. So new results, especially this paper by Lauduca and Vorden, computed this fatigue point as n to the power of 2.5 essentially. So if we choose parameters with q larger than this, we are in this region, which is known as overstretched. And in this region, the N-true problem is not as hard as we want because of the sublattice attacks. So when we use the N-true problem to instantiate our schemes, we have to restrict ourselves to this region here, so below the fatigue point. So the first contribution of the paper is constructing a scheme that looks like the GSW scheme, but it's based on the N-true, and because of this it has a faster external product. So the external product is the main operation of this type of schemes, these GSW schemes. And then we use this NGS to bootstrap a scheme that is based on the N-true. And then because this scheme is based on N-true and NGS is also based on N-true, this means that we obtain FHE based only on the N-true problem and with parameters below the fatigue point. And also we use NGS to bootstrap a LWE based scheme, and when we do this combination of LWE and N-true give us a bootstrapping that is 28% faster than TFHE's bootstrapping and uses about half of the memory that TFHE uses. So now I'll explain a little about our scheme NGS. So the secret is just the small polynomial from the n-true problem. And then we define two types of ciphertexts. A scalar ciphertext, which is just a polynomial, so we have an n-true sample and we add the message is scaled by some integer factor delta. And the vector ciphertext is composed by essentially a vector of this scalar ciphertext here, but this delta, instead of a single delta, now is a vector with powers of some value b, right? So we have a vector of n-true samples, and then the message is multiplied by the vector of powers of some base. We can choose this base b here, and then L is log of Q in this base b. So in the original GSW scheme, this instead of this vector here, what we have is a matrix like this. So you can see that here we have L again, so 2 times L rows and 2 columns, right? So 2 times L times 2, this means that we have 4 times L elements, and here we just have L elements. Then to run an external product, we just have to take this scalar ciphertext, we decompose it into a vector of L entries, and we multiply it by a vector ciphertext, right? So this is just an inner product. So the external product is an operation between a scalar and a vector ciphertext, and it costs just L multiplications on this polynomial ring. So when we compare it with the GSW scheme, we have this scalar ciphertext now is just one polynomial instead of 2, and the full ciphertext in our case is a vector with L polynomials, while in GSW it's a matrix with 4 times L polynomials. And then the external product is just an inner product in our case, so it just costs L polynomial multiplications. But with the GSW scheme, the external product is a vector matrix multiplication, and then it costs 4 times L polynomial multiplications. Now we will explain how we use the NGS to obtain fast bootstrappings. So we used the framework from FIU and TFHE, which is essentially this. So we start with an LWE encryption of some message M with some large noise E, and we want to obtain an LWE encryption of the same message but with a small noise. So what TFHE and essentially FIU does is this. We have a main loop using external products, and this is evaluated with the GSW because the GSW implements the external products. And in this main loop we are essentially running the linear part of the decryption of this scheme in the exponent of this monomial x. So what we obtain is M scaled message M plus some noise here in the exponent, and this is encrypted under the ring LWE instead of the LWE. And then there is a extraction which takes this M from the exponent and puts it in the coefficient, and also a key switching so that we go from the RLWE back to the LWE again. And then this gives us a LWE encryption of the same message M, but now this noise E doesn't exist anymore. We just have a new noise E prime, which is smaller than the original noise. So this is how TFHE does it. Well, we already have the external products with the NGS, so we can run this part. But when we do this, we obtain a monomial encrypting this same value, but encrypted under n-true instead of RLWE. And then this means that we need somehow to extract and key switch for n-true now, right? And also, if we want everything to be based on the n-true problem, then we need a new scheme based on the n-true instead of the LWE. So we will start with this. We show how we constructed the base scheme based on the n-true. So we used this matrix n-true problem, which is kind of the corresponding of the LWE for the RLWE, right? This is n-true without the ring. So what this M n-true says is that if you have a random, a small norm matrix G and a small norm matrix F, you take the inverse of F and you multiply by G, then you get this matrix C that looks random, just like for the polynomial case, right? Well, but if you take the ciphertext to be a matrix, then to decrypt you have to multiply by the matrix F, and we don't want the decryption to be a matrix multiplication because this is too complicated. We want the decryption to be simple, so just an inner product, vector multiplication, right? So what we do is, instead of considering the whole matrix C, we just take the first row of C and we use this as the ciphertext, right? And if you check it, the first row of C is actually the matrix G times the first column of the inverse of F, right? So now we have a vector of dimension n. And then to decrypt now, we just encrypt the message in the first entry of this vector C. So to decrypt, we just need to multiply by the first column of this matrix F instead of by F, right? So if define this small f here as the first column of F, the decryption now is just this inner product C times F. And then, because this is just inner product, we can compute it in the exponent of X using the external products of the NGS scheme. So now the bootstrapping goes like this. We start with an encryption of some message M under this vector small f, and then we use n external products to multiply this vector ciphertext by this secret vector f here. So what we obtain is this monomial, and in the exponent of it we get the error plus the scaled message, right? And this is a normal n-true encryption, so it's encrypted under this polynomial f and belongs to this polynomial ring. And then we run the extraction essentially in the same way as TFHE. So this eliminates this E here, removes this noise E that we had in the original ciphertext, and brings M from the exponent to the coefficient here. And then we propose a key switching for n-true ciphertexts, right? Because this is encrypted under n-true. And we apply this key switching to go back from an encryption of dimension capital N to dimension small n, and also to switch the key from this polynomial f to the vector f that we had in the beginning, so the output has exactly the same format as the input. So it's an encryption of the same message but with a smaller noise, right? And then we can set all the parameters below the fatigue point. So now we have FHE with fast bootstrapping based only on the n-true problem, right? So we start with an n-true encryption of some message M with large noise E. We use the external products and we get an n-true encryption of this monomial with the message plus some noise in the exponent. And we have the extraction and key switching, which give us an n-true encryption of this same message M again, but with a smaller noise E prime. We also used NGS to bootstrap a scheme based on the LWE. So when we have a scheme based on the LWE, just like in FEU or in TFHE, the ciphertext have this form. So to encrypt a message M under secret key S, we sample this uniform vector A, and then we compute this integer B as the inner product of this uniform A times the secret S. We add some noise and the scaled message, right? All of these modulo Q. So to decrypt, essentially we have to take this public A, multiply by S, this is an inner product just before, and subtract from B. So this we can already do using the external products of NGS, right? Then we obtain an encryption of this monomial B minus A times S, which is an encryption of the scaled message plus some noise, and all of this encrypted under the secret polynomial F of the n-true problem. So this means that we already have this first step of the bootstrapping framework, right? We can start with LW encryption of some message M with large noise E. We run the external products using NGS, and we get an n-true encryption of this power of X. Now, to go back to LWE, we proposed a key switching that switches from the n-true to the LWE problem. So we run the extraction as before. This gives us an n-true encryption of M and removes this E. And then we run this new n-true to LWE key switching to switch from an encryption of M under n-true to an encryption of M under the LWE problem. And this closes the loop and completes the bootstrapping procedure. So now we are going to see the practical results. We implemented everything in C++, and this implementation is publicly available, so you can go to this GitHub repository and download it and install and play with it. And because we mainly wanted to compare with TFHE, which is the state of the art for binary circuits, we used the same FFT library as TFHE, and then we compiled our code with the same compilation flags as TFHE, and we tried to use similar parameters as the ones used in TFHE. So we have two FHE schemes now. We have one that is based on n-true, that we call M n-true here, and one that is based on the LWE. Right? And then we bootstrap both of them using NGS, which is based on n-true. So these are the parameters for these base schemes. So the dimension of the ciphertext that we want to bootstrap with n-true is 800, and with LWE is 610. So for TFHE, they use LWE ciphertexts, and then the dimension is about 600 as well. And for the NGS, the degree of the polynomials that we have in the polynomial ring is always 2 to the 10 in our case, and what changes essentially is the decomposition base from one case to the other. And for TFHE, this dimension here is also 2 to the 10. So this means that our FFTs, the Fourier transforms, are over the same dimension as in TFHE, right? So they are really comparable. And we have to remark that this value n here, this tells us how many external products we have to run. So the thing is, for M and true, we see that we have 800. This is much more than in the LWE case. So even if each of our external products is cheaper than in TFHE, because we have to run much more of them, at the end our M and true scheme is slower than the TFHE. But for the LWE case, because the number of external products is similar to the TFHE case and each external product is cheaper, then our LWE with n true is faster than in TFHE. So when we run TFHE in our experiments, we got that each bootstrapping takes around 66 milliseconds. And then for our MN true, we got 92, so this is kind of similar, same order of magnitude, but slower. Right? But our combination of LWE and N true runs the bootstrapping 48 milliseconds. And we can see here that that's the main reason, because the number of FFTs is much smaller in our case. So essentially what we got is that if you check here, the bootstrapping key and the key switching key, they are much smaller than in TFHE. So the key material that we need is about half of what TFHE needs, and the bootstrapping time is about 28% faster. So to conclude, we proposed an FHE scheme based on N-true with parameters that lie below the fatigue point, so outside of the stretched regime. And so this brings back N-true FHE to the game, and we hope that this result will bring more attention of the academic community so that people can do further research on N-true based FHE and maybe improve the efficiency of our scheme or create new schemes based on N-true. And well, we proposed this scheme that looks like a GSW but is based on N-true, so we called it NGS, and it has a smaller ciphertexts and faster homomorphic multiplication when compared to the RLW based GSW. So we hope that this NGS will also be useful for other applications, so essentially where GSW is used, maybe we can use NGS instead. And finally, we proposed this FHE scheme mixing N-true and LWE, and we saw that this runs faster than TFHE. So that's all. If you have any questions or comment, please feel free to contact me, and thank you all.
Okay, so we are running late, and the attendees from the other room are starving in front of the food. So if there is a quick question, we can take it, but otherwise, I suggest we do it offline. Any quick question? Okay, so let's thank Hilda again.
Thank you very much.
The vegetarian options are, I mean, there are more vegetarian options in the food stand closer to the grand ballroom. So I mean, so for this dinner, the two food stands are not symmetric. There's more vegetarian options closer to this ballroom. So if you are not vegetarian, maybe, I mean, prefer the other food stand if possible.